Hello everyone, welcome to the course, Introduction to SQL. This is the first session of the course. It's an introduction to the course content, instructor, and some of the prerequisites. So when students come to Udemy, they generally have a lot of questions. With so many classes to choose from, which one is right for me? Does it have the right content I want to learn? Do I have the required prerequisites to take the course? And this lecture is aimed to answer these questions so that you can make better decisions on the course, whether you want to choose it or not. So let's talk about the course content first. Why SQL? And the answer is simply because it's popular. What you are seeing is a data set from Indeed, the job seeking site. From 2015 to 2019, the top 10 tech skills sought by employers. And guess which one is number one? Of course, it's SQL. You can see that. And recent years is popular. Python is popular, AWS popular, and Java has been popular as the de facto computer language. And look at the difference between SQL and these languages. SQL is steadily the first. And SQL has been number one skill for a long time, even before 2015. And just a matter of fact, in all of computer languages created or invented in the 1970s, SQL is the only one that is still in popular demand. You probably heard about something like Fortran or COBOL. All these are SQLs. They were created at the same time, around the same time as SQL, and nobody's using that. That's not the right word, but only a handful of people are still using those. But SQL is still in mainstream and still popular and strong. And in the foreseeable future, SQL is still strong. So that's why we want to take this course for introduction to SQL, the foundation. Something about an instructor, which is myself. I'm a long-time data warrior. I have been in the data management and data engineering field for more than 20 years. I started as a report and the ETL developer, then gradually becomes a data architect and a data project lead. I received a master's degree from Virginia Tech in computer science. Currently, I'm also serving as an adjunct professor in Columbia University and the City University of New York and other institutes. So I teach Introduction to Relational Database and SQL, which is the same course in both universities to undergraduate students and to graduate students, which happens to be the target audience of this course too. I would expect you to be the equivalent of a second year or third year undergraduate student of a computer science subject area, or can be a graduate student that's seeking for, let us outside computer science area, but seeking for knowledge of a relational database and SQL. For example, those students I have generally come from a statistics or analytics domain, and in recent years, a lot of data science students will also take the SQL course too. And also, you can be a professional who just want to know better about relational database and SQL. So all these are potential students of this course, and of course, it's up to you. But the one thing in common, no prior SQL relational database knowledge required. And talking about the course content, we're going to go through quickly the relational database definition, the relational model, entity relationship model, and normalizations. This brief introduction lay the foundation of SQL and tells us why sometimes SQL behaves like this or like that, why SQL is defined this way, all because of the relational model that is underlying the founding stone for SQL. And then the bulk of the content is in SQL, the structured query language, we will use Oracle Live SQL as a practicing environment. And in some of the lectures, we are going to provide PostgreSQL instructions to tell you the difference between Postgres and Oracle. However, the SQL introduced in this course is the ANSI standard SQL. So whatever you learn here, the majority of that is portable to any relational database platform, including PostgreSQL, including MySQL, SQL Server, and some others. All right, this is so much is for the course content. If you, after this session, you feel this course is right for you, just go ahead to the next lecture. I will see you there. Okay, let's start to talk about introduction to relational database. So what is a database? The Wikipedia definition of database is an organized collection of data, generally stored and accessed electronically from a computer system. So there are two parts to this definition. The first part is an organized collection of data. It's a place to store data. This is the most important part. And the second part, it says it's generally stored and accessed electronically. Modern day databases are all electronic. So as far as data is concerned, what you are looking at is a piece of census file, which is from late New Kingdom of ancient Egyptian time. It's about 1000 year BC. So ever since the very beginning of civilization, we human beings have been using data a lot. Like in this census file, it's basically a list of houses and their owners. Someone wrote this down on a piece of papyrus, and someone else collect this, deliver that to the pharaoh's archive. And apparently, this pharaoh's archive is a place to store and organize the storage of data, which is one of the ancient databases. Of course, there's another part of the definition that the modern databases are electronic. And this is one of the earliest data processing system, the IBM 7090, which was developed in December 1959. This is one of the earliest data processing system. And ever since then, we have been facing the same challenge again and again, over and over. The challenge is how to present the data sets, the real world data sets in computer. If you think you have a piece of papyrus with the house owner and their house and their count of their cattle, how to store that? Modern data is definitely more complex and larger than these collections of papyrus. We have to use a formal design and modeling technique to better present these data sets in our system. Before 1970s, it was pretty much a trial and error time. We used a file system for data storage, but there's a lot of problem with this approach. There's basically no clear definitions, no clear relationships between files. It's hard to manage. I personally worked on some conversions of those existing legacy file system into modern database. And it's really a pain to go through the definition of each file and the record, because for those systems, there's no clear definition or distinction between each file and the records it contains. The same file can contain different definitions, different records, and it's a layered approach. So it's hard to manage, hard to develop, and hard to maintain. Also, this file system approach causes data duplication, and sometimes because there's no dependency clearly defined, it causes data loss. And also there are security concerns around this file system approach. So in 1970, Dr. Edgar Foucault from IBM proposed the relational model, which has 2 points. One, even the most complex data sets can be represented as relations. And two, relations are operated through relational algebra. So basically what he proposed is a mathematical model, a mathematical layer between the real world problems and the computer implementations. We no longer arbitrarily create file and dump data in. Instead, there will be a formal process of identifying real world entities, real world relations, put this into a mathematical model and use this mathematical in-between to create a database system. Why this is important? Because relational model can be systematically, consistently, and logically represented in databases. It has a mathematical theory behind it, which is the relational algebra. It's simple to develop and implement. It's consistent in results across different platforms. And it can be applied to almost all business scenarios. So database that is based on DataCott's relational model is called relational database. They organize data into one or more tables or relations of columns and rows. And ever since DataCott created this relational model, 90% or even say 99% of the databases invented was a relational model, a relational database. Most commercial or open source database systems today are relational. Some of you have already heard some of those names, like for commercial database systems, like Oracle, SQL Server. For open source systems, like MySQL and Postgres. All these are very popular. And this class is all about relational database. We will go through the definition of relational database. We're going to give a brief introduction on how to design a relational database. Then we will talk about the main tool of relational database operation, which happens to be SQL. Talking about relational database design, how to create a relational database. We already said relational model is a mathematical layer in between real world and the database and the computer implementation of database. So there are two arrows here. We need to map real world into relational model. Then we need to map relational model to database. Accordingly, there are two steps in the relational database design. The first design is a logical design. Through a systematical process of database modeling, we map real-world questions into a logical model, which contains a collection of relations. The result is a logical model. The second step is physical design. We will map the relations in the logical model into database objects such as tables. The result is a physical model. We will go through these two design steps in the next few lectures. I will see you in next lecture where we will talk about logical design. In this lecture, we are going to go through the steps of logical design. And in particular, we are going to talk about entity relationship model, which is the design method we use for logical design. So what is entity relationship model? It's the most popular logical design model of relational design. It's an enhancement on the general relational model. It divides relations into two categories, entity and the relationship. It defines how entities and the relationships interact with each other. It provides a systematical way of mapping real-world objects into an entity relationship model. So what is an entity? Entity is a noun, basically anything existing in this world that you describe using a noun. It can be a person, a place, a thing, or event. For example, student is an entity. A course is an entity. An instructor is an entity. Or like a wedding event, it can be an entity. Some place like classroom can be a place, can be an entity. Each entity contains the attributes. Each entity basically have properties of their own, and these properties are called attributes. For example, a student can have an ID, can have a name, can have a date of birth, can have an address. A course can also have an ID and a name, like Introduction to SQL. It can belong to a department, to a computer science department. It can have a location, whether it's in a certain room of a certain building or it's online. So all these are entities and their attributes. However, we of course cannot draw a picture of entities every time we mention that. So what we created is a shorthand representation of each entity. In this case, we will just put entity name first, followed by parentheses, and we put their attributes inside of this parenthesis. For example, a student, the shorthand representation will start with the name student. And then in the parentheses, we are going to put all their attributes, name, ID, date of birth, and address. Similarly for course, it will be course starting with the name. Then in the parentheses, we have ID, name, department, and location. One thing to note here is there are different attributes that have the same name in different entity. For example, name. Student have a name, course have a name. How do we distinguish them? The way we distinguish them is by adding the entity name in front with a period. So it will be student.name or course.name, which will tell us which attribute we're referring to. This is called qualified representation. So much this is for entity shorthand representation. Now, talking about relationship. What is a relationship? Relationship is the association between entities. It usually is a verb. Whatever you can use verb in the real world, it can be described as a relationship. For example, registration. A student register a course. So in this case, it will be a relationship between student and the course, and the name is registration. So we will put registration as the relationship name and use a parenthesis to enclose the two entities to signify that this relationship of registration is the relationship between student and course. Of course, as you look at this, the previous example, the shorthand representation of this relationship, you will notice we put all attributes of both entities in the relationship. But then the question is, do we need all these attributes of an entity in the relationship definition? How many attributes do we need? For example, do we need a student date of birth in the registration? Is the student going to change his or her date of birth just because he or she registered in my course? The answer, of course, is no. Date of birth is something belongs to the student. It does not belong to registration. Then how do we better represent this entity inside the relationship? We only need a handful, a small set, a subset of the attributes when we represent each entity either in the relationship or in somewhere else, right? So the question becomes how to identify an entity instance. How many attributes do we need to represent an entity? That's a topic, that's a very key topic that we are going to cover next. It's called functional dependency. It defines the relationships between attributes. So X, attribute X, we call it functional dependent on Y. If and only if each X value is associated with precisely one Y value. For example, ID is functional dependent on name. We have a student ID, and then immediately going to the school registrar, you will know the student name, right? However, if you know the student name, given that student may have multiple students may have the same name, you may not know which ID you should use, right? So if you have some student called Eric, do you know the ID? You probably will get 2 or 3 in your department. That's not a function dependence. And then on the other hand, we have the function determination, which means whatever column will determine the other. It's a similar idea, just a different direction. So we talk about candidate key. What is a candidate key? If a set of attributes can functionally determine all attributes in the relation, this set of attributes functionally determines the relation. What does that mean? For example, if you have student ID, do you know student name? Yes, you do. How about date of birth? And how about address? And in normal situation, you would say yes and yes to all these questions. Fundamentally, as long as you know student ID, you know everything about the student. And that means if you have the student ID column, you will know the whole entire entity of student. In this case, we call this set of attributes the key of this relation. So student ID is the key of student. And also, you can have multiple attributes in the key. For example, in most cases, you need to use the combination of state and your driver license number if you ever need to use that as a key. In this case, both attributes form a set of attributes, and this set of attributes, of 2 attributes, becomes a key. So the definition of candidate key is set of attributes such that the relation is functionally dependent on this set of key attributes, which makes sense, right? And the second one is what we call the minimum rule. There is no subset of the attributes for which one holds, which means if you give me a set of multiple attributes as a key, all these attributes are necessary. A quick example is you can have student ID and student name. And because ID already determines everything, the combination of ID and name will, of course, indeed also determines everything. But here, name is not necessary. You only need ID. So the combination of ID and name, although it can functionally dependent on although it can functionally determine the relationship, the relation, you don't necessarily need it to be the candidate key because name is optional. Only when you have the minimum set of that column ID, that becomes a candidate key. So we're talking about a primary key. It is, if you haven't heard this before, you will hear that a lot when you're handling SQL and the relational database. Primary key is basically the best candidate key. And this definition is based on assumption that there might be many different candidate keys. For example, to identify a student, you can use a student ID. You can also use his or her social security number and use a name plus address. Usually, in the same address, you won't have two people with the same name. So name plus address can also functionally determine that student. But all these candidate keys are not created equal. For example, address. The problem with name address is they are all characters. They are all text strings, and they are very error prone. How many times did you make a mistake in typing your address or even your own name when you submit a web ordering form? I know I'm guilty of that. I always type in something wrong. And because of this, name and address is not the best thing to use as a key. ID is much easier, so is social security number. And in fact, in the 70s, 80s, 90s, most of the government agency and the financial institute, like insurance companies, they do use social security number as a primary key of their record. However, in recent years, with all these internet breaching security thing and all the privacy concerns, as well as all the legislations, people are steering away from using social security number and trying to use a random key instead of a social security number. Social security number right now is only used when it's absolutely you have to. An example is at the list here, HICN versus MBI. So basically, these two are two ID columns used by the U.S. government's CMS, Center of Medicare Service. It's basically the federal agency taking care of all the Medicare stuff. They used to have an ID column called HICN, which is a social security number plus 2 digits. So if you see this HICN, you will immediately know the first 9 digits is the patient or member's social security number. So because of this, this is actually considered a serious security concern, because if I got your paperwork, I will be able to know your SSN just by snitching into your mailbox. So so CMS later on start to move away from HICN and to MBI, which is a randomly generated string to represent each member. You can Google this HICN versus MBI and get some interesting insight into it. So this is primary key, how we choose primary key, and we usually use ID. The way we represent this primary key is to use underscore in a shorthand representation. Like here, we have a student and we have ID underscore and course ID underscore, which signifies these are the primary key of an entity. Sometimes when you do your homework or in your SQL preparation, you use a text file, and it's not possible to do underscore in a text file. In this case, a commonly accepted solution is to use star to enclose the attribute. There will be student star ID star, and this will signify this is the primary key. And let's go back to, with all this attribute functional dependency and key definition, let's go back to relationship. How do we represent the relationship? Relationship is created when you're putting two entities together, right? We get back to this point again. And now that we know each entity is represented by its key, you can use the primary keys of both entities in the relationship and the primary keys only to define this relationship. For example, in this registration example, because it comes from the relationship between student and course, you only need to put the primary keys of student and course, which is registration, student ID, and course ID. the combination of these primary keys automatically become the primary key of the relationship. So that in this registrations case, the combination of student ID and course ID forms the primary key of this registration. And the relationships can also have its own attributes. For example, registration can have a registration ID, can have a staff name, whoever did the registration, and the registration date, and possibly a deposit. These are called descriptive attributes or relationship attributes, but they are not the primary key. The primary key should be, and only should be, the primary keys of all the entities. So once we are able to identify a relationship and represent it in the shorthand representation and putting entities together, how are these entities related to each other? And this actually defines the type of relationships. For example, department and course. In all the school I've been into, each course only belongs to one department. I never seen any course belongs to multiple departments at the same time. So each course has only one department. But each department, of course, have a lot of courses. In this case, we call them the relationship one-to-many. One department has many courses. And sometimes the extreme of one-to-many is one-to-one. For example, like in the US, each state have one and only one state capital. And each state capital only belongs to one state. There's no state capital that becomes the capital of two states or more. So this is one-to-one. And of course, you will start asking, is there many-to-many? And we just go through this, the registration. In the registration, a student can register multiple courses. And multiple courses will have, each course will have multiple students. Like introduction to SQL can have usually when I teach, it will be 20 students to 30 students. That's the class. At least I hope so. I hope there's at least one student attending the course, right? So this is many-to-many. But then how is relationship determined? How do I know whether this is one-to-many or one-to-one or many-to-many? The answer is you need to go to the business, go to actually how it works in real world and do some business research. Then you need to go to do some data discovery. For example, in the state capital case, anyone have some certain kind of education in the US, you pretty much know all 50 states and you know their capital. So you know it's a one-to-one based on your knowledge. But that's because the data is relatively small and it has a finite number. What if it's a student and course one? Then you need to start a business and make an understanding of how it works. And then you go to the data, get a small sample set, analyze this, and determine this many-to-many, confirm it's a many-to-many. This process is called data discovery. And last thing about in this lecture is the distinction between relation and the relationship. It's a very confusing topic because the name is similar and they are usually used in the same context. So they have a similar name, but meaning is different. So when students start learning, this is one of the things that they always get confused about. And I won't blame you if you do the same, you feel the same way right now. But remember, relationship is just one type of relation. Relations includes both entity and relationship. Entity relationship model is a refined version of relational model. It's an enhanced version. It has more rules, more distinction. But entity and the relationship are two particular types of relation. And relationship and relation are two different things. Of course, because entity relationship model is probably the most popular relational model, we will talk a lot about relationships, and you need to know relationship is a type of relation. It signifies, it defines the interaction between entities, which is another type of relation. Hope this makes sense, and I will see you in next lecture. In this lecture, we are going to go through physical design of a relational database and show you a quick example. So the physical design as a second step in the relational database design is a relational modeling process, and it's not related to entity relationship model. Let me repeat this again. Physical design is a second step in a relational database design. It's not related to entity relationship model. It's a relational model process. But because entity and relationships, both of them are relations, so they follow the same design process. We just do not make distinction between entity and relationship in this step. It will be the same design principle applied to other non-entity relation models, if there's any. But still, because entity relationship model is the most popular relational model, we will not talk about other models in the class. So how do we map relation in relational DB? Once you have completed the logical design, you have a series of relations, being it entity or relationship. You want to map them into objects in a relational database. Relational database, by its name, is designed to best represent a relational model. So they are designed to have a series of two-dimensional tables. Relations in the relational model are directly mapped to each two-dimensional tables. And each distinct instance of a relation becomes a row in the table. For example, the entity student is a relation. It will be mapped to a table called something like student or students or student table. Each student, the information of each student, ID, name, these things will be mapped into one row in the table. And the attribute of a relation, for example, ID or name, will become the column of rows. And if you imagine a two-dimensional table, something similar to an Excel spreadsheet, you can see some rows and columns in this table definition. And each row represents a distinct instance of the relation, each student, and each column represents an attribute of the relation, like student ID and student name. All tables are two-dimensional. All tables are sets of rows with the same columns. Remember, this is the same column across different rows. Different rows have the same column structure. Each row must be unique because duplications will provide no new information. And each column has its own name and the data type, and is the same across all rows. So for entity, one entity is mapped to each table. And then attributes, as we talked about, are columns. It will be student, for example. In the student table, we should foresee to have student ID, student name, date of birth, etc., etc., whatever you define in the entity. For relationship, there's also one relationship per table. Remember, each table is a relation, and because entity and the relationships are both relations, each entity, each relationship will be mapped into a table. And we talked about primary keys. The primary key about relationship is a combination of primary keys of all the entities in this relationship. So what will be the relationship columns? It will be the keys, the primary keys of the entities. And also we will have the relationship attribute, the descriptive attributes. Now, one exception is that if it's a one-to-many relationship, they can usually be merged into functional dependent entity table. For example, there's a relationship between department and the course. But if you have a department ID with a course ID, usually you can push the department ID column into the course table. So the course table will have a department ID, which in fact is a relationship between course and department. But because it's one-to-many relationships, we usually just merge them. So I will just briefly mention it here, and we will not talk about this anymore. But when you are doing advanced SQL database design, this is some consideration you will run into. And each column has data type. The data type defines what value the column can hold. It can be an integer, it can be decimal, or text, or date. And the difference between integer and the decimal is decimal contains decimal points. Integer, of course, is just a whole number. So let's quickly go through an example of relational database. This is PG admin, which is stands for Postgres admin. It is a relatively full-scale management tool for a relational database. The relational database here is a Postgres SQL. And as I show you the dashboard, you can see it can sense information like server sessions, tuples in, tuples out, block in out. Although you may not know what it exactly means, you can pretty much guess that means some data flowing in and out, hardware and software considerations. So this is, like I said, it's a full-scale management tool. It's way too advanced, and it's complex, and it's a database specific. For these reasons, we will not cover them in this course. What we are concerned about is just in showing you what the relational database may look like. So in this relational database, what we call test data, you can see there are a whole bunch of tables. We already defined course, instructor, student. For example, if we opened up course and have columns defined as ID, name, instructor name, tuition, right? We can also view the data. So that's how this table or how this entity is stored. The course entity is mapped to the course table, which have 4 columns. Each column is an attribute. The ID, which is the primary key, it's a name, a course name, it has an instructor's name, and it has its tuition. Tuition is apparently a number, a numeric value. So it also happens to have 4 rows. Each row is a course. Like instruction tool of force taught by Obi-Wan Kenobi, and possibly a throat choking 101 from Darth Sidious. So all these are how you map an entity or similarly a relationship into a relational database table. And from here, you also see there are much more in the relationship database, which we are not going to be covering in this course. But if you take advanced database design or specific database management class, you will learn. So much for this course, for this lecture. I will see you in next lecture. In this lecture, we're going to talk about normalization. So we have talked about logical design and the physical design. we have talked about how to design a relational database. But just as in any other design, there are good designs, bad designs, and ugly designs. And based on my 20+ years of data management practice, I can confidently say bad designs can happen, do happen, and will always happen. And they happen a lot. Why do we don't like bad design? Because bad designs make it difficult to use the database and increase the cost of usage and ownership. So improving bad design is a highly skilled and well-paid job. It's called data architect. If you want to take on this highly skilled and well-paid job, you'd better learn this normalization process really well. Let's give an example of the bad design. We have an invoice, a student registration form from a company called Dataforce Academy from a galaxy far, far away. And you can see this is a regular everyday registration form. You have the student ID and name, his address, invoice number, date and date. And for this particular registration, you have a course ID and name listed. For each course, you have a course ID, name, instructor, and tuition. A quick and dirty, and really dirty way of designing this database is to put every information from this registration form into one table. And that's what you get. You get student name, address, city, all this information, registration related information into one row. But for this particular registration, as there are multiple courses, you put them into repeating groups like this, 1 and 2. For each registration, you have multiple courses. And the way we write this in shorthand representation is by use of parentheses inside the entity. This course information in parentheses is inside registration and it's repeating. The issue with this design, while I'm cleaning up, is that, actually 2 issues. The first issue is called repeating groups, and the other is called duplication of information. So the rows containing repeating groups, each registration have multiple courses. Why this is an issue? Because as we talked about relationship, about the relational modeling, each repeating group is a sub-relation inside a relation. So every time you process the registration relation, you need to do further processing. You need to go into each sub-relation and handle that as it's another relation. It's not an atomic instance of relation anymore. Thus, it loses the fundamental advantage of relational modeling. It's not a relational modeling anymore. That's the issue with repeating group. It's fundamentally wrong, fundamentally deviate away from relational modeling. Another issue is duplicated data. So you see here, for the same student, we have address and the city and the state and zip. We can also have another registration here. For if we have this for the same student, Luke Skywalker, then the address, the city, the state, and the zip will all be the same. This is the repeating of information. Why this is a problem? Because in this case, the same operation must be performed in multiple locations. If Luke moved to Yoda's house, Dagoba, then we need to update this address for each and every row. And in this case, it's just one table, so it's relatively simple. But in the real world, the same information can be spread out to different tables. If you want to update all of them, that's a performance hit. And if you forget to update one of them, then there will be data inconsistency. So wherever you are reading the data, it will affect the result of the data. We handle these two issues by going through a process called normalization. Normalization is the process of structuring a relational database in accordance with a series of so-called normal forms in order to reduce data redundancy and improve data integrity. Now let's explain this in a little bit further. Normalization is based on normal forms. There are a whole set of 6 to 8 normal forms. Exactly how many depends on how you count. These normalization forms, each of them is a rule in which if the table meets the rule, it will achieve a certain level of desired property. Multiple levels of normal form exist. A higher level of database normalization cannot be achieved unless the previous levels have been satisfied. I know it's a little bit too abstract, but think about normalization, normal forms as a rule, as a ladders of rules that you have to climb one step at a time. You become first normal form compliant. It will give you certain property that your data is not as bad. And as you go further, go to second normal form, you will achieve another set of properties that your data becomes cleaner and cleaner. Eventually, there are like 6 normal forms that you can do, but usually third normal form or a variation of third normal form, which is BCNF, they are good enough for real-world applications. And that's what we are going to teach in this class. Anything beyond BCNF, we're not going to talk. So normalization is generally achieved by decomposition. Decomposition is the process of breaking up or dividing a single relation into 2 or more. The reasoning is, as the relation has fewer columns, its functional dependency becomes simpler to handle, and thus we can avoid some of the complexity and the redundancy caused by these complex dependencies. We will, starting from first normal form, decompose the relation into first normal form compliant. Then we can work on this to achieve second normal form, then third normal form. In next lecture, we are going to go through the process, and I'll see you there. In this lecture, we are going to talk about normalization forms. Basically, it's a process how to do normalization using normal forms one by one. So let's start by talking about the issue we discussed on the original table. We are going to use the same table we demoed in last lecture, the Data Force Academy registration form. And we talked about the issue with the repeating group, that we have multiple courses in the same registration. Now, first normal form is a rule set up to ensure tables does not have repeating group. What it says is the value in each column of table must be atomic. For example, in the previous example, the course name, Introduction to the Forest, and the Moisture Farming 101, there are 2 course names in this registration. So this column is not atomic. That breaks first normal form. What can we do now? We do that by decomposition. We will break up the repeating group by breaking the groups into separate rows. Each repeating group will be a separate row. But the new primary key will be the original primary key plus the embedded entity's primary key. So this example, registration, originally we have a student ID or student name, and we have a course, and we also have a registration. Then we will break it up. We will break the parentheses. Let me try to mark it. So we have this repeating group, which is here. We will break each course into a separate row, so that here there's no more parentheses. There's no more parentheses in here. Of course, this parenthesis is actually the one for registration. But we break course out, and for the new table, the student name is the original key and plus the key for the repeating group. The combination of these 2 attributes are the new primary key for this entity. Once you achieve these, you will have an atomic value. You have an atomic value in each row for this column. Make sense? Okay, let me clean up these drawings again. And let's go to the next page. Let's talk about partial dependency. What if the primary key is a combination of columns? Just like the one we have is student name and course name. These 2 are the primary key. So it's a combo key, but then some columns are only dependent on one of the columns, like it shows here. Address, city, that's a repeating group we talked, that's the redundancy data we talked about. All these 4 columns are dependent on student name. They are not dependent on course name. Meanwhile, instructor name and tuition are functionally dependent on course name. They have nothing to do with student. Whether the student is a Luke Skywalker or Leia, the instructor will be the same, the tuition will be the same. This is what we call partial dependency. Some columns are functionally dependent on one part of the key, not the whole key. So the issue is they are repeating for each row of that student. So here we see the repeating group, the redundancy caused by partial dependency. How do we handle that? We use second normal form to handle that. In second normal form, first of all, you must be in first normal form. And then every non-key attribute must depend on the whole key, not just the part of it. Based on the example, I believe you should have a good understanding of that. And of course, because it's determined by part of a key and whole key, if your key is already one single column and the first normal form, then it's automatically second normal form. Then how do we make sure a table is in second normal form? We decompose it by breaking up the partial key and its dependency into another relation. So, but the key columns still must remain in the original table. So what's happening here is we have this course and its dependencies. We also have the student and its dependencies. We break this student and dependency into a separate table, thus removing the partial dependency, as well as course into a separate table, removing this partial dependency. But in the original table, after these address fields and the instructor fields are gone, we still need to keep the student name and the course name, which is the original primary key. By removing the partial dependency, these three tables now achieve second normal form. So if you look from here, from the shorthand representation part, it used to be student name and a whole bunch of dependencies. Course name and another two dependencies. And we break it out to course. We break it out to student. And whatever remains in registration, student name, course name, which is the original key, primary key. So this is how we'll achieve second normal form. Now, how do we handle this type of dependency? Let's say in course name, there's also another column called the instructor affiliation. For example, Obi-Wan Kenobi is a Jedi and Darth Sidious is a Sith. What is the relationship between instructor and instructor affiliation? Apparently, instructor name will determine instructor's affiliation. And here, we have a function dependency between course name and instructor. We have another dependency between instructor's name and the instructor's affiliation. The second functional dependency, which is dependent on a non-key column, is called transitive functional dependency. The issue is, apparently, you can see here that the word Jedi repeats itself for every time that Obi-Wan Kenobi is showing up. And that's what we need to get rid of by applying third normal form. Third normal form, for a table to achieve third normal form, it must be in second normal form first. And then it has no transitive dependency. In this case, we will decompose by breaking up transitive key and its dependency into another relation, but the transitive column must still remain in the original table. So this is how we do it. We have instructor and instructor name and affiliation, which is the transitive dependency. We break it out as its own table, but the transitive column still must be remaining. By doing this, we have a third normal form compliant table. So here you can see that the original instructor affiliation goes to here. But the original course name plus the instructor is still there. That's how you do third normal form. And when we talk about third normal form, a lot of times you will also hear something called Boy's Code normal form. Boy's Code normal form is an enhancement of third normal form. The official definition is all non-trivial dependencies are on table key. Trivial here means it's self-referencing. And when will this happen? It will only happen when there are multiple candidate keys. There are multiple compound candidate keys. Each candidate key consists of 2 or more columns, and there are multiple combination possibilities to form key. This is a very rare scenario. So Boyce called normal form address of this issue. And if there are no compound candidate keys, or there are only one set of candidate keys, Boyce called normal form is equivalent to third normal form. So it's an enhancement of third normal form to a particular scenario. We will use the term third normal form to reference both normal forms in this class. And it's actually the same convention in many, many other classes and the books. So we talked about the 3 normal forms. We talked about how to break up a bad design by using decomposition into a fairly well design. Let's quickly review what are these about. And if you want to remember that in the fast way, remember first normal form, each table has a key for all dependencies. There's no repeating group. It has a key. Second normal form says dependency is on a whole key. And third normal form says all dependencies are only on the key, not on some transitive column. So has a key, a whole key, only on the key. That's what these 3 normal forms are all about. That's how you break up a table or a relation into finer pieces. But sometimes you may want to combine relations into larger pieces. This process is the opposite of normalization and is called denormalization. One good example of denormalization is the address field. We all know in the regular address field, you should have a state, you have a zip. And if you think about the relationship between zip and state, a zip can functionally determine the state, right? As long as you know the zip code, you will immediately be able to tell which state it is. It's a one-to-many. So if you want to, based on third normal form, then this actually is a transitive dependency. In the address, you should just use a zip, and then you should create a zip state relational table, which pointing to some state value for each zip. However, a common practice is still to put zip and state in the same address record. Just like in any address table, you will still have address, city, state, and zip. There's no need to put state out. The reasons are twofold. One, normalization may cause performance issue. If you, for each address, run a query to get a state based on zip, there will be a performance hit. And two, the other reason is that state and zip is a relatively smaller combination. You won't save much by creating this zip and state. The saving is small, but the cost may be bigger for each row. That's why we do a denormalization, and it's a commonly accepted practice to have a zip state, both of them inside an address block. There are other reasons that you might want to do denormalization, like in a data warehouse or in a NoSQL database. But these are all beyond the topics covered in this course. So we will leave them to you. If you're interested, feel free to go ahead and read some documentation on them. Otherwise, I will see you in next lecture. In this lecture, we're going to talk about entity relationship diagram. Entity relationship is an easy and clean way of designing a database. However, in a modern database, you constantly have hundreds, if not thousands, of entities, and the relationships between these entities can be quite complex. So people have been always trying to find a better way to clearly present these entities and the relationships so that it's easier for user to use. One way is this what we call entity relationship model. It uses rectangle to represent entities and use the lines between rectangles to represent their relationship. And in addition to rectangle and the line, we also use line style or line marker to represent the type of relationships, whether it's a one-to-one, one-to-many, many-to-many. This idea was raised by Dr. Peter Chen in 1976, and that's what he shows in his program, in his presentation. You have entity department, you have an entity employee. Their relationship is represented by a diamond in between them. And the type of a relationship is marked by the words here. So this is his original design of an entity relationship model, diagram. And if we apply this diagram to our design, we will have a student rectangle, a course rectangle, a registration diamond in between, and we will put M and N or N and N here to represent that, to indicate this is a many-to-many relationship. And we will put attributes of each entity and the relation into ellipses, circles connecting to this entity or relationship that it belongs to. So this is a clear representation of the relationship entity and the relationships that we have. However, it's also a little bit complex. There are too many objects flying on a diagram. So people have been working on simplifying the different ways of simplifying this original diagram. One variant that we have is to put all the attributes inside the entity, the rectangle, like course ID, course name. They put it inside. And there are more further simplifications. For example, a very common way of doing this is called arrowed diagram. It simplifies it further by removing the relationship diagram, the diamond shaped. It uses arrow to indicate relationship type, thus removing those 1 and n markers in the relationship lines. So here we have a student. Again, we have a student, and we have a course. And this arrow indicates this is a many-to-many relationship. It's similar like in the original diagram, using a M and N. And here, one side there's arrow, one side there's no arrow. So this is a one-to-many relationship. Now, be careful on the direction of arrows. Many books use this way to represent one-to-many. Some, like in our case, use the other way for one-to-many. And because both usage are in different books, it can get really confusing. And that's why we are not going to use them in this course. What we are going to use in this course is what we call clawfoot diagram. It uses a clawfoot like this to indicate one-to-many relationship. So here, between student and the course, it will be many to many. Whereas between instructor and the course, it will be many and one, or the other way around as a one-to-many. So there's no confusion on that. And the one remaining part, so that's why we will use this diagram in our course. But there's one issue with relationship attributes. If there's some attribute for this relationship, for example, registration ID, you can actually insert a rectangle here and call it registration. Let me make it clear. You can put a rectangle here and says that's the registration. And here, then here, inside this registration, you can put attributes of this registration. So this is how we draw Crawford, how we do this entity relationship diagram. Let's quickly do a demo. Let's clear that. Okay, so I'm bringing up a Microsoft Paint. If you want, you can definitely use other tools. There are many different tools like Irwin or SQL Development Modeler or Lucio Chart. They can all be used to creating ERD, the entity relationship diagram. In this case, it's because it's very simple. I'm just going to use a diagram, Paint. So what I'm going to do first, I'm going to create a rectangle. Oops, I think I need to clean this up first. And I'm going to signify that I will do a text. The first one is student. Then I have a, somehow it's underlined. I don't need this to be underlined as this is actually the name of the entity, but I want to bold it. And student ID, of course, is the key and student name. And this time I don't want it to be this because it's just a regular attribute. And I'm going to put go back and put a diagram. And by moving this inside, this is the student entity. Now let's do another diagram. Which is course. I'm going to put course, and this one has to be bolded. That's the entity name. Course ID, which is the primary key and need to be underlined, and course name, which is a regular attribute. Now let's draw relationship between them. It will be a line, and somehow I will also draw a Crawford. Oops. Looks like I have a bad. Certainly not the best drawing in the world, but I think you get the point. So this is the simplest Crawford you can have. And just by keep on doing the same thing, You can expand this drawing over and over, and there are easily many different ER diagram samples online. You can take a look and see how they are drawn. All right, and this pretty much finishes our lecture on entity relationship and the relational model and entity relationship. And starting next lecture, we are going to go inside SQL, and we will see you there. In this lecture, we are going to give an introduction to SQL. So SQL is the abbreviate for Structured Query Language. It is the standard way of a relational database operation. It can create, maintain, and drop tables. It can insert, update, delete, and query data from or to data table. It's descriptive, not procedural. Unlike procedural language like Java or Python, it does not tell computer what to do. It tells computer what it wants. I want to get something. I want to get something done. But how to do that is up to computer. It has an ANSI standard. It's same across different vendors. So whatever we learn in this class, although we'll use Oracle Live SQL as the environment, 99% will be applicable to other DBMS. There are two types of SQL statements. One is data definition language, also called DDL. Another is called data manipulation language, DML. As the name suggests, the data definition language is create and drop or alter table structure. The manipulation language is about data. It will insert data, delete data, update data, and select data for your reference. So these 7 are the most important statements of SQL. Create, alter, insert, select, update, delete, and drop. We will cover each of them in the following lectures. We will use Oracle Live SQL for all demos. It's a lightweighted relational database, mostly based on Oracle. And it's compatible with most databases. And we will note when there are differences. So let's talk about DBMS as we are going into we are getting to a point where we're talking about Oracle, which is some kind of a database software vendor. And Oracle itself can also be referenced to a DBMS, database management system. The DBMS is the software that interacts with end user applications and the database itself to capture and analyze data. So the key here is it's the software. 1, it's a software, and 2, it interacts between end user applications and the database itself. And the database itself here means the data stored somewhere. Remember, we talked about the definition of database. It's a place to hold data. DBMS sits between this place of holding data and the user applications and bring data back and forth. So this is the architecture diagram. We have on top, number 1 is a computer server hardware. And the DBMS itself is a software running on top of this hardware. Also, the database is also a storage on this hardware. So DBMS will read and write to this database. And meanwhile, you and me as user are sitting in front of our computers using different software like Python application or analytical applications connecting to DBMS. DBMS sits between us and the computer server or database itself, communicate between these two components. That's what DBMS does. I hope this explanation is clear enough. Let's go to next page and talk about applying this idea to Oracle Live SQL. Oracle Live SQL is offered a free service offered by Oracle. Oracle runs the server in their Oracle Cloud, and Oracle also provides the DBMS software running on their remote server. These two parts is completely Oracle. And the end user is you. You will use a web browser connecting to this DBMS and run Oracle SQL. Whatever you need to run, DBMS will accept it and run it. That being said, how do we run this Oracle Live SQL? There are two tasks. First of all, you need to register with Oracle. And second, you will log in and run sample SQL to confirm the registration. So I'm bringing up a Google Chrome, and I'm going to search Oracle Live SQL here. And Oracle Live SQL here, you can click on this link, which will bring in the login page. So this is the login page, and if you already set up an account, you can click on here. You can type in your username and password and sign in. If you don't have an Oracle account, you can create an account. Let me click on the Create Account button first, show you how to register. So the Create Account page is up. You need to enter, just like many other web registration form, you need to enter your email address, password, country, a series of questions. Once you enter and you click on Create Account, in a while you will receive Oracle's registration form, registration email, where you need to verify your account and log in inside, which I believe all of you are familiar with, and I'm going to skip this part. I already created my own Oracle Live SQL account, so I'm going to log in, and I'm going to show you the interface. So this is the Oracle Live SQL interface. Once you get inside, maybe you are on home page. You can click on SQL worksheet right here. Right here, make it more obvious. This SQL worksheet, you'll click here, and it will bring you to the SQL execution page. Then we quickly type in some SQL. You don't need to know. I will cover what it means later on, but it's just how it works here. ID int. And you can click on actions. And then you can run from here. That's how you run the SQL. Now, once you are able to run the SQL, we will base all our discussion later on this Oracle Live SQL. And from here, we will see you in next lecture. In this lecture, we are going to give an introduction to PostgreSQL and provide you with a brief on how to install it on your local machine. The reason I bring up PostgreSQL is because I have multiple classes. I'm teaching the same courses to different students. In several of the classes, I use Oracle Live SQL. And in some of them, I use PostgreSQL. It depends on school policy and basically whatever is available from the school. I use Oracle Live SQL in the whole teaching because it's easier and it's simpler. But for other students, they may be needing to use a PostgreSQL. So I will give a quick introduction on PostgreSQL, its architecture. In the next lecture, I will show you how to install PostgreSQL in your local machine and how to run the test sample SQL there. If you are not using Oracle, if you are not using PostgreSQL, you feel free to skip this part as well as the next lecture, which is the installation part. So we go through DBMS just now. What is in a DBMS? In particular for PostgreSQL, we are going to install the DBMS, the PostgreSQL service on your local machine. Your local machine is going to be the computer system hardware, and the database is going to be stored on your hard drive. The DBMS, which you will install very soon, is a PostgreSQL service. And again, you are the user, and you are going to use a series of applications, including your Python code, to connect to this PostgreSQL service. PostgreSQL also provides you with an out-of-box tool, management tool, and query tool called pgadmin, which will help you a lot in running against PostgreSQL service. And next lecture, we're going to talk about how to install PostgreSQL on your local machine. And I will see you there. So let's talk about how to install PostgreSQL on your local machine. First of all, let's launch a Google Chrome, and let's search for PostgreSQL download Windows. Of course, I choose Windows because this is the local machine I have. If you have a Mac or Linux, you need to choose that accordingly. So now we have Windows installer. That's the one that I'm going to click on. Oh, let me clear. And now we need to choose the download the installer link. So once you get inside this page, there's a whole bunch of PostgreSQL versions with a supporting OS. And of course, the one that we are interested in is this. So I'm going to click here. It's loading, and I believe it's downloading right now, right here. Right here. It will take, oh, it's already done. I was about to say it will take a while to download, but this one is pretty fast today. So let's wait a little bit. Okay, it's almost done. Now let's show it in folder and kick off the execution. Let's run it. As you can see, it will take a while to launch, but as long as the mouse is spinning, it's coming up. Now it depends on your system. In Windows, sometimes it will ask you to install some Visual C++ runtime library first. In that case, just choose agree and install the component. Eventually, it will lead you to this, oh, it's actually coming up here right now. I was not expecting that, but yeah, just let it run, the Visual C++ component, and eventually it will lead me to the PostgreSQL setup screen. Okay, that's the screen that we start from. We choose next, And these are the standards that we are going to use. And here you can see there are multiple components. The first one, of course, is a PostgreSQL, its server itself. This is the DBMS that we are going to use. The second one is pgadmin4, which is the management tool that comes together with PostgreSQL, and that's the one that we are going to use to interact with PostgreSQL locally. And the third and fourth, Stack Builder and the command line tools, we're not going to use these in our class, but feel free to keep them. And now let me get rid of this, and let's start next. And you will be asked for a data. Data directory is where PostgreSQL stores its data. It's a database. And here you will be asked to provide a password for the database super user. Each database has a super user, and by default is called Postgres. Here you are asking to provide a password for this PostgreSQL. Because this is a demo, I'm going to just use Postgres. Postgres. Oops, I think I make it a typo. Okay, now I'm going to go through, and remember this, super user's name and password are both Postgres. And port is by default 5432. Use the default locale, all these are default, and you can quickly go through the settings, make sure they're all correct. And now you can start installing. Okay, it started installing. I am going to pause the video, and I will be back when the installation is done. So the PostgreSQL installation is completed. Now here you will have a Stack Builder setup checkbox. You can feel free to keep it if you want to set up Stack Builder, but in this course we do not need it. So I'm going to uncheck it and click on Finish. So once we click Finish, in the PostgreSQL part, you can launch something called pgadmin4. This is the management tool we are going to use to connect to PostgreSQL. Now, PostgreSQL itself, the DBMS, is already set up. It's up and running in our local machine now. All we need to do is to connect to it. And this pgadmin is the tool to use. So it will take us a while for pgadmin to launch for the first time. I'm going to pause this again until it finishes the launching. Okay, so pgadmin4 launching is completed. It basically launches a browser, a new tab in Chrome, and point that to local machine, to local host, it's a 50131 port. And this is how we start running the administration part of PostgreSQL. Now it is asking you for a master password. This password is for pgadmin, for the management tool. It's different from the password we entered when we set up super user. When we do the installation and set up super user Postgres, we input a password Postgres for that user. And this one, the one currently we have, is the password for pgadmin. For this purpose, we will set up a Postgres too. We want to make sure it's the same so that it's easier for us to remember. Of course, I can do this only because this is the course. This is for, there's no security requirement. In your own system, you'd better have some good password and make sure it's protected right. We're going to click OK. No, I don't want to save it. And now you can see it's a regular object browser and panel site. Click on Postgres. So this time, we need to enter the password for the user Postgres. this is the server user's password. So, but as I said, we choose the same, which is the Postgres, and we want to save the password. Okay. And you can see a lot of things here. All the administration stuff, all the administration management things, and login users and table space. This is more for data storage. For all you can see here is for the database DBMS management system, there's a lot of things to happening, but they are outside the scope of this course. We're going to ignore those and only to create our own database here. We want to create a database. So right now you need to right click on the database and choose database, create database. And let's call it test data. And click on save. So now that we have this test data, again, right click on test data and choose query tool. You need to right click and choose query tool. Once query tool is up and running, we can do some quick SQL to make sure it's running perfectly. So I'm typing in a series of SQLs to make sure PostgreSQL is working properly. Let me start running. Table created. Let me insert into test values 1. And I highlight and I run. Now let me do a select star from test. Highlight and I probably haven't shown you how to run. It is here. Once you highlight a SQL statement, click here and it will start running. Now let me run this select and it returns the proper value. And drop table test. I will highlight it. And again, I'm going to click on this button to run the SQL, drop SQL. And now it's dropped. So we can see the SQLs are running fine and the whole Postgres database is running perfectly in my machine. In this lecture, we will finally get into SQL, get hands wet, by creating create and drop statements. As we talked about this at the beginning, relational database is all about two-dimensional table. All the entity relationships and the relations basically are mapped into two-dimensional table inside a relational database. So SQL operation is all about table manipulation and data manipulation where data stores in the table. And to make this happen, the first thing needs to be happening is to create a table. And of course, you can reasonably imagine the last thing will happen in the SQL lifecycle is to drop table. And these two are the things we are going to talk about in this lecture. So here is a quick sample of create statement. If we have an instructor relationship or instruction table, where you have the instructor name as the primary key and the instructor affiliation as one of the attributes, when you translate this into create table, or should I say when you try to implement this shorthand representation in SQL, that's the SQL you're going to write. You're going to write create table, instructors, instructor name with some kind of a data type. We talked about data type before, and primary key. You need to define the primary key. So let's look at the syntax, the exact syntax of create statement. It starts with the keyword create table, and then followed by the table name. So here we have the create table instructors, then followed by parentheses. What's inside the parentheses is the table content. If you remove this part, the table content part of instructor, if you remove the highlighted part, all you see is create table instructor parentheses. And then we will insert table content inside this parenthesis, which will include column definitions. It will come first. You have one column called instructor name. You have another column called instructor affiliation, followed by other table properties. And the one that we are going to cover in this class is primary key. You will need to define the primary key, which is instructor name here. They are enclosed in parentheses and they are separated by comma, but there's no comma for last content. One issue I always see students make is that after the last content, they add a comma afterwards, which is wrong. And you do need commas in between different table contents. So this is the table content definition. There are multiple ways of defining primary key. You can define the primary key as column constraint. So instead of writing primary key at the end, you can put create tables instructor, and for this instructor name, you add the primary key afterwards. This is useful when primary key have only one column. For single column primary key, you can directly after the primary key definition, after the primary key column name, and after the data type. But it has to be before the comma. So it's between the data type and the comma. That's when you add primary key. Another issue I always see students making is they will define instructor name char and put a comma, then put primary key. That's wrong. A column definition is one integrated part. You need to write column name, data type. If it's primary key, add primary key. Remember there's a space in between, and put a comma. Of course, if it's the last column, then no comma, like here. So this is for single column. You add the primary key directly afterwards. But if it's a multiple column, if a primary key is multiple column, or you simply don't want to write the primary key after column name, you can define primary key as another part of table constraint. That has to be after all the column definitions. Column definitions comes first. After column definition, you add primary key, you put the parenthesis to enclose all the primary key columns inside. The order does not matter, but you need to include all of them. You need to include all the key columns, and there's this primary key ahead, telling DBMS that you are defining the primary key. So let's repeat. In the create table statement, you write this keyword, create table first. You put the table name, use parentheses to enclose table content. In the table content, you start with column names and their data types, and separated by comma. Then you add this primary key constraint, which has a parenthesis enclosing all the primary key columns. You need to define the columns first before you need to define the columns first before using them in the primary key definition. you do not put data type in this primary key definition. So this is the table content definition. You can also use this constraint for single column primary key. In that case, you just put a primary key, parenthesis, key, and parenthesis, close parenthesis. But if you are doing a multi-column primary key, you must use this syntax, putting primary key as the last, right after the column definition. And remember, there's no comma after this. Common mistakes. For multi-column primary key, a lot of students put two primary key column constraints. Like here, ID1 primary key, ID2 primary key. This is wrong. Another common mistake I already talked about, adding a primary key, adding a comma after the last table content. And another one, yet another one, for single column primary key, put a comma somewhere in between, or put the primary key in front. Basically, a bunch of issues with where you place different components. It will be table name, column name, data type, primary key, if any, then comma. We will use some examples and hands-on sessions to help you understand. But now, let's talk about in general, how do you convert shorthand representation to create statement? If you already have a shorthand representation, remember the table name will be relationship name. So you will use entity or relationship name as table name. Then you will use attribute name as column name, as in each column definition. Each attribute is one column. Of course, you need to add the data type to each column. And finally, you add primary key constraint to either primary key columns or the primary key definition at the end of table content definition. And do remember to add comma to the end of definitions, except for the last one. And once we know what the create statements is, it's easy to understand what the drop statement is, which is simply remove the table from database. You drop the table, you put the keyword drop table first, then followed by the table name. And remember, one drop statement is for one table. I see students writing drop table, table name 1, table name 2, table name 3, separated by comma or by parenthesis. This is wrong. You can have only one table in each drop statement. So let's quickly do some demo. I'm bringing up Oracle Live SQL, and this is the starting screen you will see. And let's go to SQL worksheet. I'm going to use the same instructor example. So this is the create table instructor, where you have the instructor name, you have a primary key, and you have instructor affiliation. So by clicking on the run button right here. Oops. Okay, right here. Let's go. Oops, not the best painting, but here. This is the run button. I click on this run button. Let me clean up my mess first. But now let's click on run button, and you see it's running and the table created. Now, after I use it, let's try to drop table. And I will click on the run button again. and now table dropped. If I try to find this instruct table, or maybe step from, you will run into this very soon. We will introduce this select very soon. But if I run, it basically tells me table does not exist. There's no such table because I already dropped it. So this is so much for table creation and a drop. In our next lecture, we are going to go into further detail on the naming table, naming standard, and we will run more create. Oh, before that, let me show you another convention, which is the multi-column primary key. So right here, we have the same create table, registration, and remember registration is between student and course. So it has a multi-column primary key. We need to enclose it inside the parenthesis, put primary key, and have it here. Now we can start running, and the table is created. Let's try to do some of the mistakes. Let's try to reproduce some of the mistakes we have. For example, what if I add a data type here? It tells me invalid statement. This is wrong. Now, what if I put a comma here at the end of a statement? I run it. It says invalid statement again. Now, when I remove, if I do not have a primary key, you also need to remove this last comma. There's no comma. If you still have this comma, when you run it, another invalid identifier, but basically it's what you what you will find, an error message. And last but not least, let's try to create a multi-primary key definition, which we mentioned just now. Now I have a primary key after student ID and the primary key after course ID. And I run it. It says table can only have one primary key. If you define a column as primary key, you cannot define another. This is the #1 mistake happened in create table statement when there are multiple columns in the primary key. So much for registration. Let me drop it. And we shall go to the next lecture. Table dropped. I'll see you in next lecture. In this lecture, we're going to go through the naming convention of Oracle Live SQL and do a quick demo. Now, when you create a shorthand representation of an entity or relationship, because it's all written on text, it's meant for human beings to read, you can name that whatever you want. You can name using special characters, you can have space, you can have single quote or double quote. But when you translate a shorthand representation into create table SQL statement, there are certain restrictions that you need to follow, certain naming conventions you need to follow. Oracle have the same restrictions on table names and column names. It has to be less than or equal to 30 characters long. It must start with a letter. It can contain letter, number, and underscore, but it cannot contain space or any special characters. When I say special characters, the most important thing to remember is those characters on top of your numbers on your keyboard, like a question mark or $sign or exclamation mark. You cannot have them. But one thing to note is all these tables and columns are not case sensitive. So some valid names include student underscore ID, teacher underscore name, and because it's not sensitive, you can have student all in lowercase or all in uppercase, and you can have a student ID without underscore. You can have N1104 underscore reservation. You can even have a my name underscore 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 underscore, although most people won't name their column this way, but it's completely valid. Some invalid name, you cannot have a student space ID. You cannot have teacher underscore salary underscore dollar sign is not valid. You cannot have a 2020 sales goal because it starts with 2. And this apparent issue is this column name is too long in Oracle DBMS. So these are the invalid names. Try to avoid. Try to name your column name and the table names as accurate and as standardized. Let's do a quick demo in Live SQL. And note that in this demo, we are going to create tables that we use for the Data Force Academy. And we will use the example. These are tables for our future SQL demo. And we add some information like course name, student name, and actual tuition to the registration table for instructional purpose. So when you see later on, when you see the registration table, you will notice it's not really third normal form compliant, and not because we intentionally use a bad design, just because it's easier for us to demo. Okay, now let's go to Live SQL. Let me bring up Google Chrome and type in Oracle Live SQL. Get inside. And I will press the SQL worksheet link to the left. And this is my sign in. So we have this SQL worksheet, and I'm going to copy and paste the scripts that I have written. 4 create statements and 4 drop statements. All these scripts are in course material and in the GitHub repository. So you don't need to type them in. Now let's go through this quickly. We have this single column primary key, and it is also a single column primary key, but for demo purpose, I put this into a primary key constraint. And similarly, primary key single column constraint for primary key, and primary key multi-column primary key definition. And then no comma after this, no comma after this. And I put create table, all this basically all these SQL keywords in capital just to make it look better. But indeed, you can do create, EA, uppercase, lowercase, all these will work. And similarly, instructor name, you can have all caps, it doesn't matter. So let's create a table first. Now, before I run this, if I, without highlighting any of the statement, and I run I click the run button, as we stated before, run button here, it will run, Oracle Live SQL will run all 4 create table statement and 4 drop table statement. In order to only run part of the SQL, I have to highlight the SQL statement I want to run. For example, if I just want to create the instructor, I need to highlight it and press the run button. 1 table created. Now, also note there's this semicolon. SQL statement will ignore all the space and the line break in between different components. So I can have this create table instructor all in one line. There's nothing stopping me from doing that. And Oracle will be able to tell that it's one good statement. But if I do not have this semicolon, Oracle will not know whether this statement is the same, is in one block statement chunk as in the next one. That's when you need to use a semicolon to separate statement from statement. It's not a part of SQL, but it's a best practice. When you have multiple statements, remember to put a semicolon after your statement to mark the end of your statement so that your next statement will not get confused. So let me I need to drop this instructor first so that it's not going to give me an error message. Now, I'm not highlighting any portion. So when I click on run, it's going to run 4 create statements, then 4 drop table statements, all in a batch. And here it is, 4 create, 4 drop. If I highlight all these 4 and create the tables, now the tables are created. If I then go to the schema, let me change the color of my marker so it's more bright. Schema part, all right? Then I will see the tables I just created. Course, instructor, registration, student. Let's use instructor as an example. You can see here, this is how Oracle stores the table and the column definition. You have the instructor, you have the instructor name and affiliation. All of them are stored in uppercase. No matter what case I type in later on in my SQL statement, Oracle will convert them to uppercase and find a match. That's why we say it's not case sensitive, right? Now, one thing to note is that Oracle Live SQL is a free service provided by Oracle, and it comes a restriction that it's session by session. If I log out right now, all these 4 tables will get lost. Also, if you stay here idle for too long, Oracle may close the session and remove all your tables. So make sure when you type in something, save it to your own text file or whatever you are comfortable with. Don't keep it here. It won't keep whatever you typed in. It won't keep whatever you created either. So let me try to log out and show you what's happening. Hopefully you are not going to lose whatever you have done in the future. Now I'm logging in again. Now let's go to schema. And there's nothing. Because in between different sessions, Oracle cleaned up everything I have created. All right, so much is for Oracle, Live SQL execution, this demo, and all the create statement and drop statement. Let's talk about in the next session, we are going to talk about simple insert and select. I'll see you there. In this session, we are going to talk about the naming convention of PostgreSQL and make a demo on PostgreSQL. Now, PostgreSQL and Oracle are very similar. So if you have go through the Oracle portion of this naming convention demo, you will see almost the same thing. PostgreSQL has the same restriction on table names and column names. What's different from Oracle is instead of 30 characters, it has the limitation of 31 characters. The names cannot be more than 31 characters. It can start with a letter or an underscore. It can contain letter, number, and underscore, but it cannot contain space or any special character like question mark or $sign or exclamation mark. One difference is that the PostgreSQL can have what we call the quoted name. If you put the name in double quote, then basically you can have whatever you want in the name. Dash, $sign, or space, and you can also start the name by number or characters. And this becomes case sensitive if you use quoted name. If you don't use quoted name and use the regular one without quote, then it will be case insensitive. So some valid name similar to Oracle, we have a student underscore ID, student underscore name, student ID, and the only difference is the underscore good name underscore in PostgreSQL. I'm not putting quoted the name here because basically you can put everything. So every name will be a valid name. There's no point of listing that out. I'm just putting unquoted name, traditional unquoted name. Invalid name for unquoted name, student ID with a space, teacher salary dollar with a $sign, 2020 sales goal, which starts with 2, a number instead of a letter. And again, this column name is too long in PostgreSQL DBMS. Let's do some quick demo in PostgreSQL. The difference this time is that we are going to use what do we call the pgadmin4. This is pgadmin4. This is the management tool. Basically, it's a tool, DBMS management tool provided by PostgreSQL. If you have go through the installations, the PostgreSQL installation part, you should already know how to start it and how to get to this page. Now, to run SQL against a database, you see this? Right now I'm putting my mouse on test data and I'm right-clicking. It gives me a right-click drop-down menu where I'm going to choose Query Tool. This is a tool I will be using to run SQL against PostgreSQL. I'm copying my statement, SQL statement here. Remember, I'm using the same statement that I use for Oracle, and that's the beauty of having an ANSI standard, that the same SQL can be applied in both DBMS and even more. And similarly, similar to Oracle Live SQL, if I just run SQL right now without any highlighting anything or selecting anything, it will run all 4 create statements and 4 drop statements all in one batch. So I'm going to click on this button. If you can see, maybe this time it's too bright, so I'll change that to a blue sign. Right here, that's the run. And I'm going to clear my drawing so that I will press the button. And you can see pgadmin only returns the result of the last statement you run. Although we run 8 statements in one batch, it only returns the information for the last statement. So what you need to do is you can highlight all 4 create statements. Press 1. Now all statements are created. All 4 tables are created. Let's open up test data, go to schemas, public, and check here. Right now it shows tables is empty. That's because I haven't refreshed that. Now if I right click on tables and click on refresh, you will see the 4 tables get created. An interesting difference between PostgreSQL and Oracle is that although both are case insensitive, the way they store the data, they store the names are different. Oracle store the names all in capital K, uppercase. Postgres store all these in lowercase. This does not matter if we are running SQL from pgadmin or Oracle Live SQL. But if you run the SQL through in Python, from Python or R, through a JDBC driver, it will matter. I have students running SQL again and again, keep on complaining cannot find a table, because in her SQL statement, she actually put a uppercase letter in the table name. Although it's the same table name, the uppercase make it impossible for PostgreSQL to find the table. So remember, you can do whatever case you want in pgadmin's interface, but if you are running SQL against the PostgreSQL through tables through JDBC connection, you need to use all lowercase. That being said, I still can do all the things with the key SQL statement. I can do lowercase drop. I can do a mixed case. I can do all uppercase because I'm using the query tool, which knows how to translate these table names. So now that if I highlight all these 4 and start running, drop table, all of them finished successfully. Now let's go back to table, right click on table and refresh again. And all of them are gone. So much is for PostgreSQL demo. We will talk about more SQL statements in the following session. I will see you there. In this lecture, we are going to talk about simple select and insert statements. Now, we already know how to create table and of course drop table, but just by creating table is still empty. You need to open up table, insert the data into table. And then once you insert the data, you need to select it out for future usage. When you create a table, when you create the data, put that into table and store it in the database. That's the whole thing that DBMS is doing for SQL. So how do you insert data into a table? The simplest form of insert is insert data with a column list. Each insert is a row. It starts with a keyword, insert into. Then followed by the table name. By running this insert, you are going to insert the row inside. So you need to specify for this row, what's the value in each column. You do this by adding a column list enclosed in parentheses after table name. So it's an integrated part of table name and column list, similar to the shorthand representation. Then you specify a values keyword and put a parenthesis, and the values should be inside this parenthesis. Column list in insert statement, they don't need to be in the same order as table definition, but column list and the value list must match with each other. If you still remember how we define instructor, in the create table statement, we actually have instructor name first, and the second one was instructor affiliation. But if you are actually inserting using a column list, then as long as this Jedi matches the affiliation and Obi-Wan Kenobi matches the instructor name, then you are good to go. You can insert. You can insert without column list. If you just put the insert into table name and the value list, it's doable. However, in that case, the value list must match the column names and order defined in the table create statement. For example, here you will be inserting into instructors name first, affiliation next. And if I have more columns in this instructor table, I must submit all the required value too. So once you insert it, you can select them out. The keyword here is select. You want to select which column you want to see from the table. If you want to select multiple columns, you separate them by comma. And again, no comma after last column. So last column here, there's no comma. It just keep on doing commas, column, comma, column, until you finish all the columns you define. Now, column names can be long. So if you are selecting columns, you don't need to, it's similar to insert. You don't need to be in the same order as how it was created. You can specify the column names and the value will show up in the order as selected. And if you don't want to type in all the column names, if you're happening to be selecting all columns, you can use asterisk, a star sign, means all columns and the default order as defined in the table create statement. So you can use a select star from instructor. It will show you instructor name and instructor affiliation. You can also mix star and column names together. For example, here, you can have a select instructor name and star from instructor, but remember to bring in comma between them and no comma after the last column, which is the star. You may wonder, why would you do that? Why would you choose instructor name twice? For a single table selection, this actually doesn't provide much value. But in the future, we are going to go through how to run SQL against a multiple column. At that time, you may want to selecting some columns from one table and selecting everything from another. That will be proved to be valuable. So let's do some quick demo in Oracle Live SQL. First, we talked about insert, right? Let me quickly type in some insert statement. And as you can see, we have affiliation first, instructor name second, but each one matches each one. So let's run. And now let's select from, oops. I think I accidentally pressed, I accidentally pressed the return button on my keyboard. That's why there's this error message, but it's not going to affect what I'm trying to show here. So I'm showing you what's inside the instructor now. I already inserted something before. I have Obi-Wan Kenobi as Jedi, Anakin Skywalker as Jedi, Yoda as Jedi, and this is the one that I just inserted, Qui-Gon as a Jedi. And remember, we used affiliation first, but when we select, we're still going to get Qui-Gon first, the name first, right? But now, if I ever try to use this to do a select, use this column list, guess what it will happen? It will show me the affiliations first, followed by the names. And we can also use insert without the column list. In this case, it will by default goes to instructor name first, which is the defined in the create statement, then by affiliation. Let me run the insert. Looks like I have been keep on pressing the enter button again and again. So let me select star from instructor and see whether the previous insert was successful or not. Press on run, and Anakin Skywalker is there. Or maybe I think I make a mistake because I shouldn't have. I already had Anakin Skywalker and it's not allowing me to insert multiple times. Remember in the very beginning of the relational model, we said we cannot have two rows with the same value, especially for the primary key. Primary key must be unique. And this is what's happening. It's stopping me from inserting Anakin Skywalker again. So how about I try Luke Skywalker? I will run it by default. One row inserted. And now if I select star from instructor, you will see both father and son in the table. Okay, so much is for simple insert and select. Starting from there, we can dig into some further details of SQL statement. Namely, the next one we will be talking about is data type. I'll see you there. In this lecture, we're going to go through different data types. So we talked about data types of a column. It defines what value a column can hold. For example, if you are trying to put a string value into a decimal, it will definitely give you an error, right? This is pretty intuitive. But now, how are these data types defined and how are they matching with each other? That's what we're going to talk in this lecture. Most common data types, including these: int, decimal, text string characters, or date. Now, first let's talk about int. Int is an integer number, it's a whole number part. You can see them as a quantity of items sold, number of days, number of students. You won't have like half of the students, right? And regularly, it will also be used as a primary key because int has a lower storage cost and highest performance of all data types. It's pretty it's pretty straightforward to use an int, but there's something to remember. One is that you should place that. You should not place it inside the quote. And you should not use comma. For example, 12,345. If you are regular writing that in regular English expression, you will put the comma between 2 and 3. But in SQL, you shouldn't do that. It will just be a single string, 1, 2, 3, 4, 5. There shouldn't be any comma. And you shouldn't have decimal points, which is self-explanatory. Now, a little bit complicated is decimal. Decimal has two parts, the whole number part and the decimal part. When you define that, you define a precision and scale. A common mistake made by students is they confuse precision with the digits of decimal of a whole number. In fact, precision is the total number of digits in the whole number, including both whole number and decimal place. But scale is the number of decimal digits. So if I have a decimal 7, 2, that means the whole length of the digits is a 7 with a decimal space of 2, which leaves 5 digits for my whole number part. What if the scale equals to 0? Yes, you can define scale as equal to 0. Then it will be the same as integer. It's commonly used for things like a currency. In that case, scale will be 2. And for percentage. Common mistakes for decimal. Don't add quote. Quote is reserved for characters. Don't add comma. 1, 2, 3, 4, 5. No comma in between. A little bit tricky here. It will overflow if you try to insert a number whose whole number digits are greater to the precision minus scale. And we talked about this in the previous slide. Precision minus scale. The result is the number of whole digits you can have in this decimal column. If you are inserting some number whose whole number digit is more than what is defined as a precision minus scale, you will have an error. Like decimal 7.2. 7 minus 2 is 5. So you can have 5 whole number per digits. If you try to insert 1, 2, 3, 4, 5, 6.78 into this decimal 7.2, you will have an overflow error message. On the other on the other end of the balance is a loss of accuracy when number of decimal space digits is greater to scale. For example, if you have 1, 2, 3, 4, 5, 6.38, which have 2 decimal digits, you try to insert that into decimal 70, which have 0 decimal digits. Oracle or other DBMS will try the best it can do. In Oracle's case, they will round it up. In some other DBMS, they will just wipe out the decimal digits. It depends on the DBMS, but basically, either way, you are losing your accuracy. The problem is, this will not result in the SQL execution failure. So you won't be able to tell by looking at the SQL execution log. You have to pay attention to it yourself, monitoring the data, and that's the only way to resolve it. So let's talk about text. Text strings, sometimes called strings, sometimes called characters, are defined as char or varchar in SQL. They are single quote delimited string. For example, city. You enclose them with a single quote, then it becomes a char. Now, single quote is used to delimit or enclose the string. It's not a part of a string itself. And once you put single quote around it, it's case sensitive. Lowercase city is different from uppercase city. And if you want to put a single quote inside the string, you use 2 continuous single quotes to represent 1 single quote. Tags are widely used for all sorts of text, name, address, anything you can think of. It can be used for primary key too. For example, in our instructor table, we actually use instructor name as the primary key. However, when you use this, make sure you understand that it comes at a price for performance, because selecting the text is slower than selecting int, and the other operations too. So you can use them as a primary key, but be aware of the performance hit. One thing interesting is how about social security number? Or in some state, if the car license plate is all numbers, should they be char or should they be int? Either way is workable. But if you use social security number as the integer, someone's social security number may be starting with 0. Then when you compare, there might be missing equation because there's a 0. So this is something to pay attention to. In general, the general guideline is that if a column cannot be summed up, it should be text. In social security numbers case, who will add up the social security number of students in a class? For what? There's no reason to do that. It should be text. So there are 2 types of text definition. One is char, one is varchar. And the difference, of course, is the VAR. VAR stands for variable, as in variable length. So varchar can have a variable length, but that does not mean it can go from 0 to infinity. So when you define char and varchar, you supply the definition with an n, with number in the parentheses. For example, char parenthesis 10 or varchar parenthesis 10. The difference here is database will fill in spaces for the rest of the char characters. So if I put a Jedi into char 10, what actually exists in the column is JEDI, J-E-D-I, plus 6 spaces. But in varchar's case, it will simply be JEDI. There's no space added. Many students thought varchar means you can have as many characters as you want. You can put a JEDI is good, this is bad into this varchar 10 field. This is wrong. You can only put up to 10 characters in this column. But if your data, if your text is less than 10 characters, Oracle will not add space after that to make it 10. Whereas in char 10's case, Oracle will add up spaces to make everything you fill in 10 characters. But what's the usage of difference? Because of this variable length character, it's varchars are useful for columns that may have variable table data, for example, name or address. And for char, we can use a fixed length. They can be used for fixed length characters, like car license plate, driver ID, or in some cases, some ID. And common mistakes: forget single quote. You have to have single quote around text. Or use double quote. That's wrong. You have to use single quote. Double quote is just a normal character. Or use wrong character of quotes when copying from rich format text editors, such as Word or Outlook. This happens to me a lot because a lot of students, when they submit their homework, they run the SQL in some SQL editor, which is a plain text. They copy that into Outlook and send this. When they copy the single quote into Outlook, Outlook automatically convert it into some kind of unidentifiable character. And when I try to run their SQL, I get the error message. So this happens a lot, and pay attention to it. Outlook or Word can sometimes switch in the character space or single quote or double quote. Make sure you are submitting the right format, the right character set. So now let's do some quick demo. In Oracle Live SQL, let's first by doing an insert. Again, all the codes are in course material and in GitHub repository. So we do this insert into course values. Now this is the course ID, which is the int. Let's see what will happen. And also, this is tuition. Tuition is a decimal, 72. We are inserting an integer here. Let's run this and see what will happen. It's ran. Then let's select from. I'm highlighting that, so I'm only running this once. This statement, I'm not running the insert into. And here is this experience the dark side provided by General Multi, actually. It should have been General Multi, I'm sorry. You can see this is 12. I put 12.34, put 12.34 here, and the Oracle will round it up. If I have another one like 13.564, and run it again, this time because it's 13.64, it's actually rounded up to 14. Experience the tar side. Now, one thing to note, very interestingly, is it's not sorted. As you can see, there's no sorting in the select result. This is the important topic that we will cover later on. For now, just keep in mind that the result is not sorted. And I have this experience, found the interesting experience where some coworkers send me a list of dates and ask me why we are missing some date, some data in the date. And I look at it and immediately I know what's going on because he forgot to sort the value. He only see the top field and happens to be broken up and missing some dates. So he thought, oh, we are missing some date, but which is not true. By sorting the result, we were able to identify that all dates are there. And how to do it, we will be talking about this in the later session. So much is for the interaction between int and the decimal. And you can see that int can be converted, when decimal is loaded to int column, Oracle does a roundup. Some other database may be doing just a simple truncate. And for decimal, for loading integer value into decimal, they will just load as is. Now let's talk about decimal precision. We're inserting into course values 101, how to blow Death Star into pieces by Luke Skywalker, my favorite topic. Now, remember this tuition is 7.2, so it can only contain 5 whole number digits. What will happen if I run this? It gives me an error message, value larger than specified precision. So Oracle will not allow you to do that. Now, what if I do 1.12345, which will meet the requirement, but I have a 678, which goes beyond the two decimal digits specified in the definition. Oops, did I just clear it? Okay. Let me try to run this. Oh, I think I accidentally pressed the Control-Z button, which may remove all my change. But now I changed that to 12345.678, which goes beyond the scale, but not a precision. Now the data is loaded, and let's select from course. And let's see our favorite topic, how to blow Death Star into pieces. It says 1, 2, 3, 4, 5, 6, 8. So you can see that Oracle rounded 7, 8 up to 8. And you are losing some precisions here. And there's no error message when we run this insert. So you have to pay attention to this in your real system and think of whether it's possible for you to lose the precision when you design your database. All right, now let's start talking about decimal. We will have some other courses, some additional courses where in the tuition area, I put a 50,000 as what I'm going to write in an English sentence with a comma. So now if I run this, what will happen? It says too many values. And the reason it gives me too many values error is because it's comma. Oracle thought that our data is first value, second value, third value, fourth value, and this is the fifth value. Apparently this is wrong, but that's how it interprets comma. So what you need to do is remove comma and you run this. I'm not going to run this because it will be a simple select, but there's another topic that what if I put a single quote around here? Will Oracle be able to identify this as the decimal? The answer is yes. And you can see the introduction to the Force, Obi-Wan Kenobi, 5,000. It was Oracle was able to identify. So what's happening is Oracle and some other DBMS, they are trying their best to guess what you try to do. It sees that you are trying to insert a value into, you're trying to insert a value into a decimal column. So it tries to convert this value into decimal. This is something that it's smart enough to do, but you should not rely on it. Because if you can do it once, it can make mistakes too. So if I put R2D2 here, we will talk about what kind of mistake can happen later when we talk about where clause. That's where this issue is more apparent. But for now, let's remember this is wrong and you shouldn't do it. You should always put the decimal as is without single quote. Now, if I accidentally, knowing its tuition, I still type in R2D2, what will happen? I will run it and I get an error message, invalid number. It is not a proper number. Oracle note that it's not saying invalid data type because Oracle is trying to convert this into a number and it cannot convert. That's why the error message says invalid number, okay? And with all this for decimal, let's start text with a lighter note. What if I use a double quote instead of a single quote? And we all know it, we will run into error message, but what is the error message? It's a colon not allowed here. Why colon is not allowed here? It's basically thinking this is a quoted name. It thought this was a column. But this is beyond the discussion of this, the discussion of this class. So all you need to take away is that you should use single quote, not double quote. So much is for general text handling. Let's also go through some quick char and varchar comparison. If we go to schema and look at the table instructor, schema, instructor, there are two columns defined in instructor. One is instructor name, which is a varchar. Another is affiliation, which is a char, varchar 20. Now, remember this. This can be interesting. Maybe what I can do, I will copy this, paste that into SQL worksheet so that we can make a comparison. Looks like Oracle Live SQL is a little bit slow now. And in order to hide some information to avoid execution, you can put a 2- in front of a row, and Oracle will treat this as a comment. So we have an instructor name and an instructor affiliation. Now that I will insert the value into instructor. We all know it can have it's a varchar 20, right? And how about a Jedi with a really no name? There will be a error message saying value too large. So varchar does not mean you can extend the char as wide as possible. If it's defined as 20, it can hold up to 20. You cannot go all the way to a Jedi with a really low name. Now, what about char? It's similar. Anakin Skywalker says, I don't care which side I'm in. And also notice there are two single quotes here, which stands for one quote. So if I run that, same error message. But if I just put I don't care or I don't, what will happen? Or maybe it's not Anakin Skywalker, but Han Solo doesn't really care, right? You run this, select star from instructor, run it. Oh, typo. Fix the typo, run that. And for solo, you see I don't and it's single quote. So we successfully escape the single quote by putting two single quotes together. So another interesting thing is we talked about how many charts. For charts, we will have space in behind. So this is Jedi. And this, according to what we said, there should be 10 space after this. So let's see, I'm moving my mouse on top. 1, 2, 3, 4, 5, 6, and no more. I'm trying to, I can no more. If for Hansel is I 1, 2, 3, 4, 5, 6, 7. So there should be 3 left. 1 space, 2 space, 3 space. That's all. But if you look at the instructor name, which is the variable, which is the varchar, you select Han Solo, nothing after. You select Luke Skywalker, nothing after. I try to very hard to make my mouse over and over and drag and show. There's simply no space after a varchar string. So much is for text and decimal and all the data type. In next session, we're going to talk about a very interesting topic, which is now, and I will see you there. In this lecture, we are going to talk about now. What is now? So when you define data, you constantly run into special values that simply does not exist, or you just don't know. For example, mid name. Not every people have a mid name. For those who does not have a mid name, the mid name field is empty. It's not like an empty string. It's just simply nothing exists there. Or home phone. Sometimes people don't have home phone, or either because they just don't have one, or because they want to, they don't want to expose their home phone to the outside world. So when you collect home phone from someone, maybe you will just get the empty. It's an unknown or non-existing value that you need to specify inside your database. But how do you make sure you understand this is empty? It's represented using the keyword NULL, now, and it's case insensitive. It can be lowercase NULL, it's still meaning the same thing. But in our class, we will always put it into uppercase so that it's easier to identify. Remember, now is not 0. It's not empty string. It's not the string now by adding 2 single quotes. And all these are common mistakes made by beginners. So let's talk about what is not now, what cannot be now. Can a primary key be now, like student ID? Apparently you cannot. Why? Because primary key, by definition, should be able to clearly identify the whole entity, right? So if you have a now, what does that mean? You do not know the key, you do not have a key, you are missing the key. What can you get from a missing key? You cannot determine anything of the entity. So primary key cannot be null. How about something that is not primary key, but based on common sense should not be null? Like emergency contact number. You should always have an emergency contact number for any student. Having a null in that field is a violation of school policy. In this case, when you define an emergency contact number for a student, you'd better define that as a not null field, where people just cannot put not null there. In order to create the student record, you have to put a value to enforce this school policy. So what you can do is adding a not null adding these two words, not now, in the column definition. When you create a table, it has to be between data type and a comma. You can have one not now for each column, and you can have multiple columns with a not now constraint in one table. If you do not put the not now after a column definition, the default is nowable. You can have a now in that field. It's like a mid name. Yes, you can have now, but the first name, it should be not now. And primary key is automatically not now. That's the only exception to this default. How do we insert now into the column? When you do insert, you can either insert it by missing out column names. For example, if I do not specify instructor affiliation, then in this insert statement, I'm telling DBMS to put now into instructor affiliation. Or I can just put the keyword NULL as the field value. It will provide the now in that field too. But remember, you cannot insert into not now. You cannot insert a now into a not now columns. We will explain this by running a series of SQL. So let's switch to Oracle Live SQL. And I'm going to have a bunch of inserts. So first of all, this is the inserting value open large without affiliation. I can also insert into instructor name, maybe total, also without affiliation. So both can work. Oh, I already inserted the instructor just now. I believe I insert something like this. So let's just about Jaja Brinks. So now another row inserted. Let's do a select star. And let's look at the two rows for Alvin Lars and the Jaja Brinks. You get a now here, you get a now here. Both can be inserted. Now, what if I put an instructor affiliation? Values, neither Jedi nor I think it's only 10, so let's just put neither. Will it give me an error message? And the answer is yes. And what is the reason? It says clearly, cannot insert now into instructor name, because instructor name is a primary key and you cannot insert a now. Of course, we didn't specifically insert now into instructor name, but we are inserting a row. And in this row, we only specify instructor affiliation. So the other columns, the missing columns, like instructor name, will default, we are telling DBMS to insert the now. That's where we get this cannot insert now into error message. All right, so much for now. Now is an interesting topic. By inserting and selecting is not as fun for now, but it will get more tricky and more interesting when we start to talk about conditions, where now equals to or not equals to. That's where all the fun part of now comes in. And I will meet you in next lecture, which we will talk about select in further. I'll see you there. In this lecture, we are going to go through some very useful features of a single table select statement. So first, let's give a quick review on what we have learned about select statement. Select statement is used to retrieve certain columns from a table. And if you want to retrieve all columns, in the default order that was specified in the create statement, you use the asterisk or the star sign to indicate you want all. What we didn't cover is that in addition to retrieve columns, you can also retrieve column computations. For example, from a sales table, if you pull quantity times price, that gives you sales. But of course, the question is then, what is the quantity times price mean? You may know that, but whoever reads your SQL may not understand. That's when we have a column alias. You can rename a column or specify a name of the expression using the AS, the S keyword. That will be select some computation as an alias. And when DBMS runs this SQL, it will provide you with total sales, the table alias title, the column alias title to the computation. Let's show this in Oracle Live SQL. And I'm going to copy and paste my SQL statement from the code block. So first one, I'm showing you how to do a calculation, which is simple. Tuition times 1.1, assuming this is a proposed 10% increase in tuition. And that's the one that I run. But as a user, you look at the definition and you said, what does the tuition times 1.1 mean? And by specifying alias, we will know this is a current tuition, and the tuition times 1.1 is a proposed new tuition. Let's run this. So this is a proposed tuition, and this is a current tuition. We will see the difference. And of course, if you want to do minus or plus or whatever division, you can do this too. So much for select alias. Another very useful feature, or in my opinion, is the most important feature, is a where clause. You can use where clause to provide you a criteria to filtering out a certain, to filtering the certain rows that meets your criteria. For example, if I'm only interested in the instructors that is affiliated with Jedi, I would like to say, I want to see all the instructors with the instructor affiliation column equals to Jedi. And that's when you use the where clause. You add a where keyword after the table name, followed by a condition. In this case, it will be instructor affiliation equals to Jedi. To explain a little bit more on how where is executed, let's talk about select, how select is executed. In fact, when you run the select, DBMS does a very tedious and very boring thing. It will go through each row to pick whatever you ask it to pick. For the select operation, each row is performed once. Let's talk about something that may be counterintuitive. What is the result of the following query? Select, this is a test from instructor. Now we already know we have 4 rows in the instructor table. Is this select going to return us 4 this is a test, or only 1? I'll give you 5 seconds to think about it. Then let's go to Oracle Live SQL. One, two, three, four, 5, and 5 seconds is up. Now, let me copy the SQL over, and let's run it. It gives us 4, this is a test. And this example shows us how select is executed in the backend. Database, DBMS, goes into this table, perform a select, this is a SQL, for each row, once, twice, 3 times, 4 times, and provide the result 4 times in the row, in the table. You know what I mean when I say in the row. Okay, so this is how select is performed. DBMS will go through each row and apply SQL action, such as select to the rows. Now, talking about where, it's exactly the same. DBMS will go through the table row by row and check the condition for that particular for the current row. If the row meets the condition, it will perform select. If the row does not meet the condition, it will discard the row. It will not take any action. For example, let's say I have two rows, Obi-Wan Kenobi and Darth Sidious. DBMS will go into the first row, Obi-Wan Kenobi, affiliation is Jedi. Okay, meet the criteria, select it. The second row, Darth Sidious, affiliation is this, doesn't meet the criteria, doing nothing. Let's explain this again using Oracle Live SQL. So I'm going to select instructor affiliation. From instructor. And we already know it will give us 4 rows, right? What if I add where instructor affiliation equals to Jedi? And what will happen before running that? Let's explain. It will go through first row. The affiliation is Jedi. So yes, we will select it. Second row, affiliation is Jedi. We will select it. Third row, affiliation is Jedi. Yes, we will select it. 3 rows so far. Fourth row, affiliation is this. We are not going to do anything. We are not going to select it. This row will not show. So by running this SQL, you should see 3 rows. And that's exactly what we get. Now, the question will become, showing 3 Jedi may not be fun. What if I just want to see 1 Jedi? If there are multiple values, I only see it once. Once is enough for me, right? And that's what the select distinct is used for. It will make sure each row, each value only show up once. For example, I can select distinct instructor affiliation. I will add a distinct keyword right after select. Remember, select distinct itself is a keyword. There's no question mark, no single quote, no parenthesis, no nothing in between. You just type the whole word select distinct. Of course, there should be a space between them, but yeah, this is select distinct. So we'll run this and expecting that only returning 1 Jedi. Yes, so this is how it works. Each row column value can repeat. If you choose multiple columns for the select distinct operation, the column value can repeat, but the combined value of a row will only show up once. Let's give you an example again. So still for instructor table, I'm going to select distinct instructor name and affiliation both. We already know that instructor name is distinct. This row is distinct in the row value. This row is distinct in the row value. The keyword Jedi, the word Jedi shows up multiple times, right? But because the row value, each row is unique, it still shows up multiple times. It's not going to show up only once. So this is what the select distinct means. It's selecting the distinct value of the whole column list from this table. So this is the, this is an interesting topic about select distinct. Remember, this select distinct itself is a keyword, so no parentheses or quotes. I do see students add quotes around distinct, and guess what? Oracle think this is just another value, another char string. And the distinct operation was not operated. So we talked about so much about select, and in previous classes, we already showed that the result of select is not sorted. If you have been seeing sorted results, that's a coincidence. You are just getting lucky. If you want the data to be sorted, you need to specifically using order by clause to tell DBMS, I want the result sorted in the order I want. You will add this order by clause to the end of the SQL statement by typing in the keyword order by, followed by columns to sort the data set. I believe you have noticed that we are saying columns, that's a plural. So which means you can sort it by multiple columns. You can specify the sorting order. Either it's a descending or ascending. Ascending is the default. By typing ASC, you are specifying this to be descending. Typing ASC after the column name. And by typing DESC after the column name, you're specifying that should be sorted descending. If you have multiple columns involved, each column can have its own ascending or descending. And in this case, column name and sorting order is the one component. Another column name and the sorting order is another component, separated by comma. Again, no comma at the end. So some quick points we talked about. It's always at the end of the select statement. It can use any columns in the data set, not necessarily in the select clause. Like in this example, I can only select instructor name. I don't need to select course name. I can still sort it by both columns. I can even just select tuition and still order by instructor name and course name. Whatever shows up in the select statement has no relationship with order by columns. The only thing is applied to by order by is the rows. It's not the select columns. Okay, and you can have multiple columns. Each can have its own sorting order. And an important part is the order of the columns determines the sorting priority. Whatever comes first has the highest priority. We'll show you all these with a series of SQLs in Oracle Live SQL. So there are a whole bunch of order by statements, select statements with order by. The first one is, of course, we want to sort course table by instructor name. Now, I'm sorting by instructor, and by default, I'm sorting ascendingly. So that's what you see. D followed by O, and OB followed by OW, and O followed by Y. This is sorted by instructor name. However, when I look at the course name, inside OB1 Kenobi's two classes, L comes before I. This is descending. Whereas in Yoda's two classes, B comes before D. This is ascending. That means course names are not sorted. If I decide to sort first by instructor name and second by course name, you can see that Yoda, because this time we specify instructor name descending, Yoda comes first. Inside Yoda's two courses, B comes before D. Then inside Obi-Wan Kenobi's two courses, I comes before L, which is the ascending order we specified. Now, you may notice that for this particular moisture farming, M is actually higher in order, or it should, or in the plain English, it should be coming after I. Still, we see this I introduction after moisture M. That's because Obi-Wan Kenobi in the sorting order is after instructor Owen Lars. So the sorting is first by instructor. Only when you have the same instructor, then it goes to the second level of sorting, which is course name. Beyond, between different instructors, the course name are not sorted. So much is for select distinct. And the last point we want to make is to show you that you can also sort by calculation. Like for example, if I want to order by tuition times 1.1, I can do that. You can see that yes, it's sorted ascending. Now, of course, you can start wondering, why would you do a order by tuition times 1.1? Because it will be the same as order by tuition, which is true. This tuition time 1.1 is more for a demonstration purpose. But if you have a larger table which has more columns, like the price and the quantity we talked about in the total sales table, you may want to sort by quantity times price. That's for the total sales. So in this case, this order by computation feature will be useful. Okay, so much is for select. We talked about these things. We talked about where clause, and we talked about order by. And as we go through this column computation, there's another interesting topic that how do you do further processing on column values? And beside the regular arithmetic calculations, we also have some advanced features, which is achieved by using functions. And that's the topic we are going to cover in the next lecture. I'll see you there. In this lecture, we are going to talk about row-level functions. And row-level functions actually is what the name suggests. It's going to get applied to every row being processed. This includes a lot of calculation, computation, and conversion functions. For example, for datetime, there's frequently a need to convert between different data format. For example, the US format, the international format, and the United Kingdom format. Also, there's string functions. You want to convert everything to uppercase, everything to lowercase. You want to measure the length of the string. You want to concatenate different strings. All this can be achieved by using row-level functions. So let's go to Oracle Live SQL. Let's first talk about the date function. First thing to note is that there's a lot of different functions serving different purpose, and nobody can remember all of them. What you can do is doing what our technical guys love to do, Google. So for example, let's search Oracle date functions. And you will see a lot of date and time functions. Add date, add time, convert, current date, current timestamp. You can pretty much assume what this means. Day name, day or month. I guess these are pretty self-explanatory. If you have any questions, if you want to find, to look up certain function that meet your need, just Google it, check the vendor's support documentation. Now, let's go back to our simple functions. We will use these simple functions just to demo how to use those functions, so that when you need, you know how to use it, you know where to find them, and that should be good enough. So let's first select star from registration. In this table, we have a date field. And you can see the registration date is displayed as 10 October 19, which means October 10th, 2019. That's a default date format for Oracle Live SQL. But this may not be the default time format for a lot of other systems. Other systems may be showing something like 10. Let's say, I will try to use something that will not be ambiguous. Let's say January 23rd, so that the Oracle will not mistake 23rd as the month, 2019. Okay, if I try to do select from registration, where registration date equals to 0/23/2019, what will happen? Because Oracle does not accept, because Oracle by default use this 23 Gen 19 format. It does not understand that this 01/23/2019 is actually a date format. You have to use this 23-Gen-19 for it to recognize. And this time it will work. But of course, there's no data found because there's no such data. Now, what if my computer system, my upstream system, returns the data like this? And this is a pretty common US format, right? You need to use a function. One of the most useful function in date format conversion is toDate. Now this toDate is an Oracle standard. Other DBMS, like PostgreSQL or SQL Server or MySQL, may be using some other tools, other functions. You need to check your vendor's function list to get an idea on how to use them. But how to format is database specific. The idea of using this function is universal across different platforms. You will still have the same function name. You will specify the column. You will specify the format, the date format. So these are the universal. So here I'm going to show DD, this month, day, y. So in this case, I'm telling Oracle, convert this string to date and use this format. How do I know this? I already checked that from Oracle manual. That's how I know how to use this function, and you should do this too. Now let's run this. And this time it gives us, oh, no data found. What if I use a 10, October 10th? It should return me 2 rows, which is correct. All right, so these are the toDate functions, and there are more. As you can see, there's something called sysdate, which will return you the current date. If I just try to do a sysdate here. Oh, I think I shouldn't use a parenthesis. See, it's showing me the current date. And by making this mistake, you can also see that even the most experienced database warrior, database guru can make mistakes when going into these functions. The only way to avoid it is not to avoid it, is to try and error and to Google the function manual. All right, so this is so much for date. Now let's talk about char functions. We were asking how to do select, uppercase, and lowercase. And this is the function Oracle use to convert. And I think most of the SQL, the DB platform use either upper or ucase. Something like that. But again, make sure you check your vendor's manual to know which function to use. So I'm selecting this upper and lower. I separate them into 2 different SQL, but in fact, I can also put them into the same SQL statement. Now, if I run this, we only have one student so far, so it's Luke and Luke himself. And also, you can do a distinct if you want. In this case, because there's only 1 row, so it doesn't matter. It will just be select distinct. Remember, select distinct is 1 keyword. Put this into chunk, followed by the column list. So much is for our demo for function. It's a short one, but does not mean it's not important. In fact, it's one of the most important features that you will use day in and day out. Because when you use SQL, of course, the regular arithmetics, the plus, minus, the divide, the multiplication will not satisfy all your needs. You will need to use a lot of function. But on the other hand, the function usage is relatively simple. You just go to the menu, understand how it works, then you can use it as free. Before we close this session, let's talk about another character manipulation, which is not a function, but more like operator. This is the concatenation. How do you put two strings together? I know there are students trying to use a plus, which theoretically makes sense, but unfortunately Oracle does not accept it. So you need to use this double bar, which is the one on top of your reverse slash key. Double of this, and you can concatenate by using this operator. So you are putting Jedi with Obi-Wan Kenobi, Jedi with Anakin Skywalker, and this with Darth Sidious. And note here, because Jedi is because the affiliation is char 10. So you actually have 10 characters in this string, and the 6 of them are space. How do I get rid of the space? We use a function. Function would be called trim. So you remove the space ahead and after, before and after, and it gives you Jedi, column, Obi-Wan Kenobi, Yoda, Anakin Skywalker. So these are the concatenation and some of the string character operations. And in next lecture, we're going to talk about aggregation function, which is also functions, but not row level, but on an aggregation level. I'll see you there. In this lecture, we are going to go through aggregation functions. We have already gone through row level functions, which process row by row. For each input row, we will generate one result. Aggregation functions operates to a selected data set. It provides statistic information of the selected data. So it's going to be working on a set of rows, a number of rows, instead of one by one, and returns one value. Aggregation functions include sum, average, which is read as AVG, max, min, and the count. So sum, average, maximum, and min, they are just what they are named for. They calculate the total or average or maximum and minimum of the data set. We also have a count function, which includes more information. There are 3 types of count functions. First is the count of a column name. So if I'm counting, for example, instructor name column, we will count the number of rows where a value exists in this column. So it will count all the rows where instructor name has a value, not null. Remember, this is a count of row. It does not count the value, the distinct value of instructor name. Another count function is count star. It will count the number of rows regardless of the value in any column. Even if there's a null, it will count as one row. The third type of count is count distinct column name. This time, the count will count the unique values in the column. For example, count distinct instructor name will count the unique value of the instructor names in the data set. We talked about count star versus count column name. And we talked about count column name will count every value, every row that has a value, and count star will count every row with a value or with a null. In general, null are ignored in aggregations. Any calculation on the null value results in null. And this is not only limited to count. The same case for sum, maximum, minimum, and average. The only exception is count star, which will count every row, including those with a null. So let's use Oracle Live SQL to demo the course. So let's look at Oracle Live SQL. We'll first go through some examples of sum, average, and the minimum and maximum. It basically returns actual tuition for the sum of actual tuition, the average, and the minimum and maximum. And note that minimum and maximum can be also applicable to chart columns. And the average and sum apparently only works on numerical values. Now let's look at some example of the count star and count column. In our particular case, we actually don't have a course without instructor. So the count star and count instructor name will return the same value. Let's try to insert a value. I'm bringing up, this is the create and drop statement, and I'm going to insert a value without a instructor name. So now I'm inserting, oh, we shouldn't use this primary key. It has to be unique. So we have one more column, one more row. This time, count star will return everything, including the one with a null instructor name. But count instructor name will return all the values except for the row with the null in it. That's what we were just talking about. Count star returns 7 rows, including the one with a null value, and count the instructor name returns all 6 occurrences where instructor name has a value. And how about count a distinct instructor? We have 4 distinct instructors. I believe Obi-Wan Kenobi and Yoda show up twice. Now let's look at how nulls are handled. Let's create a table and insert some values. We have a -1, 1, 1, 2, 3, and now in these 6 rows. So this is a new table, and how about we select sum? If we do a sum, it should go through adding all these up together. -1, 1, 1, 2, 3, and it should return 6, right? Now, how about average? The sum is 6, and 6 divided by 6 should be 1. Is that right? Let's run these 2 sequels. The sum is 6, which is correct, but the average is 1.2. What is the reason? The reason is the last row is a null, so this row is ignored. We are actually calculating 5 rows, which with a sum of 6. So 6 divided by 5 rows returns 1.2. That's why it returns a 1.2. The minimum and maximum, apparently minimum should be -1, and maximum should be 3. Note that now is neither the minimum nor the maximum. It is not considered in any of the calculation. So it's neither the maximum nor the minimum. Now let's look at average. And then let's look at count. And I believe I seem to have 2 same columns here, but count star and should count every row, including those with a null, right? So we have 6 rows here. And count ID will return count of rows where ID value is there. that should return us a 5. And if we are counting distinct ID, it will be -1 is one occurrence, 1 is occurrence, 2 is occurrence, 3 is occurrence, and now is not considered. So it should be 4. Although we actually have 5 values, -1, 1, 2, 3, and now it's not considered. So we only have 4 for the last count distinct. And that's exactly what you should get, 6, 5, and 4. Okay, so much is for aggregation functions. I'll see you in next lecture. In this lecture, we are going to talk about how to change the table data. So accident happens. When you enter data into the table, you may make mistakes. You may miss a field, you may miss some word, or you may have made a typo. How do you handle these data mistakes? How do you correct them? There are general 3 approaches. The first of all is the toughest is you drop the table, recreate it, reinsert. That basically deletes everything from the old error table. But then, if you are just made one mistake out of 1 million rows, that's probably what you want to do. The second approach is a delete a row, then reinsert that row. And third one, maybe you want to update the value. We already talked about drop, create, and insert before. So this time, for this session, we are going to talk about delete, insert, and update. So first, we review what is an insert statement. Insert statement, we talked about, you insert into a table with a column list. Then you provide the values you want to insert. Each insert handles 1 row. Well, that's a single insert. And for this row, your database will enter the value list matching to each column based on your decision. So this is a single row insert. You can also do a bulk insert from other tables. You can do an insert into some table by selecting values from another table. And of course, here the second part of this statement, select where, this basically is a separate SQL statement of its own. So you can treat this just as if it's a simple, separate, independent select statement. And you can apply where, you can apply different selected column list, and the column computation too. The only thing required here is that whatever you select in this column list has to match column list here. The number of rows, the data type, all must be matched. Now, of course, just like a single insert, you can also ignore this column list. However, if you do that, the select column list must be returning all columns in the target table in the order that listed in the create statement. So let's talk about delete. When you want to delete a certain row from a table, you run a delete by delete from keyword followed by the table name. Then you follow by the where clause, or to specify which row you want to delete or which rows you want to delete. Every row that meets the Boolean expression here will be deleted. If you don't specify a where clause, it will delete all rows. And remember this, someone made this mistake, delete all rows from the table. So this is delete. And the where clause here meets the same criteria, same format as the where clause in select statement. And if you can also imagine how this delete is executed. Database will go through row by row. If the where clause condition is met, this specific row will get deleted. For example, let's do a little bit of the Jedi purge here. We will do a delete from instructor where instruction affiliation equals to Jedi. Then that which means we will go through row by row. We see Obi-Wan Kenobi, instructor affiliation equals to the Jedi. we will apply delete to this the row. Then we also, in the same fashion, we delete Yoda, delete Anakin Skywalker. When we run into .cds, where instructor affiliation equals to sys does not meet our condition, we will ignore this row, which means in this particular case, it's not deleted. It will remain in the row. So the next effect of this delete from statement is to delete every row. All row whose instructor affiliation equals to Jedi will be gone, and only whoever is not Jedi, either it's a this or a none or something else, remains. So once you delete a statement, then you can insert the data back by using an insert statement, just like what we discussed before. This is the second approach. The third approach we talked about is to simply update all rows meeting the where condition. So you will use the keyword update followed by table name to specify which table you want to update. Then you need to put a set. This keyword specifies the column list and the value, the column name and value pair that you want to apply. So you will specify column name 1 equals to value 1, column name 2 equals to value 2, etc., separated by comma. Eventually, you will have a where clause, which will indicate which row you want to update. Is that everything from the instructor affiliation equals to Jedi? If you do not have a where clause, then similar to delete or similar to select, all rows will be affected. You will update all rows. For example, here, you want to update instructor. Set instructor name. Whenever instructor name equals to Anakin Skywalker, we will change the instructor name to Darth Vader, and we will change his affiliation to sys. Right? Makes sense, right? And these two column name and value pair will be, this one and this one will be separated by a comma. Update can also be performed by calculation. What I mean is, if you want to change a value based on the previous value, for example, if I want to have a 10% increase to the actual tuition column, I will do the same thing using update keyword, registration table name, set keyword. I will set actual tuition equals to the previous actual tuition times 1.1, which is a 10% increase, where course name equals to something. Or maybe because Anakin Skywalker has changed his affiliation, we want to invalidate his class names first for now. So we'll set this as null. And the note here, you can either set this as a calculation, a null, a fixed value, or any other column. So this is the beauty of update. It allows you to do a little bit of calculation of inline editing that you can dynamically change your data. Okay, let's try to work on some SQL examples in Oracle Live SQL. First of all, let's create a table, instructor new era, just to demo our points. So we talked about inserting into this table with the existing table from instructor. It's existing data from instructor, and 4 rows get inserted. Let's see what is there. Selected, you see all 4 rows, as we discussed before. Now, if I want to delete from this table without the where clause, guess what will happen? 4 rows get deleted, as stated here. Okay, so let's try to do an insert based on column list. again, we are selecting this affiliation instructor name. And like we said before, these column lists do not necessarily need to be in a default order, but it has to be matching whatever is specified here. So although instructor name comes first, we can select affiliation first as long as affiliation shows up in this column list first too. So let's run this. 4 rows inserted. Let's do a select again. And this, everything is fine. Jedi is in affiliation, Sith is in affiliation, and all names are in name field. Now, you can also do a select by instructor name only. I'm not going to run this because it actually will be in conflict with whatever data I have. But guess what will happen if you do this? Actually, I will run this because it will give me an error. Because select star from instructor will provide you with 2 rows or with 2 columns. And here you are only specifying 1 column. So our code will recognize the difference, the mismatching, and tells you you cannot do it. You set too many values because you getting 2 values here. Okay. So now let's do a delete from actually it should be instructor new error where affiliation equals to Jedi. Guess what will happen? 3 rows with affiliation Jedi got deleted. Let's start clean up a little bit first. Let's start from new error and see what's remaining. The only thing remaining is the one that the instructor affiliation is not Jedi. So let's do a little bit update. This is the SQL we show in the PowerPoint, where instructor name equals to Anakin Skywalker. We will update the instructor name and affiliation. Run it. 1 row get updated, and from instructor. Let's run this and see what the result is. We have Darth Vader here with this. So this table is properly updated. Let's also do a quick run of tuition increase. It should be throat choking, I believe. So I'm updating the registration table, set the tuition to 1.1, which is a 10% increase. And where course name is for throat choking, which is definitely helpful. Oh, there's no such table, such course. Maybe it is checking. I think I made it. Let me confirm what is there by checking the record. Ah, I'm missing C here. So let's quickly check what is in the registration table. Select star from registration. Did I input the proper data? Oh, because I didn't put the correct data inside. That's why SQL statement was not able to find the proper row. But if I choose to increase the tuition of this introduction to the force, 1 row get affected. And now It has an actual tuition of 198. Remember, it was 180, right? So this is so much is how do you correct data mistakes? You can either drop the table and recreate it and reinsert, which in my opinion is the most violent, most extreme way of doing things. And you can also delete the affected data and reinsert it. You can also update by running the update statement. And it's even actually beyond update, changing the mistake, because sometimes it's not a mistake. You just want to change the data. Like in this case, you want to increase the tuition, and update can help you with that. So we are going to talk about how to change table structure in the next lecture. In this lecture, we talk about changing the data, but what if you want to change the data structure? We will talk about this in the next lecture, and I will see you there. In this lecture, we are going to talking about how to change table structure. So we talked about how to change table data in previous lecture, where you can update or reinsert into a into a cell in the row. But what if you want to change the table structure, the table content, meaning that you want to have new columns or new definition of columns? For example, the tuition was decimal 72. What if I want to increase the tuition and now I need to have a tuition of A2? Or maybe I want to add a column, some kind of a type for instructors. These are table structure changes. That is, adding a column, modifying column, possibly dropping column. Well, there are two ways of doing that. One is you can drop the table, recreate it, and reinsert it. Another way is to use an alter table, a statement called alter table. The alter table, you can add or modify by using the keyword alter table, table name, then followed by modify or add, and followed by new column definition. Now, this is Oracle syntax. The PostgreSQL syntax or some other DBMS is a little bit different. In those DBMS, you will have to say add column instead of just using add. And similarly, if you want to drop a column, in Oracle, you put drop column, which we are not covering here, but you need to know for dropping column, and for other DBMS, you need to check the vendor's manual on how to do it. What we are covering here is Oracle's way of adding and modifying columns, which starts with the keyword alter table, followed by the table name, then followed by keyword add or modify. Then you follow that by new column definition. Adding column is simple. You just add whatever column definition is. For modify, you can either change the data type or you can change the null property, whether it's a not null or null. You can also change them both in one single statement. You can do this modify, actual, tuition, decimal, not null, right? So let's run some Oracle Live SQL to prove our point. First of all, let's say just I want to modify the actual tuition to decimal A2. That's the scenario we've talked about at the very beginning. Table altered, alter table, registration, modify. So if you check the schema now, in the registration area table, actual tuition now is number A2, right? Now let's go back to SQL worksheet and try to alter table instructor by adding an instructor table, instructor type. Oh, I just ran it. So basically, there is already a instructor type column there, and I already put the instructor. Now let me alter table by drop column of instructor type. And because if I want to drop, I do not need to specify the data type. You are dropping that, right? You don't concern what the data type it is. So I will drop a column dropped. Now let me add it back. So table altered, the dropped column is added back. Let's select star. So you can see that the first time you add instructor type, it's all default to now. That would be interesting to see how you want to modify. Is to chart 10 and not now. And if you guess, Oracle will error it out. You make it wrong. You made it right, because there are now values in the instructor type column, so it cannot be not now. What you can do is you can update column, set a value to it, so that it's not now anymore. And here we are running an update to set the column type equals to T without a where clause. By not adding a where clause, we are doing this update for all rows in the table. As you can see, 4 rows updated, all of them. Now, if I alter the table to change the instructor type to chart 10 and not now, it will work, right? So much is for alter table, add, modify. And the one thing to note, if you ever want to use a drop column, then you will need to use drop column instead of just drop. This is a little bit trick in Oracle. So let's go back to the slide and review a little bit. We talked about drop, delete, and alter. Students constantly got confused when they first encountered these statements. Drop removes the whole table definition. It will just drop the whole table from the database. And because of this, we are not specifying column list, and we won't use the where either, because drop is removing the whole table. Doesn't matter what condition you meet in each row. Every row is gone. Neither is a column list. Neither will column list matter, because the whole table is gone. Every column is gone. So the drop syntax is simply drop table, table name. Delete removes row, but the table structure is not changed, and the table is still there. After delete, table will still exist. Even if you delete without where, which deletes every row, the table is still there with the whole proper structure. It's just that it's empty. So delete its own row. It's not about column list. It's not deleting columns away from rows. It's deleting the whole row. That's why you do not specify column list. That's why it's delete from a table without specifying any column list. But it can have where to specify which row it is. And the alter table, drop column, removes the column. Because it removes the column from the table, every row is affected. There's no where. So let me quickly write down the proper syntax here. So this is alter table. You will drop table, the drop column, excuse me. This is the drop column syntax. You're altering table. You don't add where clause. For drop table, there's no column list, no where clause. You just drop table instructor. Students sometimes put a star here, thinking that they are removing everything, which is wrong. You don't add anything. Drop table is one key phrase. And similarly, delete from. Delete from, there's no star here. I believe some students got confused with select, so they add a star or a column list here, but no, because delete is not deleting on column list. It deletes rows. All columns are affected, so there's no need to specify a star or the column list. You just delete from instructor, but you can put a where to specify which rows is affected by this delete. So much is drop, delete, and alter. Let's also compare alter, add, and the select. So when we say we want to display something, we want to do a select as the column alias. What is the difference between this and alter table add? Alter table add actually adds a column to a table, whereas select, that's an instructor name as something from, as let's say I name, for example, I name from instructor case doesn't matter, but I just type there so that it looks better. Select instructor as is instructor name as I name. It's not creating a new row. It's just displaying it for your convenience. Displaying that with the title for your convenience. Alter table actually add a table to this select. All right. So far so much for all the table changing, including table data changing and structure changing. And in next lecture, we are going to take a deep dive into the where clause and see how we can best utilize all the versatile functionalities of a where clause. I'll see you there. In this lecture, we are going to go through where clause different options. So we already worked with a where clause before. We use that in select, delete, and update statements. Basically, we use the where clause to identify a subset of data which meets a certain condition, which we call filtering conditions. DBMS will then go through each row and apply SQL action on the rows that meet the where condition, whether it's a select or delete or update. These conditions can include the comparison between original columns. It can also be computed columns. For example, in this where clause, we have an actual tuition times 1.1 is a 10% increase greater to 500. That will tell us which registration will have an actual tuition more than 500 if we have a 10% increase. The comparisons can be done by utilizing these comparison operators. For example, equals to, and there are two not equals to. The first one is a standard SQL way of doing not equal to comparison. Some databases also use the second one, the more C languages look like not equal to sign. In our course, we will simply use the standard SQL not equal to. Then we of course we have a greater than equals to, less than or equal to, these operators. We can also combine single comparisons together to form a compound comparison. We use and or not, which we call a logical operator, to connect two different two different conditions together. For example, tuition greater to 500 and sales to less than 200. If both conditions are met, then this will be met. If any of them is not true, then the whole condition is not true. Similarly, for or, any one of the conditions is met, then an or condition is met. For example, tuition greater than 500 or sales less than 200. If sales less than 200, then the condition is true. And similarly, we can have a not. Remember, for this and or not, if each and or not, the whole where clause is evaluated on one row, on the same row. So for example, this actual tuition times 1.1 greater to 500 and the student name equals to Luke Skywalker is evaluated on one row. If this row have the actual tuition greater to 500, meanwhile the student name equals to Luke Skywalker, then it will be true. It does not mean that you will choose two rows and these two rows will have different conditions. This is not the case. The case is the whole where clause condition is applied on a single row, row by row. So there's another option of where clause, which is between and, where you will just put the column name or column computation and put a between and keyword with lower bound and upper bound. It means the column computation or column value must be greater than or equal to the lower value and less than or equal to the upper value. Remember, this is inclusive. So for example here, where actual tuition between 200 and 400. If the actual tuition is 200, it meets the condition. If the actual tuition is 400, it also meets the condition. If actual tuition is anywhere between that, it also meets the condition. Unless it's like 199, then the condition is not met. And another common mistake is we need to put lower bound be lower than upper bound. Here you have to be between 200 and 400. You cannot put between 400 and 200. If the upper bound is less than lower bound, then the condition will always be false. So let's go to Oracle Live SQL and try some quick where's the clause. So I'm copying this here, and let's select from registration table without where clause first, so that we know what's in there. There are two rows, both from Luke Skywalker. Another is actual tuition is 198. Another is now. So if I run, there's actual tuition greater to 150. The first row will return. The second row won't, because the second row's actual tuition is not greater to 150. And now let's do this AND. AND value means it has to be actual tuition times 1.1 greater to 150. At the same time, the same row, student equals to Luke Skywalker. But how about OR? OR returns two values. So here, if a student name equals to Luke Skywalker, and the actual tuition times 1.1 is greater to 150, this row meets the condition. And for the second row, as long as student name equals to Luke Skywalker, then the condition is met. This is the definition of OR, and you can compare contrast with AND. So in this case, for this particular OR where clause, both rows meet the condition. We can also put a not additional actual tuition times 1.1 greater to 150. And we can also have this where actual tuition between 100 and 200, which will give us the first row. Now, remember we talked about inbound and upper bound. If I put 198, will the first row still be selected? And the answer is yes. This 198 lower bound is inclusive. How about we put between 200, between 198 and 197, where the lower bound is higher than upper bound. We're not receiving anything because lower bound cannot be higher than upper bound. However, there's no error message. So this is something to pay attention to when you start using this between. If lower bound happens to be higher than upper bound, you will not get what you think you will get. You will not get anything. However, you are not getting error message either. So it's difficult for you to identify. This is something you need to always put in mind when you run between and. So much is for numerical comparison for where clause. We will talk about string comparison in our next lecture. I will see you there. In this lecture, we're going to talk about the string comparison for where clause. In comparing the string, we line two strings side by side. For example, introduction versus introductory. We will compare character by character. First character first. Like for example here, I equals to I. So we compare to n, then n equals to n, and t equals t. We compare so on and so forth until finally we reach I versus O. That's how we can tell the difference. If a string finished earlier, then the string is considered smaller. For example, if I have an intro here, at the 6th digit, intro has no character anymore, but the other two have more things to come. So intro is the smallest, whereas the other one is bigger than intro. So how do we compare I versus O? We do character comparison. It's based on ASCII2. ASCII2 is a standard encoding for characters. So here is the US ASCII2 code chart, and you can see that it starts from the upper left corner and goes down first. Then once you finish one column, you start with the second one. So the numeric digits 0, 1, 2, 3 start at the third column. And remember, this is hexamal. All these values are hexamal. And the fourth column is for uppercase characters. And the sixth column starting with the lowercase characters. In general, 0 less than 1 less than 2 all the way to A less than 9, and A less than B, B less than C, all the way to X less than Y, Y less than Z. So is the case for lowercase. Between the data sets, between the character sets, uppercase is greater than numerical values, numerical digits. Lowercase is greater to uppercase. So if you have a comparison between uppercase and lowercase a will be greater than uppercase a. And lowercase a will be greater than uppercase Z2. And also we can use logical operator and between and and. So for example, where student name between A and F, it will start with a character. If someone's name is just A, then this condition is met. It is in between A and F. Then anything like A0, Alpha, Albert, Adam, all this will be meeting the filtering criteria. Then anything start with the uppercase B, uppercase C, uppercase D, uppercase E are all falling into this condition, no matter how many characters they have after B, C, D, E. And finally, we have a single F, uppercase F. But anything starting with uppercase F with some more characters will be outside of the upper boundary. And remember, lower boundary has to be lower than upper boundary. So you cannot put like between F and A. That will give you nothing. So One thing to note, which we mentioned briefly when we introduced data type and insert, some DBMS, such as Oracle, can do implicit type conversion. It can interpret the following as a numeric comparison, because actual the tuition column is a decimal column. So Oracle will try its best to try to interpret what do you mean by decimal value greater to a string. It will try to convert a string into decimal, and in this case, it happens to be working. Our advice is don't trust it. If they can interpret this right, they can also interpret it wrong. DBMS cannot properly interpret it if you cannot properly write it. An example is 090 and the comparison to 10. Is 090 greater than 10? If you consider it a character, then the first character of comparison, 0 is less than 1. So the string of 090 is less than the string of 10. But if you consider this as decimal value, then 090, which is 90, is definitely greater than 10. So just by interpreting them as different data types, you will have different results. That's why we said don't trust it. Always explicitly write your type. Don't put the single quote around numbers. So another interesting topic about string is not about comparison, but more like pattern matching. We frequently run into questions like, oh, I want to look for someone's name starting with Luke. If you translate this request into a where clause, it basically means it's a string starting with LUKE, followed by an unknown number of characters. Right? Also, if you are looking for any SQL course on Udemy, what you are looking for is a course name starting with an unknown number of characters. It can be 0, then followed by the word SQL, then followed by an unknown number of characters. It can be 0. So it can be fundamental SQL programming, which starting with some fundamentals, unknown number of characters, and SQL. Then a programming is another unknown number of characters, or in our case, introduction to SQL. Starting with unknown number of characters, introduction to, followed by SQL, then followed by 0 characters. All these can be matching. And the similarity between these two requests is that we are looking for a way to combine a known character set with an unknown number of characters. The latter is called wildcard. So it will be Luke plus wildcard. You are looking for something like Luke with a wildcard, or something with a wildcard followed by SQL, then followed by another wildcard. And SQL provide this wildcard functionality in the like operator. Like will match string pattern containing wildcard. It uses %sign for multiple character wildcard and underscore sign for single character wildcard. Most of us today has experience with the star character wildcard when you do Unix or DOS operations. It's a similar here, just that you are using percentage. So you're using the % sign. So if you are looking, here are some examples. If you are looking for something starting with S, then it will be a star with the %, which means starting with S followed by an unknown number of characters. And similarly, ending with T is starting with an unknown number of characters, then followed by a T. That's %T. And starting with S and ending with T is S and T joined together with a % in between, with an unknown number of characters in between. Then containing the pattern SQL is wildcard first, an unknown number of characters, SQL, another set of unknown characters. This is containing a pattern. A common request is, I want to find something with a word SQL, but regardless of case. In this case, we can use the upper or lower function. We can put the upper in the course name to convert everything into uppercase. Then we will use this uppercase string or pattern matching for like percent SQL percent. Of course, here SQL has to be uppercase. And we also have a single character wildcard. If you remember that last character unknown, but it must be SQ, then you can put SQ underscore, or the first character unknown, but there's definitely one character there followed by TAT, MENT, then you can do that. And you can also have multiple underscores, like last 4 charts unknown, but it must be starting with state. That will be provide us with like statement or something. But as you can see, if you use underscore, you have to make sure you really know the strength, the length of the string. This usually is not so desirable. So percentage sign is used much more than underscore sign. And the big difference between underscore and the percent is that underscore means there must be a character. So if I put a state underscore, 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 that means there has to be 4 characters following. It has to be like statement or state space SQL. You cannot have states plural or staten, 3 more characters, or something like state 1, 2, 2 more characters. None of this will match the 4 character pattern. While percent means there may be nothing or 1 or many characters. So I put the state percentage, 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 percentage here. All of this, including the one in top, state SQL, statement, state XYZ, state space, they will meet this requirement. By the way, there's definitely no need to put 4 percentage sign here. I put this for them together just to show you what it looks like. But in reality, 1 percentage sign is enough. So let's run some SQL in Oracle Live SQL. So let me copy my code here. First thing we see here, we are comparing, we'll try to match any student name that's greater to H. So when we look at the name, student name Luke Skywalker, it starts with L. Uppercase L, based on what you can remember, is higher than H. So any course selected by Luke Skywalker will meet these criteria. We run this and we see the 2 rows from registration table. Similarly, when you compare this Luke Skywalker versus L, it's going to be L compared with Luke. And the first character, they equals to each other, but the second character, this one, the L character, the L string does not have any second character, whereas the Luke Skywalker has a U. So Luke Skywalker is larger than L, which means this statement also will return both rows from Luke Skywalker. Now, how about H? We know that L, uppercase L, is actually lower than lowercase, lower than any lowercase. It can be H, it can be A. It can be S, just what we see. So if I put A here, because L, uppercase L is less than lowercase l, this condition will not be met and we will not see anything from Luke Skywalker. And by the way, for illustration purpose, there are only 2 rows in registration table. Both belongs to Luke Skywalker. That's why you do not see anything else. And how about a bonus question? student name greater than 0. And of course, any character, any alphabetical character is larger than 0. So you will see anything that's starting with the alphabetical number, not alphabetical chart. And we talk about this briefly. Our code can manage to interpret this as a numeric comparison, which it returns 180 properly, but you shouldn't rely on this functionality because here I will show you 10 is greater than 090, which is true for everything in registration table. So it will return both rows from registration, right? So much is for character comparison. Now, let's talk about like. So I'm having a series of like statements here, where course name like intro. What will it brings us? It will bring us introduction to something, right? And which it does. How about like percentage 101? It will return us all the courses ending with 101, the character 101. Oh, throat choking 101. And how about this? Percent, force, percent. It will return to us every course name containing force, regardless where it's located at. And you can even have something like a force 101 without any other character in front, or introduction to force, nothing followed by force, which is what it's trying to do, introduction to the force, nothing after FORCE. And if you just want to check anything that is regardless of the case, you can use the upper. For example, if I find anything, try to find anything containing an F, you see farming, you see fighting, you see force. Interestingly, they actually have all F in uppercase. How about I use a S? Any course containing an S, regardless of case, will return dummies. You have an uppercase surviving. You have a lifesaver. You have a ghost. Regardless of case, they were all selected because we convert course name to uppercase first. And similarly, you can do this. If you want to use the lowercase s here, well, this is for demo purpose, but thinking if you are comparing two columns instead of comparing a known string, that's when you need to convert both to either upper or lower, right? So this is what I'm trying to do here. We're returning the same value. Everything contains s, regardless of case. And for this purpose, for demo purpose, this is just a percentage sign, but you may need to use this to other columns where this will be where you, or combination of columns where this technique will be very useful. Similarly, we can do a like with underscore, which only fits in one row. So instruction name like underscore ODA, of course it returns Yoda. If you happen to have some instructor's name to be Soda, it will get selected too. But what if it's a Yolanda or Yoloda? Then because it's more than one character, it won't be selected. And we talked about this. We have, I believe we have a course whose name is Dagoba Surviving Camp. What will return from here? It gives us the Dagoba Surviving Camp, 8 characters, and it's hard to tell here, but there are 1, 2, 3, 4, 5, 6, 7. Oh, I think I counted it wrong. It's 7. 1, 2, 3, 4, 5, 6, 7. Yes. So that's exactly what it's returning. However, if you that requires you to know that that planet's name is exactly 7 characters. If you do not know, or you just think it was 6, then it's not going to return anything in the second example. No data found, because Dagoba is 7 character and you are doing a 6 character string search. Whereas if you use a percentage, 6% will still provide you with what is needed. Dagoba is here, right? So in general, or in this case, 1% is actually the same as 6%. So in generally, you need it's recommended using percent, because the fact that you are using a string matching, pattern matching, means you are not sure about the value. In this case, why would you be so certain that it will be just missing 1 character? So that's why percent sign is used more popular than underscore. So much for string comparison and pattern matching. I will see you in the next lecture. In this lecture, we are going to go through null handling in where class. We already talked about what null is. It means a missing value, and it's very important to understand. It means missing value is nothing, because this explains the next topic we're going to have is a Boolean logic with null. We already talked about conditions. Where clause condition, it can be true or can be false. But once you involve null, there's one more. It's unknown, because if it's missing, how do you know whether this is true or false? You don't. It simply means it's not known. Any logical operation with null will return unknown. Like if you are measuring 1 greater to null, it will be unknown. And if you are measuring 1 less than null, it's also unknown. If you want to measure null in a null list, it's not known either. Null is neither equal to nor not equal to null. The comparison between null equals to null or null not equal to null, both will return false. It's not going to give you any definite answer. I'm sorry, there was a mistake. The result of null equal to null or null not equal to null, both will be unknown. You will not get any true answer from either. They are not mutually exclusive, simply because they are simply unknown. So the way you do detection to test null is to use is null or is not null. These two are the SQL statement, the SQL keyword to detect whether it's a null or it's not a null. You cannot use equal to null or not equal to null. The number 1 mistake I see in students involving null is this last name equals to null. A lot of students will write equals to null when they're supposed to write is null. And I do expect seeing more in this class too. So let's quickly run through some Oracle Live SQL. So let's play with some null equals to null, null not equals to null, null in null, not null in null. Or we haven't talked about in, but basically I believe you can guess what it means. It's a list where you can select from. So first one, select star from null, or let's just run all of them, because we all know all of these will return unknown. So you are not going to get anything. All of them are no data found. Null equals to null. Null not equals to null. No row will ever meet this condition, or null in null, or not, even you put not null. Because some students will think, if null in 1, 2, 3 is not meeting the condition, maybe I can put a not. The truth is, this is not false. I think I made a mistake just now by saying that was a false. It's not a false, it was unknown. So not unknown is still unknown. And the most creative way I saw a student did was that he tried to do where not instructor name like %. His reasoning is if like % basically will return you anything with a value, right? If it's a null, of course, there's no, a null value will not give you any like %, right? So this will return you anything with a value. And by putting a not, maybe he can get a null. But that's not true, because if you have an instructor name equals null, you're going through this row by row. For instructor name equals null, the null like % is going to return you an unknown, and not unknown or not null is still null. So you are not going to get away from that. The only way you can do it is by using is null. But in order to show this is null, we need to insert certain values, or maybe I have already get a value. Let me check from instructor table. No, so let's do a insert first. Let's insert overlars who is not associated with any affiliation. And now let's do equals null. Is there going to be NA equals to? Apparently not, because even for overlars, null is not equals to null, right? How about equals to null enclosed by single quote? What it does, and I do see students doing this too, but what it does is it's creating a varchar, a char string of null. So it's not null, instead it's a string with value. Similarly, this affiliation equals to single quote, this gives you an empty string, a string with no value, with empty value, but it's still a string. So neither one will provide you with anything, with a matching of nulls, right? And we talked about like % and not like % just now. Neither will return anything. Oh, the first one, I'm sorry. The first one will return you all values, right? Because it's a like %, but not % will not, the first one will return you all non-null values. Whereas the overlars, whose affiliation is null, will not meet this like % criteria. However, by adding a not, you are not going to get overlars too. So the only way to get a null is using this is null. And then you can use a is not null to get all the non-null values. Or similarly, you can use a not is null, which will return the same number, the same rows. So much is null. And remember, is null, is null, is null. Do not use equals to null. Do not use any creative way trying to figure out what the null value is. All right, so much for now. I will see you in next lecture. In this lecture, we are going to go through in and subquery in where clause. We already see some examples of in, where you just put a where clause with a column name, followed by column name, and the in keyword, followed by a value list inside a parenthesis. For example, where instructor name in Yoda and Obi-Wan Kenobi. The only thing to pay attention to here is when you use characters, make sure that you're enclosing each character by single quotes, not the whole list, like the one at the bottom. Some students actually put a single quote around the whole list, What it does is actually asking DBMS to find an instructor name with Yoda, Obi-Wan Kenobi. So it's a whole string. It's no longer two separated strings. This is wrong. So remember, each string should be enclosed by a single quote. And also, this in operator can be used on numerical value too. It will follow the same syntax where column in value list enclosed by parentheses. So in operator can be much more useful when you associate using subquery. So what is subquery? Let's talk about a very common usage pattern first. So a very common usage pattern is to use the result of a query in another queries in clause. For example, I may want to find all the instructors affiliated with Jedi. Then I want to look for all the courses of this instructor. I have two ways of doing that. The first is to I will run a one query, select instructor name from instructor, where instructor affiliation equals to Jedi. I will get a list of results of names, instructor names. I will put this into a select star from course where clause. So let's show this in example in Oracle Live SQL. I will run the SQL, run a small query. There are three instructors affiliated with Jedi. So I'm copying this over. Instead of writing this down, I'm going to use copy and paste, which is some kind of technical advancement. Then I will use this name list inside an in clause running against course table. And this is a valid SQL statement which will return the right result. However, think about a university with 2,000 instructors. There's no way you can dynamically select these 2,000 names either by typing or copy and paste and form a SQL statement. So SQL provide another way of handling this process by putting the first query in parentheses. Parentheses, which is here, you put this into a parenthesis and place it in the second query inside this in. So you will have a main query with select from and where column name in. Then inside this parenthesis, you have a subquery, which will return a value list. For example, right here, we can copy this subquery, put it inside the in, and run it, and it will return the same result. This is how you use in. Now, if you think further down this subquery thing, it's returning a value list so that we can put this into in. What's the difference between manually typing a value list and selecting something from a subquery and generate a list? The answer is no, there's really no difference. So if you even extend this idea even further, if I have a comparison, like if I want to compare tuition greater to actual tuition, then I can even use subquery to return this one of the values. It will be a single value used using aggregation function, like sum or average, or use a single value comparison under any or prefix. So if you are using aggregation functions, for example, you can have a where tuition greater to the average tuition. And this statement will provide me with all the tuitions, all the rows where tuition greater to the average tuition, right? And similarly, in the second statement, I'm going to select the maximum tuition first. I get the understanding of what is the maximum tuition. Then I can filter in the main query, find rows where the tuition equals to the maximum tuition. Let's try an example. In Oracle Live SQL. So I'm going to select start from course where tuition greater than the actual tuition of any force class, right? So this value, this subquery returns the actual tuition, the maximum actual tuition for any course that's a force class. So let's run the subquery first. And the result is 180. And by applying this subquery, the select should return me any course whose tuition is greater to 180, which it does. And this example actually shows you how to write your own SQL when you encounter these kind of questions. You write the subquery first, run it, make sure the subquery is returning what you expect. Then you place this into the main query. And you can even use the placeholder first. Like I can put, oh, this will be maximum tuition. And once I finish developing my subquery, you replace it. Right? That's how you write this query, by breaking that into smaller pieces. So this is relatively straightforward. Something can be confusing is the or and any prefix. So what or and any prefix does is that it's going to be the prefix of a subquery, and it's going to tell DBMS how to handle the processing of the value returning from this subquery. So if it's or, then in this where clause, the comparison has to be done after all comparisons are done. And their result will be AND together. If it's any prefix, then comparisons will still done row by row for all rows, but the result will be combined using OR, which means as long as there's one row from a subquery meet the condition, the any clause will return true. But you have to have all rows in the subquery meeting the condition for the all prefix to return true. Again, let's show this in an example. So let's see all first. What is returned here? It's going to return two rows, 50 and 180. So when you are running this query, you will go through all rows in course, row by row. We talked about this before. All select statements are done row by row. So you have 6 rows here. Let's copy and paste it here. For tuition greater to all, so DBMS will go through row by row. For the first row, it will go through the result of this query, which is 180 and 50. It will compare 200 to 180 and to 50. Since both are returning true, this is a good condition. This is a true condition where this will be selected. For number 2, since the first 100 greater to 180 is false, it's false. So this row will be discarded. Similarly, this 99.99 is greater than 180, as well as greater than 180 over 50. So the condition is true, and it will be selected. And the fourth one is not less than 180. It's a false, so it will be removed. So we go on and on and on, and finally these 4 rows, they are greater than the value of the tuition in these 4 rows is greater than all of the actual tuitions from registration. And when you run the SQL, it should return you all 4. Right? It's returning all 4. How about any? The word any means it will return if any of the row inside this subquery will return the value. Now let's see. Let's go get back whatever was there. So all these 6 rows. And the others, let's just focus on 2 because the others are actually pretty similar. Only this one will give us a good example of how things are happening. So for this row, the actual tuition, the tuition is 100. So it will go through all these rows again, all the sub rows, 180 and 50. Is that greater than 180? No, you get a false. But is that greater than 50? Yes. So one of the rows in subquery meets this main query's condition, which means this row will get a true. So this row will be selected. If you run this query, in addition to other rows, you will definitely get this row. Let's try. Right? So you get this 100 and the rest of them. So this is the all and the any. And you can apparently see that there are some overlapping in functionality between max and all or minimum and any. And greater to all is equivalent to greater to max. And greater to any is equivalent to greater than minimum. And less than all is equivalent to less than minimum. And less than any is equivalent to max. How to diagnose this is requires some deep thinking. So I would leave that to you to go through the definition of all any and the aggregations. But since they are overlapping each other, it's okay to use either. And you can feel free to use whatever you are most comfortable with. So much for where clause, and I will see you in next lecture. Okay, in this lecture, we are going to have a review session. If it's a regular undergraduate or graduate student class, it's a time for a midterm project or exam. Of course, there's no such thing as midterm in online class, but still, it's going to be very helpful to review what we have learned so far and put this into a big picture of how SQL and how data is used in the whole computer system. So let's talk about data life cycle, because eventually when you use a relational model, entity relationship model, or SQL, the purpose is to manipulate data. How data exists in a computer system, we generally categorize them as 4 steps. It's a create, read, update, and delete, which is called the CRUD in some of the online documentations. This is a generic life cycle of data in any computer system. It's not SQL specific. If you write the Python or Java code, you will have to follow the same process. Although some of the process, in some of steps, you may not aware that this has been done. So the first step is create, and the corresponding SQL statement is to create table and insert data. The second step, of course, once you create a data set, you need to read from the data set, and apparently this maps to the select statement. And then usually after you read, you don't just read the data itself. You need to do more manipulation. For example, you need to update or delete and insert, or sometimes you need to alter, add more columns. And eventually, after you finish using this data set, you will drop the data or delete, or in SQL statement, you will drop the table. So this is the whole process, or the whole life cycle of data in any computer system. And as you can see, we have already learned all the statements. So this is already a wrap up of what we have learned in the first half. We learned all the statements. The second half, we will go deeper into select statement. There are more in select statement on how to read and organize data. So this is so far we have done in midterm in the first half of our class. So as for the midterm project, we are going to give a real world scenario, and we are going to put what you have learned to practice. We are going to go look at the insurance claim invoice. I believe all of you have received some insurance claim invoice like this. It has a date, and there's a customer ID, a customer name, or in this case, customer is also called patient, and street address, city, street, state, and zip code. And for each patient, there's a list of providers who charge you a fee, and there's insurance coverage. And coverage usually does not pay 100% of the fee charged. So there's a balance remaining for the patient to pay. In this case, it will be provider, fee charged, coverage, and the balance. And each provider can belong to certain kind of association. This association can be some hospital, some clinic, or some other healthcare organizations. So this is a claim invoice, and we want to put this into a database, a relational database. And some people, without taking our class, has designed a data model where it has a patient ID, name, zip code, all the way to zip code, and claim date. Let me quickly mark it. So first, they have a patient ID, patient name, patient street, and also they design the claim date exactly based on the invoice. And then they also set up this provider line item, provider ID, name, association, and fee charged, coverage, and balance. So this is the model they design. And of course, you can immediately see there are issues with this design where you have repeating groups and you have data duplications, right? So as the midterm project is concerned, there are two parts. First of all, you need to normalize the given data model to certain normal form compliant. You need to describe it using shorthand representations and draw ERD. You need to create and some insert statement for the tables involved. And once you have done this create insert part, there's a part 2. I will provide you with a sample SQL to create and populate the tables. Then there's a series of questions asking you to write statements for insert, update, delete, select, and drop. So this is the part of questions for part 1. And you will do this 1, 2, 3, 4, 5 questions about normalization, shorthand representation, create statements, draw ERD, and insert into data. And then part 2 of the project, I will provide you with a create and insert. Then there are 20 questions that you need to answer. Find out associate names, find out associate ID, update, add a column, change column. Basically, as I go through these questions, you should be thinking of SQL statements that you are going to use. And eventually, after go through all these find out, you will drop all the tables. So these are the questions that we are going to have. And good luck with the project. In this lecture, we are going to go through a solution to the midterm project part 1. Remember, this is just my sample solution, and the data model is a mapping from real world, so there might be many different but both correct answers. Your answer may not be the same as mine, but still can be correct. I'm just providing my view of how to resolve this issue. Okay, let's start by first question, normalization. How do we normalize this design into third normal form compliant? We all know that if you want to do third normal form compliant, you need to become first normal form compliant first, then second normal form for second, and then you can achieve third normal form. Let's start by first normal form. First, let's copy this over and remove this command line to make it look better. The problem with this design is that it has repeating groups. And in order to remove repeating groups, we need to move relations inside this repeating group out into the parent relation. So by removing the parentheses and designate both patient ID, which is the original primary key, and the provider ID, which is the repeating group's primary key, as both of the primary key for the new relation. That's how we achieve first normal form. And if you are drawing a picture of table, you will see this part will become one row at a time, and this part will be repeating for each row, each new row. This is first normal form compliant. How about second normal form? Second normal form specify we need to remove partial dependency. So for patient name, street address, address to, city, state, and zip code, all these are dependent on patient ID, right? So these should be moved out. Let me copy this over. These should be moved out together with their original key, which is patient ID, into a separate relation. However, this patient ID primary key should still remain inside claim. Similarly, what is dependent on provider ID should be moved out, and the provider ID should still remain inside the claim table. However, there are 3 columns that we need to mentioning: fee charged, coverage, and balance. All 3 were a part of the repeating group. But once you put this into a claim table and you examine the functional dependency, you can see they are actually dependent on both patient ID and provider ID. The provider definitely will charge different amount for different patients based on whatever diagnosis they have, right? So these 3 should be moved to the claim table, whereas the provider ID and its dependencies should be moved to a different separate table. And now let's put both provider ID and the patient ID as a primary key of a claim. And there's no partial dependency in claims anymore, which means it is second form compliant. As for patient and provider, patient and provider, we now need to create their own entity. And don't forget parentheses for both new relationships. Now we have a second normal form compliant design where there's no partial dependency. However, as you can see here, association name is functionally dependent on association ID. And association ID is not a key, which means there is a transitive dependency here. So in order to remove this, in order to achieve third normal form compliance, we have to move association ID and its dependency, to a separate table, separate relation, and remove the dependent columns away from the provider table. So here we have association. We have association ID. This is a new relation, and we need to designate the primary key. All right. So this is the way we design. We're doing third normal form design. By going through one normal form at a time, we gradually remove repeating groups and the redundancies, and make sure there's no data redundancy and there's no, no unnecessary repeatings. And question number 2 asks us to identify entities and their relationships and their primary key. In fact, by doing normalization, we pretty much have gone through this and identify the entity relationships and the primary key. We may want to see the relationship types. For claim, it apparently have a magnitude 1 over patient and provider. So one patient can have multiple claim, right? And one provider can have multiple claim. So it will be patient versus claim will be one to many. And similarly, provider versus claim will be one to many. And provider association, let's name it the provider association just to make the clearer. Association and the provider is also a one-to-many relationship here. So this is how we define identify the relationships between each entity. And now let's start to write the SQL create statement. How do we convert a shorthand representation into a SQL create statement? Let's start by handling patient. If you still remember the process, first you start by writing the create tables keyword, and then patient, and everything else, then adding a semicolon as a best practice, adding a semicolon to the end. The parentheses are there. So we already get the basic structure of the table. Now the next step is to fill in the table content. Just SQL does not require you to add all the line break. I add line break here just so that we can see it better. It looks better and easier for us to handle, and add in some tabs. These are non-essential, but I'm just making that so that we can see it better. Now the next step, we want to create column by column. We want to make sure column by column it's SQL compliant. First things first, to make a name a valid name, we need to remove the space or replace it with underscore. So make all the names of compliant to Oracle's naming standard. And then we add the column data type. So for ID, it's a int. For name and address, let's use varchar because their length can change. And the length of the varchar depends on your exact application. Here we assume no name, no address will go beyond 100 characters, right? So this is address and name and city name. For state and the zip code, we pretty much know state will be 2 character, right? And zip code will be 5 character, a 5-digit. But if you want to use a full zip code, then you can define yours as a 9-digit or 10-digit, depending on your data format. Let's put char 2 here for the state. And now let's put char 5 for zip code. Remember when we talked about the social security number, it's a all digit, but if it's not aggregatable, you cannot sum or average, or the sum or average makes no sense, then you should put them as char for better display. Similarly for zip code, because there's no meaning of sum or average, so you should put them as char. Otherwise, if you have a zip code like in New York City or in New Jersey or in Massachusetts, where the zip code starts with 0, You may have a 4-digit zip code if you define them as decimal or int. So in this case, because zip codes are not aggregatable, or there's no meaning to the aggregation, you should define them as char. Now, once we finish the column definition, let's check the primary key. Since there's only one primary key, let's remove the star and add primary key constraint as a column definition, a part of column definition. So now you have the patient definition. Now let's do one more for claim. Similarly, we have the shorthand representation, starting with a create table keyword. Wrap it up by adding a semicolon, and let's put it row by row, column by column, I'm sorry. Now, I intentionally put claim date first because I want to let you know that primary key can be any of the column. When you define tables, the best practice is always put primary key as the first few columns, but it's not necessarily the only way to do it. You can put other columns as the first column. But let's make the names naming compliant to Oracle's naming convention by changing all the space to underscore. And then let's add data type column by column. Claim date apparently is a date. Int ID is an int, and it's an int. ID is an int. Fee charge, coverage, and balance, they all should be decimal. And because it's money, let's put the A and 2 as a scale, because we assume no charge will be lower than 1 cent, right? So everything is decimal A2. Now, last, primary key. Because this is the combo primary key, we need to use a table constraint, which we'll put here, primary key, and let's remove the star. We don't, patient key, patient ID, and the provider ID. And there's no comma after this. So much is for create table claim and the patient. We talked about data type selection, and we talked about primary key definition. Let me copy the other two tables, my definition of the other two tables here. Basically, we will follow the same process of creating these tables. These are the create statements that I created. You can compare this to your answer and see what's the difference. Again, there are multiple ways, many different ways to approach the same result. And your definition may be different, but they can equally be right. Make sure you understand what you are working on and what are the principles behind your decision. Question number 4, draw ERD. And let me bring up the one that I draw. Okay. So this is the ERD I draw. As we just discussed, patient have a one-to-many relationship with claim. Provider has a one-to-many relationship with a claim. And provider association has a one-to-many relationship with provider. Basically, that's how you draw an ERD with Crawford. Question number 5 is insert. Insert into provider table. And the way you do insert is you start by writing insert into keyword, followed by the table name, provider, followed by values. Now, you can add a column list here, or you can ignore a column list and we will insert by default order. Let's try the ignore column list first for the first one. So it will be 1 and add Maria. Remember, for characters, you need to add single quote, right? Single quote, then adding the association ID. we add this 3 according to the table definition, the columns in the table definition. So it's a provider ID, provider name, and association ID. You can also create insert statements based on a column list. In this case, you will add a column definition here. Provide the ID first, here, comma, provide the name, here, and the association ID. Last, where we will insert values. 2, name is Rachel. Remember to have a single quote around it, and the 102. Now, the third one, it says we do not know his association ID yet, which means it will be a now. There are 2 ways of doing this. You can either, without a column ID, insert new ID, bill, and the now. This is one way of doing that. You can also, using a column list, but without specifying association, and you put 3 and the bill, without the association ID. This way, the association ID by default will go to now. You can use either one of them, but remember, because the primary key is 3, so you can only insert one of them. You cannot insert both. Okay, so much is for the answers to part 1 of midterm. We will talk about solutions to part 2 in our next lecture. I'll see you there. In this lecture, we are going to go through the answers to the second part of midterm project. So in this midterm project, in this part, we are going to create some tables first, inserting some sample data, and then eventually we will go into answer a series of SQL questions. So let's bring up Oracle Live SQL first. This is Oracle Live SQL. Let me copy the create statements and the insert statements and execute these statements. So while it's running, all tables created and all the rows selected. And let's see what data we have. We have 2 providers, we have 2 associations, 3 providers, and some claims from this provider. I haven't populated patient, but it won't affect our SQL. I'm not going to ask questions regarding data in the patient table. So that's enough to insert. First question, find which association's name is Central City Dentistry. So when you try to do a find out, it always be select star from. And where do we have the association's name? It's from provider association table. And where association name equals to Central City Dentistry. And don't forget the semicolon as a best practice. Run this, you will get the result. Similarly, the second question asks, which provider's association ID is missing? So we are going to look at select star from provider where association ID. And now it says ID is missing, which means we are going to find some of providers where the association ID is now. We cannot do equals now because equals now will return you nothing. Equals now, nothing is nothing equals to now, and it will return not anything. So let's run this, and you will see no data returned. You have to use is now to properly identify the row with the association ID of now. Right? Remember, this is the number one issue students have when they handle where clause for now. Is now is the only way to do it. Now, update the association IDs for to 101 for the missing association, which is this row we just selected. Okay, let's do, sorry, it should be update, keyword followed by the table name, provider, set, association ID equals to 101, where, and we can copy the where clause here. This is how we do question number 3, and let's run. And one row updated. If you select star from provider now, there's nothing, there's no row with association ID equals to now. And if you just run select star, you can see that for Bill, the association ID has been changed to 101. Question number 4, change the state column of patient A table to not allowing now. So it will be alter table keyword, followed by the table name, patient, modify, state, to what do we desire? Not now. Let's run this. Let's check schema. It takes a while to bring that up, but once it's up in the patient table, for state column, the nullable attribute, the nullable definition is no. All right. So let's go back to SQL worksheet and go back to the question number 5. It says add a column called patient deductible to claim table. So it will be alter table again. Alter table, claim, table name, add. What's the column name? Patient deductible. It says it must have 6 digits in which 2 are decimal points. What does that mean? That means it has to be a decimal, 6 and 2. And now let's add this column. If we go to schema again, check claim table, and now have a new column called patient deductible. Right? Okay, let's go back to question number 6. There is an old table, patient 2018, which have the same structure as patient. Copy all its data into the patient table. So let's go back to, because the question says this new table has the same structure as patient. So let's create it by copying the definition of patient. And this time it will be called patient 2018. Let's insert some fake data. Insert into patient 2018 values, parentheses. So we have a patient ID, let's put 99001. Patient name is let's put the June. And street address, let's just use now, but now this is address 1, address 2, address 3, and let's put the address, there's a state, and zip code is 10001. Remember, this state is still not is still now, right? So if I insert this into the patient 2018 table, oops. Oh, I haven't created this table yet. But let's create a table and insert. So patient 2018 has a value where state is this value. Now, what if I try to insert the data in patient 2018 to patient. Remember, we defined the patient's date column as not now. So there are two questions. First, how to insert. And the second question is, let's put A and B. Now handling, or is there any now handling? Okay, so let's do insert first. Insert into patient. And I believe you still remember this. Let's do select star from patient 2018. It says cannot insert now into patient's date column. This is now. You cannot insert this now into patient 2018. Now, I know you will ask why this is interpreted as a now in Oracle. This actually is a feature in Oracle Live SQL. It's not a standard, but so it should have been now in order for in standard SQL. But Oracle can handle this differently. Oracle is handling this differently. Anyway, the main point here is, if I put let's say New York here, and let me delete all the data from patient. I'm going to delete all the existing data from patient 2018 and then reinsert with some data that has a value in the state column, and we insert. Now everything is good. So the key point here, one, Oracle manages to convert this quote empty string into now, which is the Oracle feature, not a standard SQL. As long as you understand that, that's fine. And two, how to insert into another table by using select. You see the statement here. And third, if a column is defined as not nullable, then you cannot insert the data into this column. You cannot insert now into this column, as we just see, right? So, question number 7. Remove all data from patient 2018, but the table should still be there for future use. Remember, we talked about how to change data and the difference between drop and delete. Drop will remove the whole table, including the table definition, the table structure, everything will go away. This is apparently is not what we are asked here. Delete will remove the rows. However, the table structure is still there, right? So that's what we are going to do here. We are going to delete from patient 2018, where there's no where because it says remove all data, so we don't need any where. Let's delete, and the only row should be removed. We actually have already used this statement just now, but this so much is for patient for question number 7. And let me move it up a little bit so you know what to pay attention to when you review this SQL. And now delete from claim table where fee charge is greater than 5,000. If you still remember, we have inserted one record where fee charged is more than 500. So right now we are going to delete from, there should be one row removed where fee charged greater to 500. And it says one row deleted. All right. Now, more select. Find from claim table which record has a fee charge of 200 and the provided number is 1. I think there's no column. It should return 0 because there's no fee charge equals to 200. But what is What if I change this to, I believe it's a 120? So in fact, I think that was a typo from my side. But anyway, select from claim where fee charged equals to 120 and provider ID equals to 1. Run this, and it returns, yes, it returns this row. So this question asks you how to use the logical operator of AND. And the next question is asking a similar question. It asks you for records have a fee charged less than or equals to 200, but greater than or equals to 100. Remember, these two criteria has to be met at the same time, which means we should use the AND operator. So it will be select star from claim where fee charged greater or equal to 200 and fee charged, less than or equal to 200, greater than or equal to 100. I believe there should be 2 rows returned. Both of them are like between 100 and 200. Now, if the question is between 120 and 200, how many should be returning? Because of the equal sign, it's still fee charge equals to 120 is still selected, right? So question 12, number 11, find from provider table of records belonging to provider Maria and the Bill. What we are going to do is we are going to select star from provider. Now, when each provider can have only one name, right? So a provider cannot be called Maria and Bill at the same time. So apparently this question is asking you to find providers, either the name is Maria or the name is Bill. Because of this, the where clause will be provider name equals to Maria. It can only be one at a time. Or Bill, right? And remember to put single quote around characters. Let's run this, and we will see both Maria and Bill. Question number 12. Find out what fee charge will be after the 20% increase. What is a 20% increase? It means your time fee charged with 1.2, right? So you are going to select fee charged times 1.2. The new value should be called new fee charged. This is a table alias. Table alias that we need to apply. So it will be as from claim. So when we run this, we will see all the new fee charged. But the problem comes in that you do not know which fee charge belongs to which provider or patient. So for a question like this, or in real world, when you type in, select something, a value, a numerical value, usually, I would say 99% of time, you need to put some labels, which means the descriptive columns in the same table so that people know what you are referring to. In this case, you will put a provider ID and the patient ID so that whoever checking your SQL result knows which one it belongs to, which patient ID and which provider it belongs to. That is how you are supposed to write it. Question number 13, find out all providers whose names start with B. What does this tell you? It means you have to find the names starting with a B, followed by an unknown number of characters. And that brings up to the like clause. Select star from provider where provider name like b%, and we have to sort it by association ID descending. So it's order by association ID descending. Semicolon. We'll start with B. It's a bill, right? And because we have only one row, so order by is not applicable here. But if you have more than one row, then it should the order by should be applied, and you can see it's ordered. Question number 14, find out all providers whose name contains E. This is similar. Just that containing E means it starts with an unknown character, unknown number of characters, followed by E, then followed by an unknown number of characters. So in this case, it will be started by like %E%, then ordered by provider name. All right, set star. And we have this E here. Question number 15, find out all provided numbers in the claim table, each showing only once. What does that mean? It means you need to select distinct, as simple as that. Provider ID from claims. And if you remember, we have column provider ID 1 showing up twice, right? If I'm going to select without a provider, without distinct, and let me run both at the same time, so you can see the difference. One shows up twice, and here we are only select once. So now, find out all associations whose association name contain D and T, regardless of case. So find out all association means select star from provider association where association name contains dent. It will be like %DNT%, but it says regardless of case, which means we need to convert both sides either to lower or upper. Let's use lower here. And don't forget semicolon. And we have all those DNT and DNT. In this particular case, DNT has the same pattern, but if we talk about like C, for the character of C, association I101 only have capital C, and the association 102 only have lowercase c. So if we put a C here, is that SQL still going to give us both, for both the uppercase and lowercase? The answer is yes. It returns both uppercase C and lowercase c. Let's put this back to that. And question number 17, find out all claims whose fee charge is lower than the average fee charged. And this apparently, when you see like average or total or minimum or maximum or count, it requires aggregation function. So there are two steps that we need to apply. First step is to get the average the fee charged, which will be select AVG fee charged from claim. And the second step will be select star from claim, where fee charged less than whatever value we can get from here. Now, if I run this first step, it will be 96.96 or 96.667, right? So if I run this, it will return me one column, one row. Now, we mentioned how we can, instead of typing a value, using a subquery. So this is how we are going to do it. We're going to copy this over this query, place it into a parenthesis, and use the subquery in the main query. Let's see whether the result is still the same. And the answer is yes. The result is still the same. Okay, now question number 18 and 19 is use a different approach for question 10 and 11. Let's go back to 10. What is it? It says find claim table which record has the charge less than or equal to 200, but greater than or equals to 100. For this question, we will be able to use between and end. So it will be fee charged between 200 and 100. Now, do you see any question with this statement? If you haven't seen it, if you haven't seen the issue, let's run this. No data found, but we did have data returned before, right? What is the reason? The reason is the lower bound is greater than the upper bound. So we need to change this, revert it to between 100 and 200. This will bring us the right number. Question number 11. Question number 11 is select from provider whose name is Maria or Bill. Okay, and in this case, we can use a in clause. Remember, for in clause, each separate value has to be enclosed by a quote. And each value is separated from others using comma. No and, no or inside this parenthesis. And this is another common mistake I see students making. They put a series of values, Maria, Bill, whatever, and then put an or inside, which makes it wrong. So this is the result for number 11, for number 19. And finally, we're going to drop all the tables. Let's start with provider association. Remember, it's drop tables, no star, no column name. Provider, dropped. And patient. And for patient, remember to drop this 2018. And also drop claim table. Drop all these 5 tables. And this completes our data lifecycle. We create it, we insert it, we do run some select and update, and finally we drop the table, delete the data, and drop the table. So much is our data lifecycle, and that wraps up our midterm project. In the midterm project, we actually go through, in the whole midterm, we actually go through the whole CREOD lifecycle: create, read, update, and delete. In the second half, we're going to go deeper into select. There are more information that we can achieve. We can retrieve from tables by using different variations of a SQL select statement. And so we will start this in next lecture, and I will see you there. In this lecture, we're going to talk about group by. So what is group by? We have already learned aggregation functions, sum, average, minimum, maximum, count. They all describe some statistic characteristics of a data set, like a sum or total or average or minimum. The need is always that we need to divide a table into smaller groups for research. For example, in a course grade table, you may want to check the average grade of one course versus average grade in another course, instead of just checking the average grade for all off-school, all course. Similarly, for weather data, in addition to knowing the national average is 50 degrees, you may also want to know what's the average weather, what's the average temperature in New York City, and what's the average temperature in Miami. If the national average is 50, but the New York City's temperature is 10 and Miami is 90, then the average 50 really doesn't help you much unless you know the local weather. Similarly, stock price may have different patterns in different sectors, and so on and so forth. There are many examples of that. And group by is designed to serve this purpose. So let's say we have a bunch of tables, data rows here, marked with red, blue, green. If I want to get a certain characteristics of a certain type of color, for example, I want to see the average across green rows and across blue rows and across red rows. So there will be red, blue, green. And what I need to do is I need to specify I'm grouping those tables, these rows, by color. In this case, I will put all those green rows together and calculate their group by, their average or total. I will also put blue rows together and red rows together and calculate their average. And the average will be per color. Either it's a green or it's a blue or a red. To be more specific and writing this in SQL, this is the group by syntax. We should put the group by keyword after the from clause. And we will put the group by columns, which is the attributes we use to characteristic data, group them by them, like color or city in our weather example. Then we also need to provide the aggregations that we want to perform on a group by data set. So it will be select group by columns and aggregation functions from some table, and then we specify the group by keyword followed by the group by columns. The order in group by does not matter. The order in select will provide you with whatever is displayed. And here, the aggregated column even come before the group by columns. But one thing to note is that select column must either be a group by column or an aggregated column. And we will discuss why very soon. So for the group by example, is a select student sum actual tuition from registration and group by student name. What does this do? It will group different rows in the registration table and map them to student name by student name. Within the same student name, we will calculate the sum of total tuition. For example, Luke Skywalker have 2 courses registered. Each of that have the actual tuition. One is 180 and 100. Then the sum of this tuition, actual tuition is 280. For another student, Leia Skywalker, she also has 2 rows, and the actual tuition for each row is 200 and 500, and the sum of this student is 700. So this is how you calculate, how you do the group by. Group by is by student name, and how you do the aggregation, which is by sum. We mentioned all columns in select must either be in group by or be in aggregation. That's because non-aggregation columns that are not in group by are returned as repeating groups, which won't be first normal form compliant. So SQL does not allow selecting groups directly without group by. We will use an example to explain this. But here we have the select student name, course name from registration, group by student name. And course name is not in group by. So if you do the select here, you will see that for each student name, there are multiple course names. And if you are putting this into one single statement, into one single table, it will result in repeating groups for each student name, which is a one group by. So this is not a first normal form compliant. Because of this, every select statement, every select columns must be either group by or aggregation. Now, if the student only have one course each, then it is possible that there may not be repeating groups based on data. But it will be all rely on your data. What does data look like? So SQL choose to enforce one first normal form by default. It will not allow you anything like this to happen, just to make sure every select will generate one first normal form compliant table. So this is the select with the aggregation. Aggregations do not need to be in group by, because these functions will only return one value per group. Thus, it's the first normal form compliant. So in this slide, you see the student name, you see the sum. These two are whatever selected by group by. Remember, each value in the group by column will return one row. As we show before here, each group by value will return one row, another row, right? So in this case, each student name returns one student name plus his or her sum. This is the meaning of group by, and this is why you can only have group by columns and aggregation functions in the select class. You can also group by multiple columns. For example, you can also group by student name and course name. In this case, we still need to make sure all select columns are either in group by columns or is a aggregation function. And in this case, because we are selecting student name and course name, and because of the nature of our data, student name and the course name happens to be equivalent of our primary key. So when group by is on a primary key or a candidate key, it will be the same as a normal select without group by. But this is basically is for your convenience. When you want to calculate aggregation, do not assume the data will provide you with any convenience. If you need to calculate average or sum or any of the aggregations, always use group by. Group by can also be combined with order by. Basically, the result set of group by is a series of rows. Each of the group by column value returns one row. So you can still be ordered by the columns in this result set. But because order by only sees the result of the group by, not the data result in the detailed data set, order by can only order the columns in the group by or aggregation functions. It cannot order by the columns in the original data set if the columns are not selected in the result set. So this is the simplified group by syntax. You will select group by columns and aggregated columns from some table. You will group by the group by columns, and you can order by the subset of columns in select clause. You cannot select columns that is in the original table, but not in a select clause. And of course, once you see a select from, you will have a question whether we are going to have a where clause or not. And we will cover this in our next lecture. But before that, let's use Oracle Live SQL to run some sample data, sample SQL to enhance our learning today. So this is the first one. We will run this query, which is in our class slide. It shows you the student name, the actual tuition, the sum of actual tuition from registration, group by student name. Now, the second one is you can group by multiple column. In this case, like we said, it's actually returning each and every row because this student name and course name combination happens to be equivalent to the primary key, which is the student ID and course ID, and thus it's a candidate key. But what will happen if we remove course name from here? Then course name is not in group by, but it is in select by. It tells us course name is not a group by expression. It has to be in group by, or it has to be aggregation. And finally, let's see the order by clause, where you can order the result by course name. And if you remember, I believe course ID is also in the registration table. What if we try to order by course ID? We get an error because it's not in group by and it's not in the aggregation function. However, if you want to group by order by aggregation function, that will work. All right. So much is for this group by introduction. In next lecture, we are going to talk about where and having, which is the applying filter conditions to the group by result. In this lecture, we are going to go through where and having in group by. And simply put, that means we are going to go through how to apply filtering conditions to group by. So when we go through this group by from a table exercise, naturally a question will come up. What if I want to apply certain filters to the group by process? There are two places where we can apply the filtering condition. First place is here on the detailed data set, on the original table. You can apply filters like if I want to see only certain course, only certain student, or some other patterns. And also, another place to apply filtering condition is here. In the at the end of group by, once you get the group by result, I want to see maybe only for the students whose total tuition is higher than 600. Or in the retail scenario, I will want to only see clients who has paid me $500 or more in total. This is my best customers, and I want to probably give them some discount or some coupons so that they will come to me again. So these are very legitimate questions, and we run into these questions every day. But there are some difference between these two filtering conditions. The filtering on the left are against the original table. So they will not see the aggregation value. You cannot apply a filter like where. You cannot apply a filter like on the total tuition here, because at this point, the total tuition hasn't been calculated yet, right? Whereas here, after aggregation, you do have the aggregation functions results, but you don't have all the details. You only have the group by columns and the aggregation functions. If some column in the original data set is not selected in group by, you will not see those in the aggregated function. So in order to distinguish between these two different kind of conditioning, group by introduced two levels of filtering. One is the original where, same as before. Another is a having. Having is a condition that only applies to the aggregated data set or the data set after group by. So I'll give an example of this. If we have a having condition of sum actual tuition greater to 600, it only applies after this student and the sum calculation is done, not here. Oops, I need to clean this up and redraw. Having is not applied here. Instead, it's applied here and here for whatever has been selected. So in this case, because this 280 is less than 600, it got filtered out. And this 700 is good. Hopefully you make some sense out of all the weird drawings, but the idea is pretty clear. Having is applied on aggregation functions on the aggregated data set, and it cannot go inside these two columns because these two columns are not in the aggregation. Thus, having cannot see these two columns. Right, let's move to the next page. This is an example of having, which we will use in Oracle Live SQL very soon. Let's bring up Oracle Live SQL, and this is the student name, where student and the sum of actual tuition. Now, if you remember, we have two rows returned before without having. One is a sum of 200 something, which is less than 600, so it's filtered out. Now, what if I put where? Remember, where has to be after from. What is the error? It says group function is not allowed here, which means group function is not allowed in the where clause. Why? Because where is applied in a detailed data set at the time of a where application. This sum, this group function, has not been calculated yet, so it's not available, right? But what if I want to apply a where clause like a course name equals to introductory to the force? This is doable because course name is available at the time when you apply where to the detail table, to the original table, right? There's no data found because each single one is less than. Now let's do great to. This will return some data to show you what I mean. What if I want to put a course name filter to heading? The answer is not a group by expression because course name is not in select clause, so you cannot apply having when by the time DBMS executes having clause, it cannot see this course name. That's why you get this error message saying it's not a group by expression, right? So much is this having examples. And let's go give a formal definition of having. Having clause, in order to apply a having clause, you need to write the keyword having after the group by clause, then followed by the filtering conditions. Conditions must be applied to the aggregated data set, and only data in the aggregated data set should be used. That means it's either an aggregation function or a group by column. And that's how it looks like. Having is after group by. and there has to be aggregation, some data in the aggregated data set. And having versus where is applied on the original data set. It cannot operate on aggregated data set, which means it has not access to the aggregation functions. You cannot have a where sum something or where average something. Having is applied on the aggregated data set on the other hand. So it cannot see the columns that is not in the aggregated data set, even though the columns may be in the original data table. And for those in the group by column, you can actually use both where and having. In this case, you should use where whenever possible. For example, you can filter on the student name either in where clause or in having clause because it exists in both the original table and in the group by column. But we always want to filter before any processing. That's why we always try to put the filters into where clause as early as possible. Having finished the having clause, we are already done with all the group by statements, all the group by functionalities in the select statement. And the execution order of group by is done in 4 steps. It first starts from the from where clause and continued with select and group by, then having and order by. So here is an example. When you write the select statement, it will always be select something from a table where with some Boolean expression and group by columns, then apply having and order by. What would you do here is DBMS will start with the from where clause. It will pull the data first, pull the data set first. Then it will group by the columns and calculate the aggregation columns. Then it will apply having condition to the aggregated functions, aggregated data set, and then it will sort it, sort the data from following the group by order, order by order. For example, in this select, we have a from registration where registration date greater to something, October 1st, 2019. At step 1, DBMS can find the registration date, this column in table. So this filter can be properly applied. Then we will group by student name and sum of actual tuition. At step 3, DBMS can only see student name and sum from the group by data set because at step 2, group by already formed its own aggregated data set. So at steps 3 and 4, having and order can only apply to the student name and the sum columns. It cannot go into the registration date anymore. And on the other hand, because where clause is applied in the first step, at that time, sum has not been calculated yet. Sum which is calculated in step 2. So you cannot put sum in the where clause. So a quick summary, where is on detailed or original data table level and can use all source columns, but not the aggregated columns. Having is on aggregation level and can use all select columns, but cannot use other columns in the original table. All right, we are done with the group by, and we'll go into data set operation in our next lecture. I'll see you there. In this lecture, we are going to talk about data set operation. So far, all our works has been focused on single table, but apparently there are more to in SQL than just working on one table each time. And you need to do a lot of data blending, which means mixing data from 2 tables or even more together. There are 2 types of data blending. One is called vertical, another is horizontal. Vertical blending, also called as set operations, means simply combine rows from 2 tables together. Like in this example, table 1, table 2, you are simply mixing their rows row by row. And horizontal blending, on the other hand, mix columns together. So this table plus this table, you will get the same amount of rows, but it's a mix of two sets of columns. We will talk about this horizontal blending, which also is called join, in the later session, actually in section 11. But for this one, this particular session 10, we are going to talk about set operation. First set operation we're talking about is union. We are going to link two statements, two select statements with union keyword, which will return us the rows in either of the data sets. For example, student registered in 2018 or student registered in 2019. If a student registered in 2018 but not in 19, or the other way around, if a student registered in 2019 but not in 2018, both students should be selected from this union. What if a student exists in both 2018 and 2019? In that case, we should see him or her only once. This is the union clause. And the requirement of union is that the column list from both select must be the same. We talked about union returns only distinct value, like one student registered in both select 2018 and 2019 will be only returned once. But sometimes you may want to see all occurrences in, like you want to see the student shows up twice. This can be helpful if you are doing a count. To show all occurrences, use union all. It has the same structure, just a different keyword, adding an all after union. So it will still be the union all between two select statements, and these two select statements must have the same column list. So we are, for union and union all, both are just merging data together. There's also intersect and minus. Intersect means data in both of the data sets. For example, student registered in both 2018 and 2019. If a student registers only in 2018 or only in 2019, he or she should not be included. This is what the intersect means. And again, column list must be the same, otherwise we won't be able to properly intersect. And also there's also a minus, which means data in one data set, but not in the other. For example, student registered in 2019, but not in 2018, they will be selecting from 2019 table minus student minus the select from the 2018 table. And we can explain this with a chart. If each circle is a data set, and the overlapping part means the data that exists in both cases, that means we union is combine them together. Is to the left part, the whole area of both cycles, both circles. Intersect is the overlapping part of the two circles, and minus is just one. It's just one circle minus the overlapping side. Let's try to show this in Oracle Live SQL. So this is Oracle Live SQL, and we are going to use an example to explain what do we mean on all these union and intersect and the minus. We're going to create two tables and insert some of the data here. Two tables with a different structure, but in the first table, we have a 1 and 1 and 2 and 3. In the second table, we have 3 and 4. But ID, there are two ID equals to 1. There are two ID equals to 1. And there's an overlapping of 3. So if we do a union, what will happen? And we're only selecting column 1 and 2, column 1 and 2, column 1 and 2. So you will see that ID equals to 1 will only show up once, ID equals 2 show up once, ID equals 3 show up once, and ID equals 4 show up once. Basically, it's getting all these 6 occurrences, but only display the unique result. What if we do a union all? Because union all will return all combinations. So all 6 rows will show up. You see 2 ID equals to 1 here and 2 ID equals to 3 here. How about intersect? Intersect will show the result that shows up in both places, which means it's just ID equal to 3, right? So let's run this intersect. And it shows only ID equals to 3. And the last but not least, minus. Minus means everything in subset 1, but not in subset, excluding everything that's in subset 2. So we are going to do this minus. And it's 1 and 2, and 3 is not in subset 2, right? So this is what we mean by all these set operations. And starting next lecture, we're going to talk about join, and I will see you there. In this lecture, we're going to talk about table joining. Table joining is a very important feature of SQL statement. We already talked about data blending, and we talked about vertical blending, meaning putting 2 tables together row by row. What we are going to talk about right now is a horizontal blending, aka join. That means place 2 tables side by side, having the same amount of rows, but add their columns together. List the columns side by side. So why do we do a join? Because sometimes we need to look up a value from another table. For example, in the course table, we have course name and instructor name. But what if I want to see which instructor affiliation is associated with each course? Instructor affiliation is only available in the instructor table. In this case, because both course table and the instructor table has a column called instructor name, we should be able to search the value by matching the instructors. So for example, the course introduction to the force, we can look at the instructor name, Obi-Wan Kenobi, find the same instructor name in the instructor table and identify the affiliation, which is Jedi. Thus, we can confirm course name is associated with the instructor affiliation Jedi. And this is how we will do it. But in DBMS, it's the same way as what we have been doing for all the select statements. We're going to do it row by row for both tables. So for each row in one table, for example, course table here, we will go over each row in another table, which is instructor here, to find the rows with matching values. For example, the first row of course table is an introduction to the force. For this row, we will go through instructor table, and we run into Obi-Wan Kenobi first, which matches the instructor name. So we have a match here, instruction to the force matches instructor affiliation. The second row, however, in instructor is Darth Sidious. And Darth Sidious instructor does not match Obi-Wan Kenobi. So we have a no match for this row-to-row match. Then we completed all rows in the instructor table. We go to the second row of a course table. And then we go to the third. Like for example, in the third row, throat choking, 101, Darth Sidious. When we match for the first row in instructor table, Obi-Wan Kenobi does not match Darth Sidious. Thus it's a no match. And the second row in instructor table, the instructor name is Darth Sidious. It matches with the instructor name in the course table. So throat choking 101 matches with the instructor affiliation, this, that's a match. So by going through this row by row, the result is a list of identical instructor names matching with each other. The end result is equivalent of applying a where clause of the following: instructor.instructor name equals to course table.instructor name. And this is how we are going to write a join. We're going to link two tables by matching common columns. We will list two or more table names in the from clause separated by comma. And this separated by comma is important because a lot of students, when they first write join, they forgot about it. Then the second step is add join condition to the where clause. So officially, the SQL will be select instructor affiliation from instructor comma course, where instructor.instructor name equals to course.instructor name. And there is a problem with though. You can see that we have instructor name in both tables. That's why we need to put a table name in front to fully qualify name. If I do not put the table name in front, we will run into an error message. For other columns, like instructor affiliation, it only shows up in the instructor table. So there's no need to put the instructor dot qualifier in front of it. However, it's recommended that you add this qualifier in front of every column to make sure your readers, your users, understand where this comes from. This is especially helpful when you have multiple tables joining with each other. The other thing will come up is, as you are writing all the qualifiers, this can be really long. Thinking about the names like the instructor affiliation, course, this can be extremely long. So there's a way of simplifying this SQL statement by adding a table alias. So you will add an alias after the table name and use this alias throughout the SQL query. For example, in here, we put an I after instructor. And then wherever we used to use instructor, we use an I dot as a qualifier. Similarly, we have a course, C. We use a C can represent course. Thus, we can use a C dot as a qualifier instead of course dot as a qualifier. Now, how to naming the alias is a personal preference. I personally like to use the first letter of the table name or first two letters to identify the table. And some people like to simply use A, B, C, or some people use A1, A2, A3. All these are perfectly fine. It's your preference. Just make sure that you and your users can understand it easily. So much is for join. Let's do some Oracle Live SQL to help us better understand the joining context. So this is our Oracle Live SQL session. First, let me bring up the join statement. This is the one that we have a select instructor affiliation from instructor and course, and where instructor name equals to course name instructor name. So let's run this query. And it brings us instructor affiliation of the five courses that we have. Now, if I add course name, we're going to have course and instructor affiliations row by row. Now, we also talked about adding qualifiers in front. We can put the instructor qualifier in front of instructor affiliation, and we can put the course qualifier in front of a course name. What if I put the instructor name without qualifier? What will happen? you will get an error message saying column ambiguously defined, because there are two instructor names in two different tables. And you have to add, for example, course dot instructor name. Of course, because we have this equal sign, so these two columns are actually identical. You can either add either table, both will be fine. So let's run that and it will come up. And now, what if I add alias as a C and I? So we will replace all the C course table name with C and all instructor table name with I. Now let's run, and we get the same result. Okay, so much is for joining the table. In next lecture, we are going to talk about another form of writing join statement, which will be much more easier to understand. I'll see you in the next lecture. In this lecture, we're going to talk about joining using the join keyword. So we already talked about using joining condition in the where clause. But the problem with this approach is that we also put filtering conditions in the where clause. So if I have the same joining statement as we talked about in last lecture, and I want to add a filter where course name contains the word force in it, that will be the statement you will look at. Select something from something where instructor name equals to instructor name and course name like %force%. Now we only have two tables and one join condition and one filtering condition. Imagine you have 12 tables joining with each other and 13 filtering conditions. And this happens a lot in the real world. In that case, you will have 25 separate courses in the where portion of the select. It will be mixed with each other, and it's hard to identify where is the joining condition, which table joins which one, and what's the filtering condition. To resolve this issue, SQL introduced the join on keyword to separate the join from filtering conditions. What it does is it removes the joining condition from where clause into this specific join on keyword. So the same old filter, same old joining from instructor course where instructor name equals to instructor name becomes from instructor I join course C, where both tables shows up one in front, another in join, and the join condition will be on the on clause, where it says on I.instructor underscore name equals to C.instructor underscore name. And if you have where clause, the where clause will solely contain the filtering condition. They will be no longer mixed with the joining condition. So let's see the official syntax. You should put one table in the front clause, only one, and together with its alias. Then you put the keyword join, J-O-I-N, following the front clause, followed by a table name, another table name. Again, only one table. Then you followed by the on keyword, followed by the joining condition. If you have more tables, then you will add more join and add more on. Each table joining as one join and one on. So this is the official join syntax. And next, we will use some SQL example in Oracle Live SQL to show you how to write the proper join. So this is the SQL we just used. And if you still remember, this is the join course. This is the join statement we just wrote. How to convert this into a join table, a table joining. So instead of comma, let's write a J-O-I-N. Remember, once you use join, there's only one table in each clause. Do not use comma. Then this join condition should be in the on clause right after the join clause. And then everything used to belong to the where clause still belongs to the where clause, which is the filtering condition. Now let's run both together and compare their results side by side. You will see that they are actually returning the same result. So much is for join. Because of this join advantage of this joining, it's simpler and it's easier to understand. Most modern DBMS are supporting this, and this is the syntax we are going to use. We will not use a joining where clause. We will always use a joining where join clause. And as we go, introducing more tables and more joining conditions, you will see how adventurous it is comparing to the where clause. Okay, in next lecture, that's exactly what we are going to do. We're going to introduce multi-table join, and I'll see you there. In this lecture, we're going to talk about multi-table join. So we already show you how to join two tables together. What if I have more tables than two? So if I have 3 tables joining here and centered around one table, it's called a star join. Of course, this doesn't look like a star, but imagine there are 5 tables joining into the same table in the center. Then they will look like a star, right? That's why this is called star join. Star join means join from one table to multiple tables. For example, here, we have this registration R and joining both student and the course. In this case, we are going to write the registration in the front, and then from this R, we will write one join at a time. Each join is a join table alias on join condition, followed by another join, another complete join table name, table alias, on join condition. And if you have 5 tables, you will repeat this join on 5 times. You have 12 tables, you repeat it 12 times. That's what we call star join. Another possible scenario is called chain join, where we join from one table to another, and then this second table join to the third table. What we are going to do is we are going to select from registration table, join course, then the course table, C, will then join an instructor table. In this case, we're still starting from the first table, write the complete join, the join clause, where you have a join table name, table alias, on join condition. Then followed by another join clause, where you have a join table name, table alias, on the condition. So essentially, this chain join follow the same way as in star join, where you have one table called from using in the from, and each table added is in another join with an on clause of join condition. One thing to note is that in chain join, you need to avoid looping join. For example, here, this table is joined with table 1 and table 2. Then both table 1 and table 2 joins with table 3. What's the problem with this? The problem is, in real world, if such a loop join happens, usually it's because table 1 and table 2 are coming from 2 different sources. And usually there will be data inconsistency between these 2 data sources. And when you do a loop join, the data inconsistency will cause you to lose data. So even though your data source may have different data or data inconsistency, you shouldn't do that. You shouldn't try to overcome that by doing a looping join. You should always do either one way of join or the other way of join, but not both. Okay, so much for looping join. we talked about chain join and the star join. If we mix them together, oops, let me clear my drawings, and you can see here we have a looping join. We have a chain join here, chain join here, chain join here, and another chain join here. The only difference, and if you are ignoring these chains, each chain is actually a star join of itself, joining the fact table. So this is actually the most common usage of SQL query, because this looks like a snowflake where the star has more stars. We usually call it a snowflake join. You may be wondering, why would you do auto join, especially when you think about the auto normalization we do? Didn't we break a big table using normalization? Why do we want to join the tables back again? The reason is there are two types of data usage. One is the operational or transactional, where you are writing some single entries to the table. You want it to be fast. You want it to be simple. But meanwhile, you want to maintain integrity when you add or update new data. This requires, normalization to avoid complexity and redundancy. But once you write all the data into the table, you want to read it out for analysis. This is the analytical side of data operation. You want to read through the historical statistics involving a variety of information. In this case, you need to join data from multiple places to perform complex transformation calculation. Now, because analytical needs are usually more time tolerant, it can run slower, whereas the operational side requires faster access. So when you design data model, you tend to emphasize more on the fast side. That's why you want to always break the data into smaller pieces, break the table into smaller pieces to make sure it's fast and it's simple. And then when you need to read the data, you can use join. It's slower, but it will serve the need. So this is a join versus normalization, and hopefully this will explain a little bit on why we need join. Now let's run some SQL in Oracle Live SQL to show you how this join works. So first, we have a star join where the registration table will join the student table and the course table. Both joins come from registration table. And that's how that looks. We have a course, we have a student. This shows us which student registered inside each course. We can also have a chain join where registration R joins course C, then course C joins instructor. This will provide us with a list of registered course name and their instructor affiliation. And finally, we have our favorite topic, the snowflake join, where you will have registration joining student and the registration joining course. And on this course branch, we have a chain join of course joining instructor. And this is what we are going to get for the student and the course name and instructor affiliation. All right, so much is for this lecture. We'll see you in next one. In this lecture, we are going to go through select statements with join and group by. So right now with join and group by, we have learned everything of a select statement. This is the full syntax of a select statement. You will select from a qualified column list, from one table, join another table on a join condition, possibly repeating the join on multiple times. And then we have the where clause to filter on the detail level. Then the from join where forms a detailed data set. And from there, we do a group by. After the group by, we have an aggregated data set where we will do a having on top of the aggregated data set and order by this aggregated data set. The execution order of a select statement is exactly like what I just described. We will start from join where, which creates the detailed data set. Group by on top of this detailed data set will form an aggregated data set over the join tables. Then we use having to filter on aggregated data set and use order by to sort the result. Why this is important? Because this is going to be the same way, same order that you write a complex select statement. There's a lot of questions from students then how to write a select statement. A lot of question was, I see the question, I know I need to pick from this table, but I do not know how to put all these questions into a select statement. And this is what we are going to talk about. So we have these 4 steps from join where, which forms the basic fundamental detailed data set. Group by forms the aggregated data sets, having filter on the aggregated data set, and order by sort the end result. And that's exactly how to write a select statement. First of all, we need to find the tables involved. For each column required, the question will always ask you to select, to find, to identify some columns. We need to find for each column required the source table of the column. Once you have all the tables, the source table, once you have the source tables, you will start from a from. You will usually find the table with most join keys in the from clause. Usually it's also the table with lowest level of detail. You have one table in the from clause, then we do a from, join. You will add other table names in the join clause, then add join key in the on clause. For each new table, we add an independent join on clause. So we have a from, join on, etc. Eventually, this from join will form the big data set. Then we will add a where condition. And this 1A, 1, 2, or 1B, 1C, 1D forms the detailed data set. From there, we apply aggregation by add, group by for each. In the question, you always ask for each something, like for each student, give me the total tuition. For each course, give me the total registration. This for each is a group by. Each for each is a group by. Once you have a group by, you have a group by columns, you add the same column to select. And then you add the required aggregation functions to select. After that, you can add having and order by. This is how you write a select statement. Now let's use Oracle Oracle Live SQL as an example. So let's say we have this question: find the instructor affiliation for each course and identify the student count. How many columns do we have here? We have the instructor affiliation. We have the course, where we can just say course name. And we have a student count. So you need to count student ID. Apparently, student account is a count of student ID, and which will be from claim table. And we know that we have a course name in claim, but assuming there's no such table, that we need to go to course table for this information. And for instructor affiliation, apparently this is instructor table. All right. So claim table apparently have the most lowest level of details. So let's do from claim. Then we do join course, You can of course join instructor, but there's really nothing related between claim and instructor. So we need to join from claim to course. I just put CR on C dot course ID equals to CR dot course ID. Then from course, we will join instructor I on C dot instructor name equals to I dot instruct name. And if we have any where clause required, we should have put it here. For example, for course, where C course name like and force. This is just an example. Let's just say that. So this is the detailed data set. If you run a select star right now, you will see that it's actually giving us, oops. Oh, I forgot to create a table. Okay, now I already created the original table. Let's try. If you run the select star, so if I think I accidentally typed in claim as a instead of registration. Now that it's corrected, if you run this with a select star, you will see every column from every table and all the rows of the join result. This is the detailed data set, right? But of course, we are not only interested in this detailed data set, we're also interested in, for each course, so this is a group by. CR.course name. And once you have the CR cross course name in the group by, we do a select. And now count. This should be registration table. This is the group by. So now let's run this, and we will have a count. Of course, you can add having and order by if you ever want it. But basically, that's the way we write a SQL statement. You will start from. You will start by identifying the tables involved and their relationship. Start from writing the from, add a table at a time, which is a join and on, applying where. Thus, you get the detailed data set. Then on top of that, you add select and group by to get the aggregated data set. On top of the aggregated data set, you apply having, and you apply order by. No matter how many SQL you have, how many tables you have, this is the way you should write a complex SQL statement. All right, so much for writing a SQL statement. I will see you in the next lecture. In this lecture, we are going to talk about advanced joining. We are going to talk about the columns used in joining. So far, within this course, all joins are performed on one column with same names from different tables. For example, when we join course and instructor, the join key on both tables are called instructor name. When we join course and the registration, the join key on both tables are called course ID. This actually makes sense because the definition of join is to match different entities on their common attribute. And if it's a common attribute, they should have the same name within two different tables. This is called natural join. SQL can also join tables or multiple columns or columns with different names. or both. And this is more common in real world. For example, joining on multiple columns. Here we have one table joining another. And in the join, in the on clause, we have matching column 1 equals to matching column 1, and the matching column 2 equals to matching column 2. If you have more columns in the join key, you can add more and, but the on still remain the same. And remember, this is the one key that when you pay attention to. For each on clause, there's only one on. Everything else, all the equals here are linked by AND operator. The other common scenario is SQL can match tables on columns with different names. We will follow the same syntax. From table 1, join table 2 on a join condition. The only difference here is in the join condition, the two column names can be different. Now, because the table names can be different, we do not necessarily need table qualifier. However, it is still a best practice to use table alias on all columns. Table name can be different just because of the description, how they were named, and they can still mean the same thing. For example, you can join student ID with another table's student number. These two may be the same, just that they are called differently due to historical reasons. Similarly, sometimes a course ID can be called course code or course session, and you can still join although they have different names. There's another scenario of joining on different names, which is what we will call self-join, meaning one table joining itself. And when it joins itself, it uses different keys within itself. When the table is referencing itself, for example, we have an employee table with an employee and a supervisor. Now, supervisor itself is also an employee. So supervisor also have a supervisor. If I want to find the supervisor of supervisors, what can I do? Apparently, I need to place this supervisor as if they were employee, and I will match these supervisors against our own employee table, employee column. So what I'm going to do here is to select something, select a supervisor from one employee table, join another employee table. And the employee table on the left is the employees table, is the employee entity, and the employee table on the right is the supervisor entity, where all employees in this right table are actually supervisors. So here we are matching the left table's supervisor against the right table's employee. In this example, Alice matches Alice, and the Bill through supervisor Alice joins to the supervisor of supervisor Rachel. That's how it works in self-join. So let's go to Oracle Live SQL and create some example. Let's create two tables first. Talking about joining on multiple tables, multiple columns, we have two tables, sample 1 and sample 2. In sample 1, we have 1, 1, 2, 2, 3, 3, and in sample 2, we have 1, 1, 2, 2, 2, 3, and 4, 4. Now, what if we join them on both ID 1 and ID 2? Creating the table, insert the data, and let's see. So 1, 1 matches 1, 1, 2, 2 matches 2, 2. This is one matching. This is another matching. And here, 2, 3, 3, 3, and 2, 3 doesn't match. 2, 2, and 2, 3 doesn't match. That's why this is not selected. And 4, 4 or 3, 3 has no matching in the other table. And that's the result of 1, 1, 1, 1, and 2, 2, 2, 2. That's a multi-column join. Let's also go through an example of self-join. Within self-join, let's create an employee table that we just showed in the PowerPoint. Employee and supervisor, and we insert Bill, Alice, Tom, Alice, and Alice, Rachel. Now, if we align employee table E, let's see, E.S and S.star, from one employee table, which provides the supervisor, matching supervisor tables employee, what is going to be showing. And you can see here, this is from the employee table, and this is the employee supervisor table. Bill supervisor is Alice. So as an employee, Alice supervisor is Rachel. If we remove this one and this one, then we have a matching between employee and the supervisor. That's Bill and Rachel and Tom and Rachel. So much is for self-join. All right, I will see you in next lecture. In this lecture, we are going to talk about join on key. So far, we have been talking about all the regular joins, either through the same table or column name, or through a different table or column name. The similarity is there's always this on clause where you define which column to match the other when you do the join, when you put two tables together. Now, what if we forget the on clause? It will become select star from course join instructor. Remember we talked about how join is performed. We will match each row in one table to each row in another table. This will be a mathematical product of this, or we call Cartesian product between two tables, where each row meets the other one. If the first table have m rows and the second table have n rows, the result will be m times n rows table, right? And if your m or n is big, you can result in a huge table. Because of this, modern DBMS usually don't allow this. They won't allow you to do a from course join without an on. However, you can still do it with where. If you put a from table, comma table, without the where clause, you can still result in a Cartesian product. That's another reason we always want to do a join, because we don't want you to accidentally write some Cartesian join and returning a million rows. But there's another scenario in which if you are joining on multiple columns, if you're supposed to join on multiple columns, but only join on one of them, so then neither side is unique. That will happen a partial cross join. For example, if the instructors join itself or affiliation, we know there are multiple affiliations, multiple Jedi and multiple Sith. Then for each Jedi, they will join with other Jedi. For each Sith, they will join in with all other Sith. This is still based on sum of condition, which means there's still a join between affiliations. So it's not a completely Cartesian join. That's why it's called partial cross join. This can be helpful if you want to find the matching to form a pair of Jedis or a pair of Sith. An example here, table 1 and table 2, both table 1 and table 2 have an ID 1 twice, but 2 only once. So when table 1 joins table 2, the 2 ones in table 1 will match with the 2 ones in table 2. The first one in table 1 will first join this one. Let me try to mark it so it looks easier. So the first one will try to join this first, this one first, then it will go through one, and this one more. Now let's change the color. And this is the second row of one, which is one more. It will join this one once. Then it will join this one more. That's when you have 4 rows, which is 2 times 2 equals to 4. This is a partial cross join. Because of this, we will usually require a join has to be on key. Otherwise, there will be duplicated value. The join key usually should be the primary key of one of the 2 key tables, or at least the candidate key. Otherwise, there will be duplicated values, and the duplicated values from 2 tables will cause a partial cross join. If the join key is the primary key of one table, it's called foreign key on the other table, because from the other table side, the key comes from a foreign table. So this is called foreign key. You can add certain column constraint or table constraint designated some columns to be foreign key. And once you add the foreign key constraint, all the values in this column must be coming from the other table. This is used to restrict the value in the foreign table to the foreign table. All values must be valid. Let's try do some joins using Oracle Live SQL. First, let's see what if I'm trying to join without the on. So now I'm having a select star from one table separated by comma and another table. Normally, I should have a where clause specifying a join, but right now I forgot about it. So I run it. You can see that for each and every course ID, 1, 2, 3, 4, 6, it matches one instructor. For another 1, 2, 3, 4, 5, 6 course ID, it matches another instructor, and so on and so forth for Yoda, for Dacidius. This is what we call cross join or a Cartesian join, Cartesian product join. Now, if you have a very justified reason to do this, you can specify cross join you will get the same result, 24 rows. So SQL specifically asks you to put a cross here if you really want to do a cross join. If you do not specify a cross, SQL would think you made a mistake forgetting the on and would not allow you to do that. This is the protection mechanism SQL placed in case you made a mistake, because there are rarely any opportunity that a cross join will happen. That's why SQL think it's easier to restrict you on the cross join side than allowing you to do that. But still, if you really want to do that, you have to specify, you have to explicitly put a cross there and tell in SQL you do want to do it. Okay, so much is for cross join. Okay, let's do some partial cross join. Let's create some table first. So this is the sample table that we created with 2 IDs. And the first column, 1, 1, 1, 1, right? Now, if I run all of them, and I join them on ID 1. What will happen? You can see that for 101, it joins twice. And for 102, it joins twice because there are another tables 1 and 1. Or from the other table side, this 1 and 101 joins the other two rows once, and this row 1 and 102 joins the other table twice, and thus forming a 2 by 2 equals to 4 rows table. So these are the partial cross join and the Cartesian product join. Remember, try to avoid it. Always join on key. Unless you have a very justified reason, you should always join on a primary key of one table. All right, so much is for join on key. I will see you in next lecture. In this lecture, we are going to talk about outer join. So let's review regular join. When we match course with instructor, we need to match instructor name by instructor name. If an instructor name does not appear in another table, there will be no match, and this will not show in the end result. For example, instructor with no course in course table will be ignored. Result is the common set between the two tables, which is called inner join. What if we want to see all instructors, even for those with no course? For example, we know Anakin Skywalker is in instructors list, but he doesn't teach any course. What if we still want to show him, and probably with null or 0 in the course name field? In order to do that, to preserve all data from a certain table during join, we use what we call outer join. So in this example, for the two tables, original table blue, and original green. If blue joins green, and only these 3 rows match, then this is inner join. Inner join only keep these 3 that we have common join key in the two tables. If we want to do a left outer join from this side, and keeping all in the blue rows in the blue table, and only the common ones in the green table, this is called left outer join, where we preserve all data from the left table. And if there's no data, it will be null. The opposite of left outer join is right outer join, where you keep everything in the right table, whereas the left table only kept the common tables and the common rows. And if there's no data in the left table, we will place null there. And combining left join and outer join, right join, we get a full outer join. Full outer join means preserve the data from both left table and the right table, right? So let's see an example. If we are selecting from instructor, left outer join course, the syntax will be from table 1, left outer join table 2. That's a left outer join. And all the rows in table 1 will be preserved. All the instructors will showing up in the end table, in the end result. Whereas from only the common tables, common rows from course, where instructor name exists in instructor, will show up for course. We can also simplify this join keyword as left join, which is okay too. Now, to note, this left and right is based on from join. If you move this up, instructor on the left and the course on the right, the order in the on clause does not matter. Repeat, left and right is based on the from and join clause. The order in the on clause doesn't matter. So once we do this, select from instructor, outer join, left outer join the course. Data from left table will be preserved. All instructors will show up. If there's no matching data from the right table, this course name will show now. This comes from right table, right? If there's no matching instructor in the instructor table, this course will show, if there's no matching course name for the instructor, this field will show now. There are three types of auto joins, and left, right, and full. And when you do this, either left or right, you just or full, you simply replace the word left with right or full from the format which is discussed before. You just replace this with right or full in order to get your type of auto join. One thing to note is left auto join and right auto join are actually reversible. T1 left join T2 equals to T2 right join T1, right? So these are the things that we want to pay attention to. Now let's look at some examples from Live SQL. So let's first compare the result of this. First, let's get whatever we show in the PowerPoint. Now, note here is a left auto join, left from instructor to course. So every data from instructor should remain, and only the common data in course will be remaining. And if the instructor does not have a course, then this course name from right table will show as now. And the order is defined by from and the join. Whatever order in the select statement, in the select course, or in the on clause does not matter, right? You can see this here, course is on the left, here course is on the left, but doesn't matter. The left auto join is based on the from clause and join clause, so the left table is instructor. Let's run it. And you can see Anakin Skywalker as an instructor doesn't have any course. So it shows as now. Now let's perform another left auto join, but this time it's from course to instructor. What will happen? Every course will show up, and only those instructors with courses will show up here. So Anakin Skywalker should not show up anymore, but instead, some courses that without instructor defined in this table will have a now instructor name. For example, there's moisture farming for dummies. There's no Jedi or Sith teaching, so there's no instructor belonging to here. That's the other way of joining. Now, we also talked about left auto join and the right auto join. If you are, in this example, we are left auto join from instructor to course, which means if we are right auto join from course to instructor, we should see the same thing, right? So from here is a course, right auto join instructor. And these two should be equivalent. Let's run both. And the answer is yes. They are the same. All right. So much is for auto join. I will see you in next lecture. In this lecture, we're going to talk about how to filter from another table. So we already have done this before in the in subquery. How do we use the result of a query in another query's in clause? we will put the first query in parentheses and place it in the second query. So here we have this select from course where instructor name in, select instructors from instructors affiliation equals to Jedi. That basically gives us all the courses taught by Jedi affiliated instructors, right? So how do you associate? Now that we have learned join, and we can think from a way of how two tables are interacting with each other. How do you associate data from one table to another? When you associate data from one table to another, you always need to do it via a common column. So here, this one is instructor. Instructor here from a course, and the instructor here from instructor. And we match them by using in select. And that's exactly what join does too, which means for in subquery, we can always convert it into a join. And this is what we do here. And if we compare this one against the other one, this is the course instructor name. And we keep it here in the on clause. And this is the instructor name. And we put it here also as another condition of the in clause. And the where condition now becomes a part of the mainstream, the main query where. So this is how we associate two tables, either by joining with the on clause. You associate two tables through on clause, or you join them by using in select subquery, where you put these two associations before and after in. And there are three ways actually to filter data using another table's data. The first method is use the where in subquery clause, which we covered just now. The second method is join two tables together and filter on the join data set. And the third method is use where exists. Exists, check the result of a correlated subquery. Subquery with a correlation condition between main query and subquery. Still, it's the same that you are using a condition to associate two tables. It will be same as the on clause in join between the two related tables. So here, this is how exists is defined. You will do a where exists select star from one table. How do you associate these two tables together? You will associate them by defining a where clause inside the exists query, where one table's column equals to another. So there are, as you can see, these are matching records. There are matching columns and patterns that you can use to convert among these three. It's the same process in execution, where the outside query or the join slab table will be executed row by row. For each row in the outside query or the join table, DBMS will go through the inner query or join table row by row, matching outside query's current row and apply where clause. So there are similarities in execution. There are matching values in another table. If a select contains information from both tables, you have to use join, because when you do select, you cannot select from subquery, right? So join is the only way when you need information from both tables. But if you are only select from one main table, you can use either in or exist or join. In most cases, if you use in or exist, you can also use join. How about performance? Which one should you use? Which one should you use is based on logic and the performance. So logic, if logic is identical, performance is the only thing you need to consider. But the reason that we have these three listed all together is because there's really no significant difference between each of them. The performance really depends on your DBMS setup. So you have to use trial and error to determine which one to use. Let's use an example to explain. So we have Oracle Live SQL. We have this select. Let me make it more readable by adding indents. So it's a select from course where instructor name in select instructor name from instructor. I can run this, no problem. If I want to join, so how do we transform this? We will still have a select from course. Now, we want to join on this, on the second tip. And then we already know it's associated through this instructor name column. So we will do on. Of course, we need to add C and I. And finally, we will put a where clause. Now that this where clause is applicable to the outside query, so you will put like I dot affiliation equals Jedi. So this is how we do it. We move the inner query into join, and we put the association, the column association, into the on clause as a join condition. If I run both at the same time, it's actually returning similar things, same rows, but it's also returning information from instructor table. That's what I mean by if you want to see the table, the information from both tables, you need to use join, because when you are using the subquery, the outside select will not see whatever is in the subquery. It only sees whatever is outside in the main query. Now, let's do a select exist. Similarly, we will do select from course where, this is where it different, exists. And again, we have a include everything in parentheses. That's a subquery. And you can already foresee that this select, without running that, you can foresee that this select will only return the course table columns, right? Now, for this exist, we want to select star from the same table. Add this where, which is the original condition. And let's add the association columns where it should be, if I put a C here and I here. Or you can use the table name if you want. But basically the association table, column association is the same. I should run all three at the same time. So that you can see, first, in and the select returning the same thing. And the second one returns both tables, right? So they are equivalent in execution. As SQL goes more complex, as you involve more tables and more where conditions, you may need to choose among in or exist or join. But like we said, you need to choose based on performance, and sometimes you need to try and error. There's no universal answer on which one you should choose. All right, so much for filtering from another table. I will see you in next lecture. In this lecture, we are going to talk about non-equi-join. Non-equi-join, as the name suggests, means when you join, you are not using the equal sign for the join condition. So you will associate two tables with non-equal operators, greater to or less than between and end. Non-equal join can be is applicable in many different scenarios. Most frequently scenario is in slow changing dimension, which means values change over time. For example, a coupon may have a effective date and the termination date. So if you want to check transaction whether you apply the coupon or not, you may want to use first of all, you need to join on a coupon ID, make sure the transaction is actually using this coupon. Then you want to confirm the transaction date is between the effective date and termination date. Similarly, you might also be using greater than or less than, depends on your scenario. We're not going to cover much about this because this is non-equal join, as we can see, is a scenario by scenario. But basically, when you see non-equal join, you analyze it the same way as we analyze normal join. Remember, it's always select from one table, row by row, pick one row at a time, and match it with every row in another table. And then here you apply the join condition the same way as you apply where clause. Both matching on coupon ID and matching on transaction date and the other two dates. This is how you handle non-equal join. If you have any questions, let me know. You can leave a message and let me know. Otherwise, we will go to the next lecture. In this lecture, we're going to introduce view. So we're already using subqueries in where clause. And basically, subqueries returns you a list of items of rows, a set of rows and columns, which is fundamentally a small table. Now, subqueries can also be used in the from join clause too, as a data set to be selected from. For example, in this SQL, we have a subquery select star from instructor where instructor affiliation equal to Jedi. Inside the parenthesis with the as Jedi instructor, this table alias. So you can do select instructor name from this table. And you can also run other SQL queries when you put this parenthesis and subquery inside the other SQL queries. You can put this in the from and you can put this in the join. Now, naturally, the question comes up, what if I want to use this in many different places? What if I want to reuse this subquery? SQL provides this functionality to define a view, to store a select statement, and make it easier to remember and use. It's also a way to reuse subquery. So you will do by starting with a create view keyword, followed by a view name, and optionally you can have a column list, defining which columns are in this view, followed by the as keyword, and then your subquery. Column list is used to define column names. You are not supposed to put the data type there. And views can be altered and dropped too. Another topic is updating view. In general, you should avoid updating views, and some DBMS don't even allow you to update. But there are scenarios where you can only see views. You cannot see the underlying table. In this case, you may want to update. If you want to update a view that's based on one single table, that's doable if a DBMS allows it. You can update the row and column. And if you update some columns, in the view, other columns that's not in the view will be populated with null. You can updating join-based views, but this can cause confusion on which table to update. Because if I'm updating, for example, instructor name, what is the table that's containing this instructor name if I use both course and instructor in the view? So this is not recommended. It won't always work. Similarly, you are not supposed to update aggregation views because Aggregation views, the result comes from aggregation. If I'm trying to update the sum of a tuition, where should I update it to? Should I update it in one column, one row, and make all the change there in that row? Or should I spread the change over all the rows involved in this group by? There's no fixed definition on that. So in general, you should avoid updating views, and you should always avoid updating join-based views or aggregation views. Let's try one example of creating view in Oracle Live SQL. So this is the query we talked about, select star from instructors, where instructor affiliation equals to Jedi. We will create a view. This is a keyword. This is a table. This is a view name, Jedi instructor S. Run it, and the view is created. You can use the same, you can use the view same place as in the other tables. I can select star from this Jedi view. Oops. And once I select them, I may want to where instructor name equals to or like Yoda %. And it's returning only Yoda. Now, you can use all where, group by, join, having, order by on a view, same as if they are a table. The difference between a view and table is that view, as you can see, is based on a query. You are not inserting data into view. View is just a query sitting there. Every time you run to select something from a view or update something from the view, or a DBMS will run the query and fetch the data, and as if it's actually something running inside. For example, here, if you think about how DBMS execute that, DBMS actually will replace this view name with a view definition. I'm not sure whether you can run this. I believe you have to have an S something. Oh, so Oracle actually can accept it, right? So it's a select star from, in some DBMS, you have to have an alias. In that case, it will be a dot select where. So this is what the view is, how Oracle or in DBMS in general parses view. They will just replace the view definition, the view name with a view definition, and start trying to run this SQL. In this case, it will be this simple subquery. All right, so much is for the view. I will see you in next lecture. In this lecture, we are going to go through non-permanent table. So when you run Oracle SQL, or actually any DBMS, when you run the SQL, sometimes you need to store temporary data somewhere in your user session. And that's when you still need to use a permanent table. Oracle provides the functionality called temporary table. Now, actually, all DBMS provide this functionality of temporary table, which exists only for the user session. You log in, you create a table, it exists until you log out. Once you log out, DBMS will automatically drop this temp table. So it is only used for you to do some temporary storage. If you want to keep the data after you log out in the database, you need to use a regular table. However, the syntax on creating temporary table is vendor specific. Oracle's syntax may not be working in SQL Server and vice versa. That's why we are just going to briefly introduce the idea of this temporary table. If you want to use it, you need to consult to your DBMS vendor manual on how to create that. In Oracle, it will be create global temp table. Instead of create table, you add a global temporary in front between create and the table. Then the rest is the same. The rest is the same as a regular create table statement. You will call it the my temp table or whatever. You can even call it my permanent table. But if you have a global temporary definition there, once you log out, this table will be dropped. Another interesting topic is common table expression, or CTE. Common table expression is created as a part of query. It's actually a subquery. For example, here we have two CTEs. Both are subqueries. You define them as a part of the query. So this CTE and CTE2, CTE1 and CTE2 are both defined before the main query, where in the main query, you will use CTE1 and CTE2 as subquery. This is actually very similar to the definition of view. And the Oracle will, or DBMS will handle it the same way as view. It will copy this CTE definition into here, and this query definition, this CTE definition into here when they start running this main query. So it's the difference between CTE and the view is that it's created as a part of a query, so it's effective only for a specific query. Once you stop running specific query, this CTE definition is gone. But why would you want some temporary query? There are multiple reasons for it. Sometimes you don't have the authority to create the view. Sometimes you have a huge query where the same definition of query is used again and again. As the same subquery is used again and again in multiple places. And sometimes, and the other reason is sometimes you want to use a recursive data set. How to use CTE and how and why to create recursive data set is beyond scope of this course. If you are interested, you can Google that. It should be easier for you to understand based on all the SQL fundamentals we have already learned. All right, so much is for the non-permanent tables. I will see you in next lecture. In this lecture, we are going to go through stored procedure. Stored procedure is a very important component of SQL. I would estimate half of the SQL usage is stored procedure. It basically put a series of SQL statements together in order and execute them one by one to achieve a certain functionality. But as important as it is, we won't cover that in depth in this course, because first of all, it's essentially a combination of simple SQL statements, everything we have already taught in this class before. Also, the syntax of defining a stored procedure is highly vendor specific. But the good thing is the basic logic is still the same. So we are going to go through some stored procedure examples so that you know what it is and how to use them. And in case you need to use them, you need to consult your owner's specific manual to have an understanding of the stored procedure function and the syntax in your particular DBMS. So when you use stored procedure, you basically define a series of SQL statements. You also need to define parameters. These parameters, some of the parameters, you will pass in so that the SQL statement can run against a certain value. Some of the parameters will be out so that it will return a value you can use once the stored procedure is completed. store procedure usually is done doing some select or update or insert functionality. You can also do create and drop or delete in these procedures. However, you should avoid creating permanent objects in store procedure. If you have to create some tables, remember to use the temporary tables. So let's go to Oracle Live SQL again, and let's bring up some store procedure examples. This is the first store procedure we will introduce. It basically have two components. One is a select statement. Second is that this put line is similar to print. So the procedure have two parameters. One is the input parameter of course ID. Another is the output parameter of course name. When you run this store procedure, you specify the course ID, the input value. And in the first statement, select statement, DBMS will select course name from course table where course ID equals to your input parameter of course ID. And whatever course name you find out, it will be saved into the vCourse name output variable for you to use. And also it will also print out the vCourse name. Now let's create a procedure. And let's generate a SQL statement to run this store procedure. And you can see, when you run this store procedure, you specify one, which is the course ID. You also specify R, which we declared before as a, as a course name. So after execution, R, in this variable R, we will have the course name returned, which mapping to the course ID 1. But in our case, we're not using this R. We just run this procedure and check the put line, the print output. Let's run this store procedure. And that's what you see, introduction to the force. So this is a select the procedure, which will select things into certain values. A more common usage of store procedure is to update a table. And in this particular case, we create this procedure and have an input of course name, course ID, and the course name. Both are input parameters. We will update course table, set the course name equals to the course name you specified, where the course ID equals to the course ID you specify. So this update course will update course table on the row where course equals to your input parameter and update the name per your request. So let's create a store procedure and let's run this by using a begin end. In this update, we will change course ID 1 course name to my new course. So once we are done with running this procedure, let's select star from course and look at the row where course ID equals to 1. So now the row ID equals to 1 have my new course. All right, so much is for store procedure. Just remember it's important, but due to its highly vendor specific, we're not covering that. But you should know what it is. It's a combination of SQL statements. And what it does is it can run these statements per your input. Okay, I will see you in next lecture. In this lecture, we are going to talk about cursor. So let's talk about procedural processing of data. So far, all SQL statements that we have learned worked on data sets. And when we talked about sets, all set-based algorithms cannot handle processing between rows, For example, you want to get difference between this row versus the other, because there's no such thing as order between objects in the set. So you still need to have a procedural processing capability if you want to do row-by-row calculation. In SQL, in traditional SQL, this is done using cursor. Cursor will define a data set and process one row at a time. And this is the cursor definition. And just like a store procedure, cursor definition is highly vendor specific, but the basic logic is the same. We should define cursor based on query. Usually, it's comes with an order by, so that you know which row you should be expecting. Then you will start or initialize the cursor. Literally means loading the data into the cursor. Then you will loop through each row in the cursor to process each row. And usually you will store previous rows in variables inside the processing if necessary. Let's go to Oracle Live SQL, and we will do some experiments. So this is the cursor example. What it does, this is the declaration part. You have the select star from course, ordered by course ID. So it's ordered by primary key, getting each and every row from course. This is your declaration. And within, I shouldn't select only, because the beginning and end is a part of this cursor execution. And this cursor is actually defined on top of this beginning end. But once you have the cursor, you can go through for each course in the C course cursor, you loop through and print out the course name. So let's run this cursor, this beginning end, and that's exactly what it does. My new course, which we changed in our previous section, moisture farming, all these things, right? So much this is for cursor. Cursor is useful if you want to process row by row. Of course, here we are just printing out the course name. But if you want to have a variable containing the holding previous course names and doing comparison, that's perfectly fine, and that's exactly what the people have been using this for. But note, there are two things to note. First of all, cursor provides you a procedural processing power, but you do not necessarily need to have this power. A lot of students, they try to use, they come from a Python or Java programming background. So they tend to think all the data processing are procedural row by row, which is not true. When you do processing, always think first from a set operation part. Using regular SQL to do set processing, it will be much faster and much simpler. Only when you need to do row by row processing, comparing between rows, that's the only time you need to do cursor. Which brings up our second topic, that cursor is used less and less frequently these years. And the reason is because there's another powerful tool coming up, which is the window functions, which we'll cover in next lecture. I'll see you in next lecture. In this lecture, we are going to talk about window functions. What is the window function? Window functions return one value for each input row and a set of rows affiliated with that row, usually ordered. This set of rows is called a window. That's how window functions get its name. So comparing to aggregation functions return one row for a set of rows, whereas the window function returns one row for each input row. But of course, this input row has a set of rows associated with it. Let's use an example, which is rank. We are trying to identify for each student what's the highest what's the rank of tuition on course? Or I should say, for each student, what's the rank of course based on tuition? So what we are doing here is we have a partition by student name. This partition by student name basically defines the windows. The window is divided by student name. Each window has one student name. And within this window, we have course name and tuition. We will rank all the course based on tuition descending. This is how you get a rank for each student. This rank is probably the most useful window function. There are more to window functions. And in general, we have a series of row level window functions. Number one is row number, which will return. Once you order it, it will return the ID in which you increment row by row, starting usually by default start with 1, so that you know which row you are in if you want to perform row calculations between rows. Then you have rank, we just talked about, and we have dense rank. Dense rank differs from rank on how it handles equal values when it does ranking. We have n-tile, which will separate a data set into n groups based on the ranking. And similarly, we have percent rank, and we also have lag and lead, which calculate between different rows. So these are the row level window functions. They handle differences between rows, like rank or percentage. There's also something called running or moving calculation. A running calculation starts from the beginning of the data window. For example, a running sum for inventory. Inventory usually starts with 0. Then once you have an increase or decrease, it keeps on adding up from the beginning of time. This is what we call running sum. There's also something called a moving sum or moving average. A very useful financial indicator is a moving 10-day average or moving 5-day average. This means a sliding 5-day window in which you calculate your average. The moving 5-day average of yesterday, starting from 6 days before today, and with 1 day before today, which is yesterday. Then the moving 5-day average of today, starting with 5 days before, and ends today, which is the 0 day before today. Then the moving average of tomorrow, starting with 4 days before today, and 1 day after today. This is how we calculate the moving average. Let's use a rank example. Excuse me. So this is the window function example. Let's go to Live SQL. Then this is the student name, and this is the course name. We partition by student name, which defines the window. All the course name and the tuition pairs of each student. Then we order by tuition. Course will be marked with a rank. And here is the result. For layout Skywalker, there are 2 rows. Public speaking has the highest tuition. Introduction to the Force has the second. And similarly for Luke. So you divided, the window is based on each student. Within this window, you have 2 rows calculating the rank or 3 rows calculating the rank. That's how Windows function works. All right. So much for Windows function. I will see you in next lecture. In this lecture, we are going to go through DBMS operations. These are the operations in addition to SQL query execution that DBMS performs in order to make that system up and running and available and secure. These operations are highly vendor specific. For this reason, we're not going to go into depths on how to perform each functionality. However, we are going to tell you what it is and what it covers. So the first topic we cover is system catalogs. There's a central location in any DBMS to store all related information in DBMS, like what tables do we have? What tables have you created? What are their definitions? How many columns we have? If you remember Oracle Live SQL, there's a schema tab from which you can see how many tables and each table structure. All these comes from this system catalog. In addition to table definition, system catalog also checks user. How many users are there? Who can access them? What is the last time someone read or write to this table? All these activities are logged into system catalog. If you are a database administrator, you will rely heavily on system catalogs, but the table name of system catalog differs from DBMS to DBMS. So you will need to consult your owner's manual in order to understand your own DBMS. The next question we talked about is security. Security controls who can do what action to which object. And in our database's specific case, who is the identity. It's the user. You log in as yourself. Someone logging as himself or herself. And what you can do. Maybe the administrator can do drop table, and a normal user can only do select from. And which means access. I can see all the tables as an administrator, while the other student can only see his or her own tables. He or she cannot see other students' tables. This is access. That means who can do what to which object. We control the security by creating users and grant or deny access to or from objects. For example, I can grant select on certain table to myself, or revoke delete on certain table to student 1. These are the securities you need to control, and this is the part of administrator's daily work. Another thing administrators always does is to define index. What is index? Index is a lookup list for row entries to speed up SQL execution. By default, all tables are indexed by primary keys. If you want to define index on other columns, you need to explicitly define them. And usually, indexes are commonly defined on foreign keys to help join. Now, index is more art than technical in most cases. But these years, as artificial intelligence picks up, we see more and more databases claim they can do query optimization without indexing. So again, you need to go consult your own DBMS manual to see what you can do or what you cannot do on this index front. And finally, we have this integrity constraints, which will control what can be placed into column. You can have primary key, which means this column is a primary key, and you can have a not null, which means this column cannot contain any null, which these two we already covered. And you can also have others like unique, means the value in this column has to be unique. And the foreign key means this column should have the same value as the primary key of another table. And check is more flexible. You can define value range. You can define something like or between and. All these you can check on your owner's manual and make sure how this works in your system. All right, so much is for DBMS operations. We will not go into, like we said, we are not going into detail because these are highly vendor specific. Make sure you consult your owner's manual and understand what is going on. Okay, and in next lecture, we are going to talk about a final project, and I'll see you there. In this lecture, we are going to have a quick final review. We are going to review what we have learned, and we are going to lay out a plan for the final project. So we talked about SQL throughout this course. We talked about data lifecycle. How data exists in computer system. It starts with a create, then followed by read and update, and ends up with delete. And we have a corresponding SQL statement for each of this stage. We have a create and statements for the create stage. We have a select statement for the read stage. We have alter, update, insert, and delete for updating data. And finally, we have a drop statement for delete. This is the generic life cycle of data in any computer system. We just use our corresponding SQL statement to make this functionality available in a relational database. As for the final project, we will still use the same insurance claim invoice example, but this time, because we already go through the midterm project of creating the table and populating data, I will give you a set of SQLs to create and populate the tables. You just need to write statement for a plot of select statements. So this is the original data, and we have a claim invoice with a customer, which is a patient, and the provider. Provider also have a provider association associated with it. And this is a data model of a patient is a one-to-many parent of claim. Provider is a one-to-many parent of claim, and provider association is one-to-many parent of claim. And we will go through the questions too. So here, I already provide you with the create tables statements and the delete statement and insert statements. There are 20 questions in total. All of them are some kind of select. You will get a list of the providers. You will check how many claims and find out this and find out that. And eventually, you will go through all the group by and join statements we talked about in the second half of this course. And finally, you will do a one window function and the one stop procedure. All right, have fun with this project. So in this lecture, I'm going to go through my sample answer to the final project questions. And again, data modeling is part art, part technology. So there might be many different answers to the same question, whereas all the answers may be correct. I'm just showing you what I think is correct, what the way I look at the question. Feel free to come up with your answer. And if you think my answers are not correct, feel free to raise it. So first of all, let's create tables and insert data. This already provided in the question text file. So let's create the tables, insert the data. Now let's start working on the questions. So the first question is, get the list of all providers, ID only, provider ID, in claim table. That means what? Select provider ID from claim. And it says each data only showing once. That's a typo, but you get what it means. So what should we use? We should use select distinct. That's right. And apparently it works. So the second question says, check how many claims the claim table contains, which will bring up select count. And we can use count star because within this claim table, each row is a claim. So here we can use a count star. If we have a claim ID as a primary key, then yes, you can also use select count claim ID. Count star is basically the same as count primary key because primary key will not be now. And let's run this. And it works as 4 rows. Now, questions number 3. Find out the highest coverage of patient for each provider. So coverage is one field. Highest coverage means maximum coverage. Of course, you need to do select. But it says for each provider. What does that mean? If you still remember how to write a SQL, we mentioned that for each provider means you should group by provider ID, right? So we will also put whatever is in group by to group by to a select. I missed the L. That's why the color is not right. So we run this, and for each provider, we get a maximum of the coverage. Question number 5. For each provider, find out the patient count. Oops, I didn't write this down. Now, question number 4. For each provider, find out the unique patient count. What does unique patient count mean? It means it's a count distinct patient ID, right? It should be from claim. That's the only place where provider and the patient meets. And we already said it's for each provider. So it's group by provider ID. And whatever you put in the group by, don't forget to put it into the select. So question number 5, it says, same thing, for each provider, find out the patient count in history. However, it does not mention it's a unique patient. So in this case, we will just use a regular count instead of a count distinct. You want to run this. What if we run both? So the first row returns 211. The second row also returns 211. So because that's due to our data, there's no duplicated patient for each provider. Now, question number 6. For each patient with total fee charged less than 200. Total fee charged means the sum of fee charged. Sum of fee charged less than 200. What does that mean? It means it must be in the having clause. And once you see having, and you also see for each patient, that means it's a group by patient ID, which should also be in select. And apparently it's a from claim table. It says find the total balance, right? So that means for each patient, you need to find the total balance. Total means sum. So there's only one patient with a fee charge less than 200. And for this particular patient, the sum of balance is 30. Question number 7, list all provider association names with the count of their provider. That means it's a provider association. This is from this table. where you have the association name, right? You also need to count provider, right? That means you are counting provider name or ID. Let's just put ID. But once you see this provider ID, it comes from provider table, which means you need to join these two tables. So if you still remember, once you identify the tables involved, you need to put one after from, and let's put a PA as the alias, and join, let's put a PA alias. And once you have join, of course, you will have on PA dot association name, I think. Association ID, actually, equals to once you have this join and you have association name and the count provider ID, you also need to group by association ID name and put select. That will list all association names with the count of their providers. All right. So question number 8. Find out the provider association in which claim count is more than 1, sorted by registration count and highest first. Okay, so that means find out the provider association. You need to group by provider association in which claim count, because basically you have a count, right? That means the count star. Oops. For each provider, there will be association name count, and apparently association comes from association name comes from association table, and the count comes from claim table. So you need to join from claim to provider association table. However, there's no way we can join these two because they don't have common columns. That means we need to find some other table in between so that we can join. And we all know this should be provider table. P. So C joins P first. So P, and then P can join PA. Let's copy this over. Now, once you have a group, this will be select. And don't forget PA.PA association and count star. Now, once you have this join and group by, don't forget which claim count is more than 1. And that brings up having. And you need to sort it. Remember to put order by. I see students using sort by or sorted by. Order by is the only one. And once you want to use order by, you need to order by count first. And because highest first, it should be descending. And I believe I made a mistake here. It's not registration count, it's claim count. I copied this from my Data Academy, the Data Force Academy questions. So this is how we do it. Let's run. And that's the result. Okay. Question number 9. List all patient names and each patient's total balance. So there will be total balance is sum of balance, which comes from claim table and the patient name. And patient name comes from patient table. So there's a claim and the patient, right? Then we'll also be asked about provider association's name starting with C, which means we will need to go into the association table. That means we will have a claim table, patient table, provider table, and the provider association table. So let's put the patient as use PT C, and there will be PT dot. There will be from claim join patient. On C dot patient ID equals to PT dot. Then this becomes a star join, or we can even say that's a snowflake join, because now we have a provider ID equals to P dot provider ID. Now we have a chain join here from provider to provider association. We have the from and join, and we need to have a where, right? Where association name, it comes from PA. So association name start with C, like C%. I hope you still remember why we are doing this. And now you need to group by patient name. And don't forget select. So this brings up a snowflake join with where clause, where from, join, on, and where forms the detailed data set, and the group by will give you the aggregation. This is how you get it. Okay, question number 10. List all patient names and each patient's total balance for patient with balance more than 10. Patients with balance more than 10, that apparently comes from claim table. And then you have a patient name. And you also need to list the patient names and total balance, sum of balance, right? So once you have this column and table, you know you should start with the from, joining patient. Let me copy this over. Don't need to type this anymore again. And it will be PT dot patient name is where I want to group by. And make it more complicated is that for patients with balance more than 10, that will bring up having, because it's a total balance more than 10 for each patient. That's why it's having, it's not where. More than 10. And we do a select. And yes, balance is 30 and 111. Now, number 11. List all providers' name with their provider association names. If the provider association's name does not exist in provider association table, show now for the name. What does that mean? That means it's the outer join. Show now for it, for the missing name, right? So we will do a provider, joining provider, alias P, joining provider, association, PA, be from. Is that left join or right join? Because it says if the provider association name does not exist, that means the provider, all the information in provider must be showing, where provider association's name can be different, can be missing. So it's a left join from provider to association. And we can still copy this join on. And we need to select P dot provider name and the PA dot association name, right? So let's run this SQL and we will see some nulls. Yes, we see only one, right? Now the next question, number 12, says, redo question number 11 using different approach. And the way I mean that is that we should use, we can use right join. Instead of left. But once you change that to right join, you need to switch these two tables so that you are still joining from provider and keep all the data in provider. And for missing data in provider association, you can use now, right? And we're getting the same data. Okay. Question number 13, list all provider names if a provider association name starts with C. Provider name and the provider association name come from two different tables. So you are displaying data from one table filtered by data from another. And the first thing come to your mind should be join. Well, let's do a from join again. I just copy this over and remove the left of the join. This is the two tables joining, and we need to check for where PA dot association name like C%. Again, if you don't know why we use this like C% for question like starting with C, you need to go back and review the where clause session. Okay. Now the question comes, redo question number 13, use a different approach. And here we can use in. And how do we use in? We will select from provider where something in, right? What's this something? It will be what do we associate these two tables with, which is the association ID. And accordingly, we also need to specify select PA's association ID from this PA table. And don't miss this where clause. Oops. And question number 15 asks the same question using still a different approach, which certainly brings up where exists. So what we are going to do is here, we will do where exists. And by doing exists, the first thing you do is to select star from another table, which is the provider association. And you need to apply the where clause first. And now you need to associate main query and subquery next. That's where you have the end. Now let's run all these three together at the same time and see the result. So the first one returns Maria, second one returns Maria, all of them return the same result. So we know they are equivalent. This is question number 15. Question number 16 wants us to create a view based on the result of question number 16. Oops, I think I actually means number 15. Not 16. Actually, a high balance, that means it's number 10. This is the someone with a high balance. Which means the sum balance is greater than 10. Okay, let's create a view. High balance patients, and because it has two columns, you can just do things like the S. You can also add a column list. Patient name, patient balance. And that's how you define the view. View created. Number 17, find patient with a claim from provider 1, but no claims with provider 2. So you will select patient ID, not JD, from claim where provider ID equals to 1. And the other set is provider ID equals to 2. So you should have someone from this one, but not this one. So you do that by adding minus. And when you run the result, when you run the SQL, the result will be this person, he or she only have one record in the claim table, which belongs to provider ID 1. The other patient in the claim table has both data from provider ID 1 and provider ID 2. So the question now is, redo question number 17 use a different approach. And by doing this, what I mean is, you can also use two where clauses. Same where clause, but you can use the and not operator between two tables, between two select in from subqueries. So that will be where patient ID in. This will be patient ID with a claim from provider 1. And not patient ID equals to select patient ID where provider ID equals to 1, equals 2. Oops, 2. So let's run both together and see the result. Oh, I think I missed, I missed the patient ID in. So let's run this two statements together. Both return the same value, right? So question 19, you want to rank provider for each patient based on their balance highest first. So I'm going to just copy because this rank is a little bit, it requires more typing. I'm just going to copy what I have created before. It basically comes from the same rank function I introduced in the PowerPoint slide, where you have select patient ID for each, because you have this partition by, you have the patient ID, and you're breaking this into provider ID, you're breaking the data set by patient ID. For each patient ID is a window. Within this window, you list provider ID with balance and order by balance. Thus, you get a balance list based on provider ID. So let's run this. So for 001, provider 3 have the highest balance. Provider 2 has the second highest balance, and provider 1 is lowest. Similarly, for number 20, we just select and create table and create a stop procedure. Stop procedure created. Let's run stop procedure. It says use the stop procedure to provide a 10% decrease to all balances. Now remember, this is the balance line. So it's a 19101 something. Let's run the update and let's select again. All these are updated, right? And the reason that it's updated is because in here, in this procedure, we have update claim set balance equals to balance times %. This percentage is what we pass in. In this particular case, we're passing 0.9, meaning we want to have a 10% decrease. Okay, so far, this is all for our final project. In next lecture, we're going to give a really quick overview of where we are and where to go next. And that will sum up the whole lecture. I'll see you in next lecture. So by going into this lecture, you have already completed the whole content of this course. You have already learned all 7 different SQL statements. And now you will be able to write simple SQL queries against these particular questions. So what's your next step? Your next step should be putting your hands on more SQL questions and have more practice. SQL is a highly practical, highly hands-on skill. If you don't use that, you will forget very soon. So I recommend you either try to use it in at your work, or you should find some other project to keep yourself fresh. All right, so much is for this course. Thank you and good luck.